Welcome to the ARM Microcontroller Masterclass, version 1. This course aligns with university-level classes such as Embedded Systems, Microprocessor Architecture, Digital Systems Design, and Introduction to Electronics Programming. It also serves as a prerequisite for advanced subjects like real-time systems, embedded C programming, IoT device design, and hardware-software integration. And it will be updated regularly with enhanced editing of this video for brevity and clarity, and additional projects that have yet to be added. So make sure to subscribe to stay updated on the latest videos, revisions, and new lessons. Now here's what you'll learn in this course. We'll begin with an introduction to bare chip development, learning to work directly with ARM microcontrollers at the register level. Then we'll go through the prototyping setup, software setup, an introduction to STM32 IDE, and how to create a project in the IDE. We'll learn transferring the program to the microcontroller and using STMStudio to monitor and visualize data. Next are real troubleshooting scenarios. Then the four most important code instructions, changing and testing bits. After that, we'll begin the projects. Turning on an LED, the hello world of MCU projects, receiving input from a button, latching an input, interfacing an LCD display, sending integers on the LCD, sending floating point numbers on the LCD, and setting the location on the LCD. We'll then move on to analog to digital conversion with ADC conversions using the internal temperature sensor, converting the ADC value to a meaningful number, temperature, using a potentiometer as the ADC input. Next, we'll tackle timers and counters with Prescaler, where it skips oscillations, and auto reload register, count direction, and center aligned mode. Then we'll explore PWM, pulse width modulation, introduction to PWM signal generation, creating an ADC header file, control PWM operations with the ADC, control the dimming of an LED using PWM and a potentiometer, control a Hobby Servo with the PWM output, control a Hobby Servo with a potentiometer connected to the ADC. Then we'll move into interrupts, introduction to interrupts, using interrupts for ADC conversion, using interrupts for ADC conversion with 2 channels, fixing an artifact on the LCD, push-button interrupt, internal interrupts on 2 pins, switching output to STMStudio rather than the LCD. Then we'll cover communication protocols, introduction to I2C communication, communicating with the ADXL 345 accelerometer using I2C, writing a single byte, communicating with the ADXL 345 accelerometer using I2C, reading a single byte, introduction to USART and other communication protocols, changing the clock speed to 48 MHz because we'll be using that with the USART, and then transferring using the USART. By the end of this masterclass, you'll have completed over 25 hands-on projects, mastering the STM32 architecture from registers to real-world applications. This is version 1, and new modules and hardware demos are always on the way. All of the chapters and projects in this course can be easily navigated using the timestamps in the description below. This is the most comprehensive instruction on the internet in video form for this subject. If you'd like to delve deeper into more advanced topics like sophisticated PCB design, higher level programming using the HAL or Hardware Abstraction Layer, or CubeMX, check out Phil's lab. I've left a link in the description. This is an STM32 microcontroller. It is an ARM-based chip. So what is a microcontroller? A microcontroller is a device that can receive input, as in ones and zeros, and communication from other devices like a computer or from various devices that provide different types of communication. It can receive an analog voltage using the onboard analog to digital converter. So it takes an analog voltage, which could be anywhere between 0 and, let's say, 3.3 volts, and convert that into a digital number. The microcontroller can also output. It can create an output in the form of a 0 or a 1. You can control devices using this type of output, like say turning on an LED or turning off an LED, communicating with devices like an LCD, turning on and off various digital lines of an LCD. You can also output a digital-like analog signal called a PWM, where it outputs a digital signal that can be between 0 and a voltage reference like 3.3 volts and anywhere in between. One of the coolest things about the microcontroller is that you can sense the environment, and that's part of an input. Specifically, it could be you're sensing temperature, and the temperature would be converted to a voltage, and then you can convert that voltage into a number on the microcontroller specifying the temperature. You can also control much higher power devices. Microcontrollers are everywhere. They're used in almost every electronic device that would be inside of a home or inside of your car. These microcontrollers are used in smart home devices and the Internet of Things, wireless devices, washing machines, TVs, monitors, computers. It controls the efficiency of your engine in your car. It's used in robotics. It can also be tied together to create a much more complex system. Used in critical applications where lives are dependent on the functioning of the microcontroller. If you were starting your project from the actual chip itself and building from that chip out using only the components that you need, then you've already built in a more efficient design for the project. When you're developing from the bare chip, you're not bound by any specific chip. As long as you know the fundamentals of programming from the bare chip. There's a wide selection of ARM-based chips out there, and there might be some variations in the datasheet, but that's easy to just reference when you need to. The programming that you have to do to make an Arduino work and the program that you have to do to make a chip function in the same respect as the Arduino is very, very similar. So the microcontroller that I'm holding in my hand right now, it's obviously very difficult to interact with this microcontroller the way it is here. Microcontrollers can be broken out into pins like this, where you just plug this into a breadboard. And breadboards are used for prototyping, where you develop your circuit on the actual breadboard itself, where you have all of your discrete components taking advantage of the pins of this microcontroller. This is an example of how you use the microcontroller. So you have the microcontroller like this that is in the middle of this circuit board here. This circuit board is only the microcontroller, and it's broken out into these pins. That's it. There's no other components on this circuit board, so you know that you're designing specifically for this chip. And then when you go to create your product, all of the components you add around the microcontroller, you can easily design in your PCB designing software when you decide to put out a product. The device that allows you to connect the computer to the STM32 microcontroller is the programmer, and it allows you to send the programs that you create to the microcontroller. The programmer also allows you to connect the microcontroller to the STMStudio to monitor the variables that you wish, to graph the variables that you wish, and also to debug the program while it's running. ST also make a programmer like this you can purchase if you're looking for something that is directly from ST Micro. The device provides 3.3 volts of power for the microcontroller to run. It also has a 5-volt power if you need it. And it has two data lines. One is a clock and one is an I/O. These two work together to communicate between the computer and the microcontroller. The power pins of the microcontroller need to be connected to multiple pins on the microcontroller. These two pins here, these two pins over here, and this one pin over here. It can also be connected to a couple pins over here that's used for the analog to digital converter, but you only need to use them when you're using that converter. To be able to power the pins that are around the microcontroller, you need to connect the breadboards all together on the power rails. There are two power rails, one for the plus and one for the minus. And then those pins are connected to those power rails. Pin number 64 is a positive pin. And you'll want the 3.3 volt positive pin from the ST-Link V2 to be plugged into that pin. The ground pin will be connected to pin number 63. Pin number 63 will go to the negative rail. The positive and negative rail will be connected to this next breadboard, negative rail to negative and positive to positive. Pin number 31 will connect to the negative rail, and pin number 32 will be connected to the positive rail. You'll also want to use a 0.1 UF capacitor between pins number 31 and 32. Pins number 63 and 64, and pin number 1 is a positive pin, so it needs to be connected to the positive rail, and you'll have a 0.1 UF capacitor between the positive and negative on this rail, so it's as close to this pin as possible. And these two breadboards need to be connected for power as well, so positive goes to positive and negative goes to negative. So when 3.3 volts and ground is connected to these two pins, it will power the rails along the entire length of the power rails on all of the breadboards. The SWCLK, which is the clock, will be connected to this pin here, which is number 49, and number 46 is SWDIO, which is the IO pin. You can see those two pins here, SWCLK and SWDIO. And this diagram here corresponds to the pins in the back of the ST-Link. You can put a 510 ohm resistor and going to ground on the boot 0 pin, and that boot 0 pin is pin number 60. I'm going to show you how to set up the software environment, the IDE, which is the Integrated Development Environment. This is where you're going to write the programs that's going to be put into the microcontroller to make the microcontroller do something. The IDE also allows you to transfer the program to the microcontroller. I'm also going to add 2 other programs to this arsenal of programs, and those are the STMStudio and the STM32CubeMonitor. Both of those programs will allow you to monitor what's going on inside the microcontroller in real time. So you can see what's going on, look at your variables, and in the STM32CubeMonitor, you can also control, you can actually make changes to things in the microcontroller. The IDE I'm installing is called the STM32Cube IDE. The IDE is based on the Eclipse IDE and modified to work with the CubeMX by STMicro. Search for STM32Cube IDE and click on the link from st.com. On that page, scroll down below the description and a list of available downloads will be shown. I'm installing the Windows version. You will need to accept the license agreement and either log in or provide your name and email to continue with the download. The download will be in the form of a compressed zip file. Go to the file location and double-click the zip file to open it. I'm going to run the setup application directly from the zip file. The setup wizard will start. I am maintaining all default values for my installation, including the drivers for the ST-Link and J-Link. Now I will add the STMStudio and the STM32CubeMonitor. Both of these programs will allow you to monitor what's going on with the microcontroller. With the STMStudio, it's very simple. You can monitor variables and you can show the variables in some state like a chart, a line chart, a table form, and a bar chart. With the STM32CubeMonitor, you can not only look at variables, but you can also change and control the microcontroller while it's running in real time. So you have much more flexibility with the STM32CubeMonitor than you do with the Studio, but sometimes just going to the Studio and checking a variable really quickly makes a little bit more sense, depending on the scenario. I will install STMStudio first. Search for STMStudio and click on the link from st.com. STMStudio gives you the ability to read and display variables in real time while the microcontroller is running. The download is below the description of the program on the web page. Click the Get Latest link to start the download. You may need to either log in or provide some information, including accepting the license agreement. Open the compressed zip file that was downloaded. I am double-clicking directly from the application in the zip file. STMStudio requires the installation of the GRE, Java Runtime Environment. The program links to the Java Development Kit, but I have found that this does not work. To correct for this problem, you'll need to search for the Java Runtime Environment and install that program instead. You can see here that I installed the Java Development Kit, which is where the installation links to when I click the Yes button. And when I restart the installation of the STMStudio, it repeats the instructions to install the Java Runtime Environment. So here are the instructions on how to install the Java Runtime Environment instead. Search for the Java Runtime Environment on the internet. Click on the link under java.com, Java Downloads for all operating systems. You will be taken to a rather technical and non-adorned page with the download links. I am using the Windows Online link to install the Java Runtime Environment. Once the download is completed, click on the download and follow the installation instructions. Once the Java Runtime Environment is installed, STMStudio should have no problem installing completely. I am restarting the STMStudio installation. I'm also keeping the default values throughout the installation process. The installation creates a desktop shortcut. My shortcut is hidden in the sea of icons on my desktop, so I wasn't able to find it very quickly. So I use the Windows Start button to start the application. This is what STMStudio looks like. It is a relatively simple application. You specify the file associated with the program that is on the microcontroller, specify the variables, and view the variables in your choice of a bar graph, line chart, or table view. Now let's install another type of monitor called the STM32CubeMonitor. Like the STM32Cube IDE is based on the Eclipse IDE platform, the STM32CubeMonitor is based on the Node-RED platform. The STM32CubeMonitor allows you to view variables, but the application also allows you far more control over the microcontroller. You can create your own dashboard to control various aspects of the microcontroller while it's running. I will install the Windows option. Follow the same process as with the other applications. It looks like I downloaded the application twice. I think it is letting you download without logging in or providing the name and email information. After the download is completed, you will need to extract the files, so the installation process uses uncompressed files. I just created a temporary folder on my desktop and extracted, or clicked and dragged, the files into this new folder. From that folder, I can double-click the setup application. As with the other installations, I'm keeping the default values. When the installation finishes, it will launch the program automatically. If you are running this under Windows, some of the features of the STM monitor will need access through the firewall. If you are okay with this, click on the Allow Access for either public or private networks. This is what the program looks like when it starts up. You can start the IDE by clicking on the icon labeled IDE. If you have a special place where you want to hold your files and your projects, change the workspace location. I'm keeping it as the default. This message will only appear if you have a previous installation of the STM32Cube IDE. If you have another instance of the IDE, go ahead and click Yes if you want to associate your project files. When you first open the IDE, you'll be presented the Information Center. In most cases, you won't be using the screen, but let's go ahead and click on the Start STM32 project from here. You'll need to select the chip that you're going to be working with. There are so many selections that you will need to use a filter to reduce the number of selections so you can find the chip. The one I'm using is at the top, so it's pretty easy to find, but you can filter using the ARM core type, the series of the chip, like F0, F1, L1, the ST micro product line, the package of the chip, like how many pins that the chip has and the size of the chip. For instance, we are using the LQFP64. The filter labeled Other allows you to filter by specific attributes of the chip. And finally, you can filter by the feature or peripherals that the chip contains. Say, for instance, you wanted the chip to have USB functionality. This is where you would go to find the chip that you need. Now that I know where my chip is, I can go ahead and click on it and press Next. The IDE will start the project creation wizard. You'll need to put in a project name. I'm naming this project Test, Studio, and Monitor since that's what I'm going to be doing. The target language will be C. I want this to be an executable, not a static library, and it'll use the STM32 cube rather than an empty type. Click on Next, and on this page, you can leave everything as default. The code generator options might be something you will change in the future, but in this case, I'm leaving it default. Once you click the Finish button, the project will be created, but it'll also ask you if you want to open the perspective view, and I always click Yes for this. This is the screen you'll be presented when the project is created. This is the .ioc file that is shown that has the microcontroller and the pins in an interactive graphical representation. If you want the initialization code to be auto-generated, this is where you do it. The initialization code is generally just setting up pins and timers and other features of the chip. In the Project Explorer, I'm going to open up the source folder and double-click on main.c. Let's go ahead and click on the Start STM32 project from here. You'll need to select the chip that you're going to be working with. There are so many selections that you will need to use a filter to reduce the number of selections so you can find the chip. The one I'm using is at the top, so it's pretty easy to find, but you can filter using the ARM core type, the series of the chip, like F0, F1, L1, the ST micro product line, the package of the chip, like how many pins that the chip has, and the size of the chip. For instance, we are using the LQFP64. The filter labeled Other allows you to filter by specific attributes of the chip. And finally, you can filter by the feature or peripherals that the chip contains. Say, for instance, you wanted the chip to have USB functionality. This is where you would go to find the chip that you need. Now that I know where my chip is, I can go ahead and click on it and press Next. The IDE will start the project creation wizard. You'll need to put in a project name. I'm naming this project Test Studio and Monitor since that's what I'm going to be doing. The target language will be C. I want this to be an executable, not a static library, and it'll use the STM32 cube rather than an empty type. Click on Next, and on this page, you can leave everything as default. Once you click the Finish button, the project will be created, but it'll also ask you if you want to open the perspective view, and I always click yes for this. This is the screen you'll be presented when the project is created. This is the .ioc file that is shown that has the microcontroller and the pins in an interactive graphical representation. If you want the initialization code to be auto-generated, this is where you do it. The initialization code is generally just setting up pins and timers and other features of the chip. In the Project Explorer, I'm going to open up the source folder and double-click on main.c. This is the main entry point of the program and where you'll do most of your programming. The IDE adds a lot of comment lines, so I'm going to remove those, since in these tutorials I'm going to show you where much of the coding will need to happen. The removal of these comments isn't absolutely necessary. I am removing anything with a /, asterisk, message, asterisk, and a /. So if you want to do this, go ahead and just remove any of those types of lines that you see. The purpose of this program is only to introduce a variable so I can monitor that using the STMStudio or the STM32 CubeMonitor. Let's add a variable called test seconds. This variable will need to be a volatile variable. The volatile keyword is added just so the compiler doesn't optimize this variable out. And I'm initializing it as 0 so the compiler can infer that this is an integer. The test seconds variable will be updated in the while loop, which is the never-ending loop. But I don't want it to be updating that quickly, so I'm using a delay that is available from the HAL library. You may have noticed the list that appeared below the HAL delay while I was typing. I used the Control spacebar to get that list, so it'll be a little easier for you to find the functions and variables available to you. This delay is in milliseconds, so I'm using 1000 milliseconds to equal 1 second, and I'm going to increment test seconds by 1 for each iteration of the while loop. Now we are ready to run the project, which is transferring the program to this microcontroller and monitoring the variable we just created. To do this, we need to plug the computer to the programmer, and you'll hear the notification on the computer that something has been plugged in. If this is the first time you're plugging it in, it'll take a little time to install. So just follow the prompts you have with Windows to make sure it's installed correctly. When you are running the program, or transferring the program, or some kind of communication is happening with the ST-Link and the computer, there will be a red and blue LED that blinks back and forth. And there is also an error condition. I think the error condition is both blue and red are on at the same time. So let's go ahead and transfer the program to the microcontroller. Use the play button to initiate the transfer of the program and execute the program on the microcontroller. When you do this for the first time, the run configurations will appear. You can also see the run configurations dialog if you press the down arrow next to the play button and select Run Configurations. In this configuration dialog box, click on the Debugger tab. You want to make sure that under the Interface section, SWD is selected. The ST-Link serial number does not need to be populated. If you want it to, just press the Scan button. I set the reset behavior to none. You may need to set it as under reset. If you are having problems connecting to the target in this case is the microcontroller, then make sure that the connections to the microcontroller are correct and that they're solid. You'll have messages like cannot erase memory or cannot connect to target. Those are all signs of a bad connection from the microcontroller to the ST-Link V2 programmer. After pressing the Run button from the dialog box or pressing the Play button, all of the information that gives you the status of the ST-Link and errors in your program will be in the console tab on the bottom of the IDE. You can see here that I received a target comms error, and that's because I didn't have the USB cable plugged into the ST-Link programmer. In this case, it said, error, failed to erase memory. This was because my SWDIO was not connected securely to pin number 46. Sometimes you'll get an error that has to do with the GDB server. This is due to having multiple errors happen when trying to connect to the target. What you need to do is unplug the ST-Link and plug it back in, and then do the run again. I created these errors intentionally so you can understand what action to take. This is what the console will look like once you've successfully programmed the microcontroller. The status will have file downloaded complete, verifying, and download verified successfully, shutting down, and exit. Now let's start STMStudio so we can monitor the variable that we have in the microcontroller. Make sure the ST-Link programmer is still plugged in. We'll use the top pane of the display variable setting. Click the right mouse button and click on Import. We will need to locate the ELF file for the project that we just created. An easy way to do this is to go into the binaries folder of the project that we have in the IDE. Right-click on the ELF file under the binaries and click on Properties. Under Properties, you'll see the location. Just select the entire location, including the ELF file, and copy to the clipboard. You can cancel that to get out of that and go back into the STMStudio. The ELF file contains all of the information about the program, including information about the variables. In the STMStudio Import Variables from Executable dialog box, click on the ellipsis button and paste the clipboard into the file location text box. Don't worry about the unknown symbols error message that pops up if you get one. A list of variables will be shown in this dialog box, and you'll select the test seconds variable. Clicking the import button will add it to the STMStudio. We want to send this variable information to the var viewer 1, which is the chart to the right. Press the play button at the top to start monitoring the variable. You can see that the test seconds count got up to 100, or around 100. That's how many seconds it took me to import the variable into the STMStudio. You can zoom in and out of this chart using the mouse wheel. In the display section of the STMStudio, you can select how you want to see the variable, as a chart, a bar graph, or as a table. What would happen if we went back to the program and removed the HAL delay of 1 second? Since this number can get quite large, I made it an integer data type. I'm going to rerun the program, make sure that the ST-Link was able to transfer the program successfully, and go back to the STMStudio and play again. In this case, I had to zoom out quite a bit using the mouse wheel, and you can see how fast the variable is climbing. Now let's try the same thing in the STM32CubeMonitor. Start the STM32CubeMonitor by double-clicking on the icon labeled MON. You'll need to allow access as before, and you'll be presented with the Node-RED flow diagram. This is the request, and this is the response. The probe is the ST-Link, so we need to create that or add that. Click on one of the probe nodes and click on the pencil icon on the probe config line. Click the drop-down in the probe name to select the ST-Link. We're going to go ahead and add. Done. You can see that the little triangle, the red triangle, has disappeared. So we're going to go ahead and do the same thing with this. We're going to select the same probe, add, and done. Okay, so those are good. What this is doing is it's creating a dashboard. These are buttons. You can see by this little finger icon. This is where we're going to create the variables. We have our test seconds as a variable, so we can use that. And then it's going to send that to the probe or the ST-Link. And from the ST-Link, once it's passed its request, it's going to create a response. So this is, some people call this a transmit and a receive. So in the receiving side, or the response side, from the probe, it's going to go back into my variables, which we have to create, and it's going to go to the chart. And we can also use, this is another button, we can clear the graph. All right, so let's go ahead and put the variables in there. So we have to put in our executable. Let's try that first. So let's go ahead and get the executable, the binary. I'm going to go to the properties and select this path here. I'm going to use Control-C to copy it and Control-V, paste it. Let's see, actually, let's put the folder portion of it in the folder area. There we go. Oh, this is a name. Okay, we can name this something else. Just call it the Studio and Monitor. Let's go ahead and click on the test seconds and let's add it, and we're done. So this should be connected with this. So if I double click this, it should be the same. Just go ahead and done. Click on the deploy button to accept the changes and click on dashboard. You can see that our variable is climbing very quickly as expected. If you've gotten this far and you are still with me, congratulations. You are ready to start your journey in ARM microcontroller development. You've actually bricked the microcontroller, where maybe you've had an error in the program, or you've actually caused the program to do something unintended to the microcontroller. You may have bricked it. Pull the boot 0, which is pin 60, high, and you can use a 10K resistor to do this. And all you're going to do is pull it high using the 10K going to the positive rail. While the pin is pulled high, you would do a full chip erase or full memory erase. You'd use a program called the STM32 ST-Link utility. You can find the ST-Link utility just by searching for it, and it should be the first link, and do the download and installation. It's very straightforward. You can also use this program to program the microcontroller by just loading the file, opening the file, and selecting it from the debug and the binary file. So just double click that and you'll have the file loaded up in this program. It'll also show you the device memory when you have it connected. You can click on the connect to target and you'll see that it'll show you what's on the actual microcontroller at all the memory addresses. And you need to click on this icon to program it. The settings can be changed using this icon, and you can see that it has the firmware version. It has the target information, which is the actual microcontroller, and the mode should be in normal SWD, which is the CLK and SWDIO pins that are being used with this ST-Link. And I have mine set at 1.8 megahertz. And to do a full chip erase, you can use this icon here. Since those pins have been programmed as a function of digital output rather than the SWDIO and SWCLK for programming, there's no way for the STM32 ST-Link utility to actually connect to the chip to communicate with it. The only thing you're going to be able to do is get voltage to the circuit, but no communication can happen. So if you try to connect to the microcontroller, you'll see that you're going to get a message like this: cannot connect to target. If you're trying to connect to an STM32 device, please select normal or hot plug mode from target settings menu. And generally these recommendations are not going to help you. First, we need to find the reset pin. And on this development board, the reset pin is located on pin 7. So find pin number 7. We're going to put one end of the resistor on that pin, and I'm using a 500 ohm resistor. And then we're going to pull it down to ground, which will put the chip into reset mode. And then we're going to go to the link utility, and we're going to click on the full chip erase, which is a little dynamite button here. And you'll notice that it doesn't do anything, it just locks up. We're going to remove the resistor, and you'll see that the full chip erase is in progress, and it erases it successfully. So if I click on the connect to target, you'll notice that it connects perfectly fine. And we can go ahead and program it again, and you'll see that it programs successfully. Let me show you how I bricked my microcontroller so it doesn't happen to you. You're going to make programs, you're going to program microcontrollers, and you're going to have problems inevitably. So as long as you're not making mistakes like putting the wrong connectors to the microcontroller to permanently fry the microcontroller, you're most likely going to be able to resolve the situation. In making the video that I was intending to upload, changing the microcontroller's clock speed from 8 megahertz to 48 megahertz, every time I write the code in either the auto-generated code to do it or doing it through manual register manipulation, I brick the chip every single time. And it is only when I use the PLL clock. So I'll show you what happens when I do try to transfer this to the microcontroller. Doing it successfully. So it downloaded and verified successfully, but the target is not responding now because I've bricked it. I've put the microcontroller in a state that is broken. I cannot connect to the microcontroller. If I try to download again, you can see that it's in a state that I can download. So it's red, which is a state that it's connected. At least the ST-Link is working. So if I try to do it again, it's going to give me an error. And you can see it says target no device found. And you'll see it says failed to start GDB server. Error in initializing ST-Link device, but it's still red, so it says it's still in a ready state. So you need to fix the microcontroller first before you continue using it. And the way to do that is you have to do a full chip erase. So let me show you how to do that. And this full chip erase will solve 99% of the problems you'll have. You're going to use the STM32 ST-Link utility to do this. So I'm going to double click that. And there's a little dynamite icon. It says full chip erase. So that's what you want to use. And I'm going to be using a resistor connected to pin number 7. Pin number 7 is the reset pin for the STM32 microcontroller, at least this particular one. So you might want to look at the datasheet or the reference manual to see which pin for yours is reset. So I'm going to insert it into pin number 7 here. And then the other leg, the other side of the resistor, is going to go to ground. So the reason why I'm putting a resistor from 7 to ground is because I don't like to bring any pin to the full of 3.3 or the ground directly. I like to put it through a resistor. And this isn't from my own experience of having prior failures. This is from just responses from comments in YouTube. I just try not to do anything that's going to harm a microcontroller. So I want to try to keep it as safe as possible. So I'm going to go ahead and click on the full chip erase, but you have to be kind of quick with this. So have your finger ready. When I press the full chip erase, it's going to just pause for a moment and wait for you to take that out. So I took it out and you can see that it's going through a full chip erase. And now you can see the contents of the memory of the microcontroller. You'll also notice that the red LED is blinking, and that means that it's in a connected state. Before you do any further programming the microcontroller, you want to disconnect from target. So it's disconnected. I can minimize that now and I can go back. And if I want to, I can do another programming of my microcontroller. Because the PLL clock uses the VSSA and VDDA to power its clock, pins number 12 and 13 need to be connected to the power as well. Pin number 12 is connected to the negative, and pin number 13 is connected to the positive. I'm going to go ahead and press OK, and hopefully everything goes well. Okay, we didn't have any errors after the download verified successfully. I wasn't using the VDDA and the VSSA. Let's go ahead and take a look at those, the power domain, and show you why that didn't work. So this is the data sheet for the microcontroller that I'm using. We're going to go to the power supply scheme, the VDDA and the VSSA, which is the same, it's just positive and negative. The PLL uses that portion of the power. I didn't have those two connected, so I would immediately get an error here, and I would have to erase the microcontroller to be able to reprogram the microcontroller. I'm going to show you the lines of code that you'll be using the most. The way to control features and enable features and set features of the microcontroller is to control bits or turn on and off bits in registers. Bits are ones and zeros, and the microcontroller is made up of a bunch of registers, which is like a huge set of control panels with a bunch of switches. Each switch is like a bit. It's either on or off, a 1 or a 0. On is 1, off is 0. And the register has 32 of these bits. You will need to know how to turn on a bit or turn off a bit, or setting a 1 as a bit or setting the bit as a 0. You can also toggle a bit inside of a register. So if the bit is a 0, you can turn it into a 1. If the bit is a 1, you can turn it into a 0. You will also need to know how to determine what a bit is in a particular register. So, for instance, when you enable something, you need to wait until a flag or another bit is set before you move on in the program. So I'm going to show you how to write a line of code that will test whether a bit is 0 or 1 and wait until that happens. The example that I'm going to use in this project is to turn an LED on or off. There are multiple registers we have to affect and bits to set in these registers to be able to turn an LED on and turn an LED off. To turn on a bit in a register, or to set a bit as 1 in a register that has 32 bits in length, we need to specify the register. We're going to use the OR operation, which is the pipe character. It's just a vertical character, and equals, and the bit that we're going to be setting, making a 1. To set a bit to 0 or false or resetting a bit, they're all the same, you're going to use what is called the AND NOT operation. So you're going to specify the register, you're going to specify the AND sign or the ampersand sign, equals, and then a NOT symbol, which is a tilde, and then the bit. Toggling a bit, you're going to be specifying the register and the caret character, equals, and then the bit. If we are waiting for a particular bit to become a 1 or a 0, you're going to use a line of code that starts with while, which is while a condition is true, keep looping until that condition is false, and then it'll get out of that loop. And the condition within this while loop is the register and the AND sign and the bit, and whether that is equal to 0 or 1, or whether that is not equal to 0 or 1, however you want to represent that condition. A scenario where you would use this testing whether a bit is on or off is when you enable something inside the microcontroller, let's say the analog to digital converter. You will have to enable certain aspects of that converter. And once you set something to be enabled, the microcontroller needs some time to be able to make sure that that particular feature is enabled. And the way to do this is to wait using a while statement, a while, a condition, and for a particular flag in that feature to be set. So you try to enable something, and then the microcontroller will set a particular bit to true or false, 1 or 0, when that particular feature is enabled. And then you can move on to the next part of the program. To see an example of the way I'm using the while to wait for something to be set or reset, here I am starting the ADC calibration, which is setting the AD cal in the CR register of the ADC1 control register. And down here, I'm using the while. There is a while this same bit, the AD cal bit, is not equal to 0. If this condition is true, then keep waiting, because it's waiting for this to be a 0. Because we set it to 1, and it's calibrating, and it's waiting to make sure the calibration is completed. And when it becomes a 0 again, it's finished. I could have also said while it's equal to 1. This would have been the same thing. So while I set it to 1, while it's still set at 1, it will keep going through this while loop. And if it becomes 0, then it goes on to the next one. This example is on page 233 of the book. It's not really important at this particular time to understand why or how this is working, because understanding a combination like and not is not the most intuitive thing. So just remember these lines of code to turn a bit on, setting a bit to 1, turning a bit off, setting a bit to 0, or toggling a bit. If a bit is 1, it can become a 0. If a bit is 0, it'll become a 1. With these 4 variations of code, you will be able to affect any register in the ARM microcontroller, any bit in any register in the microcontroller, and you'll also be able to test whether a particular bit is on or off, 1 or 0, or true or false. Let's put these operations into practice. So I'm going to take an LED and connect it to pin number 37, which is right here. The LED needs a resistor to reduce its voltage
because if we don't put a resistor on here, it's going to burn the LED out. So I'm going to use a 330 ohm resistor. I probably don't need something this large because this is already at 3.3 volts, but a 330 ohm resistor will just make the LED a little bit more dim than its brightest. If you want to figure out the actual resistor you need to use, you can figure that out using this formula. The resistance is equal to the supply voltage minus the LED voltage, which you'll need to know, divided by the current.
I lost sound at this point, but if you use 0.01 amps for your current, which is a conservative number, the supply voltage is 3.3, and I use 2 volts for the LED voltage. You'll have to look at the data sheet for your LED if you are using a different LED. And my resistance value came out to be 130 ohms. Let's draw the schematic. You're going to put the resistor in line with the LED. So let's draw the resistor. So this is what the resistor would look like. And now let's draw the LED symbol. And the LED will be connected to the ground power rail. Let's add the resistor and the LED to the breadboard. Make sure to have the LED oriented so the flat side of the LED is connected to the ground rail.
Okay, I've fixed the circuit so it's a little bit less ugly, and it probably serves better and doesn't act as antennas. Breadboards themselves actually cause a lot of interference in general, and you don't want to create more interference by putting components in with bare wires all over the place.
Okay, let's start the IDE. All right, I have a couple programs here open. Let me close those, and I'm going to start a new STM32 project. I'm using the F030R8. I'm going to click Next, and the project name will be LED on-off toggle, and press Finish. We're going to be using this pin here. Exit that, and this is the project that we're using. I'm going to open up core, source, and the main.c is the one we're going to be using. These comments always cloud me, so I'm going to go ahead and take them out. Or I got a comment that I should keep these in, and I probably will for future videos, but I'm taking this out so I'm able to show the program in a very simple state. So this is the entire program. It has an hash include, a prototype for this function here, which is the system clock config. It's configuring the system clock to run at its default 8 megahertz. You can see that the PLL is none. If it was going to be a different speed, it would have a different value here. Like PLL is a multiplier of the system clock. All right, so we don't want to go into the while loop yet. We're just going to be setting up some of the registers to enable the port C pin 6, which is pin number 37, as output. You can use the reference manual to find the registers that you need to change to make something work. So we want the port C pin 6 to be output, but how do we do that? Well, you could read the entire manual, and it is long. It is, see, 767 pages. I've pretty much gone through the entire manual, so you don't have to. So let's see, what do we need to do first? We need to go to the Advanced High Performance Bus Clock Enable Register. So let's look for that. And to do that, I'm just going to use Control F to find, and I'm going to type in Advanced High Performance Bus ENR. And I'm going to go to the, let's see, to the first one. I'm going to just scroll up here, and I should go to the table of contents. And it's not showing up for me, so I'll just press the up to go to the first one. Okay, here we go. And I'm just going to click on this. It's on page 112. And this register allows you to enable the I/O for any of the ports. So we're concerned with port C here. So we need to enable bit number 19. So let's go ahead and do that using one of our 4 bitwise operations. So we need the AHBENR register, and it's under the RCC, Reset, Clock, and Control. So the way we write that is RCC for the Reset, Clock, and Control. And we're going to use a hyphen greater than symbol to point to It's like you can think of this as like a little arrow pointing to the particular register that we need. So the one we're going to be looking for is the AHBENR, which is the first option. If you don't see this list, you can click on the Control spacebar to get this list. So I'm going to go ahead and click on that, or double click it, space, and I'm going to use the OR bitwise operation to set that bit, and then the equals. And we have to repeat the register name again, but if we press Control space, we might be able to find it in here, but that would take too long to find it. So let's go ahead and just start typing RCC, and you'll start to see different things pop up. Underscore AHBENR. I'm going to do the Control space again. So now you can see some more options appear. So what we were looking for is the GPIO enable for the C port, and this is the one right here. So we're going to press enter and then semicolon to end our code line. So now we've set the GPIO to be enabled. We can go ahead and start setting up the specific pin as an output. And to do that, we have to modify 4 registers. First register is the mode register. The second register is the output type register. Third one is the output speed register. And the fourth one is the pull up, pull down register. By the way, I am using my book to do all of this because I wouldn't remember all of this information. So the mode register is abbreviated by MODER. The output type is O type. The output speed is O speed. And the pull up, pull down is, you guessed it, PUPD register. All right, so let's start with the mode register. And looking at the reference manual again, I'm going to use Control F, search for mode, MODER. And this is general purpose IOs for GPIOs. And I'm going to go to the register description here. So this is the mode register. You can also see the other registers here as well, the type register, speed register, and the pull up and pull down register. When you look at a register like this, it's generally going to show you for the port. And if you look at the mode R0 and 1 and 2 and 3, these are the actual pin numbers for that particular port. So the one we're looking for is port C pin 6. So this is the one we want to adjust. Let's go to newbiehack.com and let's take a look at the board and look at number 37, which is over here on this side. You can see it says port C pin 6. So that's the port and pin we're looking for in the reference manual. So on pin 6, there are various states that you can specify. You can put it in input mode. That's where you'd maybe put a push button or read a 0 or a 1 state coming in from a port, from a pin. You have the general purpose output mode, which is what we're going to be using because we want to output a high or a low signal or a 1 or a 0. We have an alternate function mode, and that's where you can use, let's see, the one we're using is here. The alternate function would be the timer. These are all the alternate functions here on this column. And then you have analog mode. So let's go ahead and set the general purpose output mode. We need to set the first digit here as 1 and then the second digit as 0. You can see it says 0 and 1. So 0 goes here and 1 goes here. So in this mode, 1 and 0, 1 would go here and a 0 would go here. So let's go ahead and do that. We are specifically talking about the GPIO-C, so you can just type in GPIO-C right here, pointing to the mode register. And pressing that, we go down to the mode register. Since we're going to set this to a 1, we're going to be using the OR bitwise operation again. Equals and GPIO. We don't use the C here because this is a general definition of just a particular number for what bit we're going to be changing. So underscore and then mode. Actually, we can press the Control Shift or Control Space and take a look at all of them. So we can find the underscore mode. Let's just go ahead and type in mode. And we have motor 01 for 0. So let's look for 6. So this is the both of the digits. This is the 0 digit and this is the 1 digit. We need to put a 1 in the 0 space. So that's all we have to do is to set this to a 1. We just use the OR bitwise operation to set this to 1. And then we need to set the second digit, the 1 digit, to a 0. Now we have to set this digit to a 0. And you can see it's already as 0. It's set as 0 as default, but we don't want to trust that because we could be in the middle of a larger program that we may have set it to something else. So we want to always make sure to set it to a 0, even though we really don't need to. So let's go ahead and do that. We're going to do the same thing, GPIO-C mode register, and we're going to use the AND NOT bitwise operation. I usually keep the NOT next to the bit number because we can do multiple bit changes in one line, which we'll do later on in the series. But right now we'll keep it simple. GPIO. I'll use the control space to get my list, and we're going to go to number 6 again, and this is the second digit. So by using the AND and NOT, we're making this bit number a 0. Let's go take a look at the type. And the type register means that it's either in a push-pull state, which is the reset state, or it's an open drain. And this falls into a category of understanding transistors. I'm not going to bore you with that right now, but to keep it simple, we're just going to be using the reset state, which it's already defaulted as that, but we don't want to trust that. So we're going to go ahead and set this to 0. And this is the O-type output type register. And we're going to reset this one or set it to 0 using the AND NOT bitwise operation. And we're going to use the control space again to go to the one we need. And since this is actually showing you only a single bit, let me show you why that's happening. So you can see that even though this is a 32-bit register, you're only using from 0 to 6 to 15, which is 16 bits. All of these other ones are reserved. So we're only needing to either put a 0 or a 1 for that particular pin. So that's why it only needs 16 bits. So we only need to affect a single bit. So it only gives you that option when you look at the list. So you have 0 through 15. So we're just going to go to 6. And that's all we have to do. Now for the speed, we're going to do the same thing. GPIO-C. So let's take a look at what we need to do for the speed. That's the next one here. And we have options of low speed, medium speed, and high speed. And this is really mainly to do with how much current you're going to consume in the microcontroller. So I would recommend, if you're just doing something like blinking an LED, just keep it at low speed. In this instance, because both of these have a 1 for the medium and high speed, and there's only 3 options, only putting a 0 at the 0 space, the first digit of that particular pin, is all we need to do. So let's go ahead and do that. So we're going to be using the AND NOT operation again. So we're going to look at the 0 place of pin number 6. So we're just making sure that this is a 0. Even though the reset value or the default value is already 0, we just want to make sure to do that. Now the pull up and pull down register, we are using no pull up and pull down on this pin. Pull up and pull down mean that there's an internal resistor you can use if you want it. You can either pull the pin up to positive voltage, or you can pull down the pin to ground. We're not going to worry about that. This is more necessary for using the input. This feature eliminates the need to have an external pull up or pull down resistor if you need it. So we'll go ahead and just make sure that there's a 0, 0 here. So both of these positions will be a 0. 0 position and the 1 position. When I press the control space, because there was nothing else in the list, it automatically populated by itself. So this is going to be another AND NOT. We're going to be using 2 of these. I'm using the control space again. Let's go down to pin number 6. I'm just going to do a copy and paste of this line. And we're just going to change this to a 1. So now we've made sure that there's the bits 0 and 1 on pin number 6 are 0 because we're using the AND NOT operation. Now we've set the port C pin 6 to be output, and now we can actually send a high or low signal to the LED. I'm going to do this in the while loop. Actually, no, I'm going to do this outside of the while loop for now. I'm just going to do one version. I'm just going to turn it on. We're going to use a register called the bit set
reset register. And it should be in the same chapter as these registers. So let's take a look at that. I'm going to keep going down. This is the port bit set and reset register. And you can see that there's a bit set and there's a bit reset. When you put a 1 in the bit set register, it will output a 1 or a high signal to that pin. If you put a 1 in the bit reset register, it outputs a low signal, or it'll turn off the LED. So it's almost as if you're setting this and resetting this, or putting a 0 in here instead. So what this is going to do is just make sure that this bit set is not set, if that makes any sense. So let's go ahead and do that. So let's go ahead and do that using one of our 3 bitwise operations. So GPIO C, the same thing. We're going to look at the bit set and reset register. So we want to put a 1 in the pin number 6 for the bit set. So we're going to use the OR operation equals, and then we're going to use the pin number is going to be GPIO underscore bit set and reset register. Let's take a look, and you can see the BR is bit reset and the BS is the bit set. So let's look for the bit set for number 6, semicolon to end the line. And now we should have an LED that lights up once we run this program. So let's go ahead and do that. Run the program. If you're doing this for the first time, you may get the run configuration. First, let me plug in the programmer that is also plugged into the microcontroller. Okay, this is the programmer. It's plugged into the microcontroller. And all I have to do is plug the programmer into the computer. Okay, I heard the signal on the computer that it's plugged in. Let's go ahead and program it. Clicking the play button, it's building the project. Proceed with launch. Errors exist in the active configuration of project LED on-off toggle. Let's see. Let's go ahead and proceed. Let's see what happens. Oh, I see. What is this? So if we hover over the X, this is undeclared. In my haste to erase all of the comments, I accidentally erased some vital lines of code. Okay, so I need these. So let's go ahead and do it again. Play, and it should redo everything. Looks like there's no errors. That's good. Now it's waiting for the debugger connection, and there we go. After programming, you can see that the LED lights up. Let's turn off the LED. So if you want to turn the LED off, we're going to use the bit reset register, BR. And let's go ahead and use the play button to build the project and program the microcontroller. And you can see that the LED is off. Let's go ahead and blink the LED. We'll use the toggle. But since the toggle is toggling a single bit, that means that we'll need to find a register that I can update a single bit to turn on and off the LED. Let's take a look at what we have here. If we look at the ODR register under the GPIO, we can set or reset from a single bit. So let's use the ODR6. And if we write a 1 here, the LED will turn on. And if we write a 0 here, the LED will turn off. ODR. And I'm going to use the toggle. Let's find ODR number 6. And I want this inside of my while loop. So every time it goes through the while loop, it will toggle it on and then toggle it off, toggle on, toggle off. But it's going to be going way too fast because there's nothing to slow it down. We won't even be able to see the LED turning on and off. So let's add a delay, a 1-second delay. And we're going to use the HAL delay like we used before. There we go. And the delay is in milliseconds. So we can put 1000 here. And for every second, it'll turn off and on. Let's try that. Press the play button. And now we can see that the LED is turning on and off every second. So we'll take a look at using the GPIO, the general purpose input-output, and we'll take a look at the input side of things. Using a push button connected to one of the GPIO pins, and then we'll output to an LED. We'll take a push button switch like this. We'll have the microcontroller read the push button switch on one of the GPIO pins, and then we'll output on another pin, completely different port and completely different pin on an LED. When we press the button, the LED will turn on. For the LED output, I'm going to use the same port and pin that we used in the instructional video for LED output, which is port C, pin 6. And that was located
it on pin number 37, which is right around here. As before, we'll use a resistor and an LED, and it will be connected back to ground. When we output a 1 or a high to this pin, we will light up the LED because it's connected to ground. For the input, I'm going to connect the push button switch to pin number 27, which is port B, pin 1. The push button schematic is going to look like this. It's going to come from 27, which is the port B, pin 1, and it's going to have a resistor. And the resistor here is just to protect the pin. It's going to be a 330 ohm resistor. And then this will be the switch. And from the pin, we're going to have another resistor, and that's going to be connected to ground. And the ground resistor will be at a high resistance, so we're not going to be using a lot of current when the switch is actually depressed. This will be a 220k ohm resistor. The resistor coming from the pin will be a 330 ohm resistor. And this resistor really is only to be used when this is going to be connected to VCC. So in the pressed state, you're going to have these two connected. So you're going to have a connection between ground and VCC, which will be at 220k ohms, which is high resistance. So very little current is being used when we're pressing the button. But it's also connecting to the pin at a 330 ohm resistance. So we're protecting the pin, but we're still getting the high signal from VCC. When the push button is not being depressed, you'll notice that the pin is going to be directly connected to ground. And what we're doing here is we're pulling this pin down as a natural state. We're doing this instead of actually pulling the pin down internally. We could do that in software where we use the PUPD, pull up, pull down register, and pull this down, but that's only pulling it down to about 40k as specified in the datasheet. And we're pulling it down at 220k, which is a lot more resistance and will draw less current when the push button is pressed. If we didn't have a pull down resistor externally and we didn't have the pull up, pull down resolved internally, when the push button is not pressed, this would be in a floating state. And you'll notice quite unpredictable behavior. Even waving your hand over the circuit could cause unpredictable outcomes. So when you're putting a circuit together that has an input, that is the mode for the particular pin is set as input, you want to make sure that it's either pulled down or pulled up and not in a floating state, because that input is going to be acting like an antenna and can pick up noise. And if that noise goes above or below the thresholds for TTL circuits, transistor logic circuits, it will produce an outcome, make the LED turn on or do some other unpredictable effect if you have a much more complex circuit. Now that we understand how the circuit works, we can go ahead and put together the circuit on our breadboard. The first thing you'll want to do, if you haven't done so already, is set up your board so you'll have all of your power connected and all the power rails connect together. And this power connected, the power connected from the bottom of the board, and you have the boot 0 connected to ground with the 510 ohm resistor. Let's get started by connecting the LED to port C, pin 6. And that's on the pin number 37. Insert the 330 ohm resistor across the two tie strips, and then the LED with the flat side towards the ground. So from pin 37, we have a 330 ohm resistor to an LED that is connected to ground. Now we can connect the switch to pin number 27, which is port B, pin 1. We'll start with the 330 ohm resistor, connecting the two tie strips. Then we'll put the switch, allowing the lead of the switch in the back here to share one of the spots in the tie strip with the resistor. So it can give me enough room back here to put the other resistor. And we'll put the 220 ohm resistor on that same tie strip to ground. Now we only have to put in the connection from VCC to the other side of the switch. So now when the switch is depressed, this lead will be connected to this lead. And VCC will be connected to ground through a 220k resistor. And it'll also be connected back to pin number 27 with the 330 ohm resistor. We're going to be looking at the GPIO input registers, or the registers we need to use to make the input happen. The registers that we use for the input is very similar to the registers we're going to use for the output. In fact, some of them are the same. We're going to look at the mode register, the O-type register, which is the output type register. We probably won't be using that one. The speed register, the pull-up, pull-down register, and one new one is the IDR register. The switch is going to be connected to the input pin. We need to figure out how to get the information from the input pin. We're going to need to know whether there's a 1 or 0 on that pin. Since we need the microcontroller to act on when the pin is 1, we need to figure out how to do that. And the couple ways to do that is by polling it, meaning we're going to test that pin every time we go through the loop. So every time we go through the loop, we're going to test whether there's a 1 on that pin. The other way is using an interrupt. In the interrupt, the microcontroller will tell us automatically, and it will go into another part of the program called subroutine or a method. In this video, we're going to be using the polling method. So let's get started. Okay, let's create our pseudocode. We need to include the library. Since we have skeleton code, it really doesn't know how to control the chip, the microcontroller. So we need to include that library in there. In the main section, we need to set up the control registers for the LED output. And we need to set up control registers for the input. And in here, when turn on LED, when button is pressed. Okay, so that's a very simplistic pseudocode. We're going to set up the registers. This is where the program enters. This is the entry point of the program. It's going to do some setting up of the output and input. In the loop, we're going to actually test if the button is pressed, and if it is, then we'll turn on the LED. The button is pressed, turn on the LED. If the button is not pressed, turn off the LED. All right, so in the output, we need to set up the mode register, type register, the speed register, and the pull up, pull down register. And then for the input, we need to set up the mode register for input. Let's go ahead and just put for output up here, and the pull up, pull down. Okay, and the turning on the LED, we've already done that, so we already know that's the BSRR register. And then turning off the LED, we can still use the BSRR, but we can also use the BRR register as well. So when the button is pressed, we're going to use the IDR register. This is the input data register. When we're polling this register, it'll have a 1 if the button is pressed and a 0 if it's not, in that specific bit that we're using. Before we forget, we need to set up the RCC, or the reset and clock control. And within this reset and clock control, the advanced high performance bus. And all we're doing is we're enabling the GPIOs that we need for port C, pin 6, and port B, pin 1. Let's go ahead and take care of the port C, pin 6. We've already done that before, so we'll just go ahead and enter that in. We need to include the library because it doesn't know what we're talking about yet. So let's go ahead and do that. Pound include, and it is the STM32 F0XX.H. Reset and clock control, and we'll use the member AHBENR, which is the advanced high performance bus enable register. And we're going to enable the GPIO C. Okay, so we're going to do that same thing to the B, port B. We took care of that. The really cool thing about putting in the pseudocode is because they serve as great commenting and annotations within the program. So you know what it does after you've actually put in the code, and it also helps you put in the code. So let's go ahead and set up the control registers. So we'll do the mode register first. So this is going to be under GPIOC. Under that, we'll have the mode register. So we need the general purpose output mode, which is a 0 and a 1, and we're doing it to the 6th pin. So that'll be a 0 and a 1. So we're going to put in the 1 first. Actually, I did that backwards, didn't I? It'll be, yeah, that's the 1 here, and then that's the 0 spot. So the first spot would be a 0, and the second spot will be a 1. So in the 0 spot, which is this one, we need a 1. In the 1 spot, which is this one, we need a 0. So let's do the 1 first, which is in the 0 spot. All right. And then we need a 0 in the 1 spot. So we're going to use an AND and a NOT, as we did in the previous instruction video. So we're ensuring that there's a 0 in this spot. Okay, now the output type. Let's see how that works. And the output type register needs to have it's going to be push-pull in the 6th place. So it's going to be a 0. So we're going to have to use the AND and NOT again. Output type 6. Okay, now for the speed, let's see what we need for that one. We're going to have the high speed, so it's a 1 and 1. So that's just going to be 2 ORs, 0, and we're going to OR 1. So speed is taken care of. Now the push-pull, or pull up, pull down register, and we're going to have no pull up, pull down. So we're going to do an AND NOT with a 1, 1. So AND equals NOT GPIO PUPD R. We're going to go to the number 6. And as we learned last time, this is a 1 in the 0 place, this is a 1 in the 1 place, and this is a 1 in the 0 and 1 place. So we'll use that. And by doing that, we're AND NOTing, making sure there's a 0, 0 there because we're using the NOT. All right, so let's take care of the input side. So obviously we want the mode to be input. So we want the GPIO B. We're using port B, and then we're going to go to the mode R register, and let's see what that is in the data sheet. So we want input. The input mode is 0, 0. So we can use the mode R1, and we can just use the 1 and 1 using the AND NOT, just like we did with the pull up, pull down for the output. So we'll use the AND equals NOT. That should be it. Okay, so now the pull up, pull down is not going to have, it's not going to have any pull up, pull down because we're resolving pulling it down externally. So let's go ahead and do that. Let's see how we do that again. Oh yeah, we're doing it the same way we did this one. So AND equals NOT. So just to review, we are setting up our mode for output for the LED. We're setting up our output type to be push-pull. We're setting up our speed register for the highest speed, and we're setting up our pull-up, pull-down as no pull-up, pull-down for the output. In the input, we're setting the mode for input, and we're setting no to pull-up, pull-down because we're resolving that externally with that 220K resistor going down to ground. Now in the infinite loop, we're going to be using the polling method. So we're going to say if button is pressed, we need it to do something. And we're going to be turning on the LED. And here we'll use the else. We're turning it off. Now, what do we need to put in the parentheses here? What is the condition? The condition is we're going to be doing some AND bitwise arithmetic. So let's go over how we do this. The IDR register has 16 bits. Each one represents a single pin. If there is a high digital level on one of the pins, then there will be a 1 in one of these bit positions. We have it on 1, port B, pin 1. If we press the button and we put a high signal on that pin, there will be a 1 here. If we have no other switches on these other bits, then all of them will be 0. We need to test whether this is going to be 1 or 0. So let's see how we can do that. We're going to use the AND bitwise operation here. We're going to start with the actual register, which is the GPIO BIDR register. And that register is going to have 16 bits in it. So let's go ahead and put in the zeros. Okay, and then we're going to use a mask, which is the GPIO IDR1 register. And that register, or that number, it's not really a register, this is just a number, it's a mask. Let me divide these into 4s. And because we have a 1 here, it's going to have a 1 in the 1 bit place. This is 0, this is 1. Let me just put the 0 here. 1, 2, 3, and then so on. So in the non-push button depressed state, this will have a 0 in it. But when we depress the button, it will actually have a 1 here. If we use an AND, this is the AND operation, AND bitwise operation. So we're going to do some AND arithmetic here. So 0 and 0 is 0, 1 and 0 is 0, and then 0 and 0 is 0, and so on. So this would be a false statement because 0 generally means false and 1 means true when it comes to if statements. To make this come true, obviously we have to press the button because there'll be a 1 here. So when there's a 1 here, 1 and 1 will equal 1. So that will be a true statement. So by using this mask for this position, which is indicated by this, we can test whether that particular pin and the push button is pressed or not. So let's go see how we do that in code. So we start out with GPIO B IDR. So this is the actual register that will be listening for the pins to be turning into a 1 or a 0, and it's under GPIO B. And the mask, this is an AND arithmetic. The mask is going to be GPIO IDR 1. So this is the mask. This one has a 1 in that location. And you know that 2 in binary is a 0 and a 1. So the first 2 numbers in this is a 4-digit binary number in hex. So this will have a 0 and a 1. This is actually a 32-bit number here, but it only allows us to use half of it. Because in the datasheet, you notice that all of this is not being used at all. It's only the 0 through 15, which is 16 bits, representing each pin on that port. So now we need to turn on the LED. So we'll use the GPIO-C and the BSRR register. To turn it on, we're going to use the bit set. So we're going to use the OR bitwise operation, GPIO-C. So the bit set register is, so we're turning on the LED. Let me put this comment above. Now we need to turn off the LED if this is a false statement. So GPIO-C. Let's go ahead and use the BSRR. We're going to put a 1 in that place. So the bit reset. Last time we used the BRR, which is the bit reset register, but we can use the bit set reset register, and you can see it uses all 32 bits, and we use the bit reset for number 6. So we're putting a 0 in that pin if this turns out to be false or we're not pressing the button. Of course, in this simple implementation of code for pressing the button, we're not taking advantage of any debouncing or anything like that because it's just going to turn on when we're pressing it and holding it down. It'll stay on, and it should turn off when we release it. So it's a very simple implementation of using the button. We'll take a look at more complex situations where we're debouncing and when we're using interrupts to turn it on and off. So let's see if this works. Let's see if it compiles. Looks like it compiled successfully, and that was the first time, which is really good. That's where having these come up automatically really helps when you have the library on. It doesn't mean the code will work, but it means that we don't have any syntactical errors. Let's see if this code works. Okay, the microcontroller was programmed. When we press the push button on port B pin 1, you'll see that the LED lights up. We're going to make an LED toggle on and off every time we fully depress a push button and we release a push button. I'm going to add a little bit of complexity to our simple input for push buttons. But because the push button is a mechanical component, we're going to have some problems because mechanically the signal is going to bounce up and down. So we need to take that garbage out, only consider the pure high or low values on that pin. Push button switches are mechanical components. Within this push button switch, you have leads that have contacts at the leads. Then you have a plate. This is a very simplistic diagram. And when you push down on the push button, this conductive plate creates a contact with the two plates that connect to the leads, creating a complete circuit. This action is going to cause problems electrically because it's mechanical, and mechanical things happen a lot slower than electrical current can. You can have a scenario where a high signal or 1, when you press the button to make a contact ground, it should go low or 0, or vice versa. It could be low, and then when you make contact, it can go to a high signal. That depends on how you have the switch connected. If it's connected to the low when you press it, then it'll go low. If you have it connected to the high, when you press it, it'll go high. What is actually happening, however, when you're pressing a push button is it's starting low, and then when you press it, it could be doing some jumps before it gets to the high digital level. In software, you're going to be able to see all of this. You're going to see it go from 0 to 1 to 0 to 1 to 0 to 1. And if it goes below the thresholds, then you may see it go back to 0 or not. And then it should, if it's depressed for a period of time, you should see a good signal of high. We would like to eliminate this portion. So when the LED is turning on or is toggling, the LED is going from off to on. So let's say it starts off. We don't want it to turn on until it passes this threshold here. And I'm going to use a counter to count cycles when this is actually constantly on a high or low signal. I'll count it on a low signal and I'll count it on a high signal. So we'll know if it's not being pressed and it's being pressed. And all this stuff will be eliminated in software. If you look at code online, you'll notice that a lot of people will just implement a delay from when it thinks it's pressed, like from here, they'll introduce a delay that they know that if it's still pressed over here, then they know it is an actual pressed. But I don't like that technique because what it does two things. It only tests 2 points to see if it is not bouncing. And it ties up your microcontroller for a specified amount of time, allowing you not to do any other instructions in between that. Alternatively, I would like to have the program on every cycle test either if this is a 1 or a 0. And if it's a 1, every cycle it'll test it again to see if it's another 1. If it's a 0, then it eliminates it. It's not pressed. But when it keeps doing that and it gets to this point, it has to keep doing the cycles until I get maybe 500 or so of these. So I'm able to do other programming within these cycles. I can do all kinds of other code inside of these cycles. With a delay, you'd have to wait from this point to some specified point without doing any instructions or code within the microcontroller. It wouldn't be able to run or execute the code during that time. This is very similar to a state machine where the state machine is cycling through operations and it keeps cycling through and it collects data as it goes and responds to that data. We'll get into state machines in more detail in future tutorials. So specifically, how do we do this? We're measuring a 0 on the pin, and then we'll have some kind of bouncing going on, and then we'll end up on a high level. During this time, we're going to have a few variables we're going to be working with. One variable is going to be, obviously, it's going to be button pressed. If it's going to be equal to a 0 or a 1, telling me that whether the button is actually pressed or not. And I want to know whether it is actually pressed or not. When it has a good count of high digital level samples, it will be button pressed 1. If it has a good number of samples of a low level, it'll be button pressed 0. So we have to introduce another variable, and we'll call that one button pressed confidence and button released confidence level. And what we'll be doing is we'll be counting up the button pressed confidence level when it matches a high level here, and it'll keep making samples until the number of samples is equal to the threshold that we set for the confidence level. And the same thing with the released. When we're testing it, however, we want to make sure that when we're counting the button pressed confidence level, that's going to be just a counter. We want to count it while the button pressed is 0 because we don't know if it's 1 yet. So while the button pressed is 0, we'll start counting. It could be counting here, but then maybe it doesn't, it shows a 0, so it has to eliminate that confidence level, and the confidence level goes back down to 0. So while the button pressed is equal to 0, and it matches a good number of samples for the button pressed or a high level, then we can turn the button pressed variable to 1. And the same goes for the button released confidence level. When it's pressed over here somewhere, and then it starts to do some bouncing, and it finally gets to 0, we want to eliminate all of this bouncing as well. We don't want any of this. So we're going to do the same thing. If it's button pressed as 1, then when it gets through enough samples for when the button is released, then we can say that the button pressed is equal to 0, meaning the button is released. When the button pressed is equal to 1, when we know that the confidence level is high enough beyond our threshold, we will set the button press to 1, and then at that particular point, we will toggle the LED. So we'll turn it either on or off. If it was on, then we'll turn it off. If it was off, then we'll turn it back on. So every time you're pressing the button and releasing it, it'll turn on, press it, release it, it'll turn off, press it, release it, it'll turn on, and so on. So we'll have to introduce code to toggle the LED as well. So let's start with the program that we had from the previous video. This is the code where you test whether the pin has a high level digital signal or 1 on it. And we're turning on the LED if it's 1, and we're turning off the LED when it's not 1. So this is just a simple, if you press the button, it turns the LED on. If you release the button, it turns the LED off. In this case, we want to press and release, it turns on. And we want to press and release, and it turns off. So I'm going to eliminate this code right now because we don't really need it yet. We'll be using it in our toggling of the LED. So let's write some pseudocode within this portion here. So when we know that that pin is receiving a 1 on it, we need to measure the confidence of that, or increase the confidence. Once the threshold for the confidence level has been reached, we can toggle the LEDs. When there is a 0 coming in on that pin, we want to increase the button released confidence level. In both of these, we're going to have to include some kind of variable to show us the state of the button pressed once the confidence level has been reached. So we'll call that button pressed. In the released portion, once the button released level, confidence level, we want to update the button pressed variable to 0. We want these variables to lie outside of the while loop because we don't want to keep initializing it while we're in our infinite loop. So we need to do that over here. We only want to do this code when the button pressed variable is equal to 0 because we're trying to make this button pressed variable equal to 1. So it must be 0 when we're doing this portion of the programming. It doesn't make sense to run this part of the code when the button pressed variable is equal to 1 already. It's just a waste of cycles for the processor, and it's not necessary. And it could cause the toggling of the LEDs to happen when you don't want it to happen. So let's go ahead and put in that code. So if the button press variable is 0, then do this stuff. Else, we're going to make it so if the is 1, then we can do this code because it doesn't make sense to turn it into a 0, the button press variable to a 0, if it's already 0. So we want to make sure that it's 1 and not run this code unnecessarily. This is all the pseudocode we really need, and it should be self-explanatory. Let's go ahead and start making our real code. We'll start with the variables. And we're going to make them volatile so they're not optimized out when we're doing the building of this code. These variables will remain live and dynamic throughout the running of this code. So we use the volatile, and we'll start with the button pressed variable. So we'll make that a char, relatively small variable, small size variable. It's only 8 bits. A side note with this variable type char is just an integer of 8 bits, and you can have it either signed or unsigned. Signed, if you put signed before it, that means it could be a value from negative 128 to a positive value of 128. But char alone, it's unsigned, is 0 to 255. So we're going to initialize this to be 0, and this is actually really important because if we don't have it 0, then it won't actually get into this portion of the code for it to actually set this to a 1 in the first place. So you want to make sure that it's initialized to 0. So let's initialize our button pressed confidence level. And it's going to be also volatile. And this one will be an int because it could be a large number. and we'll initialize that to 0, and we'll do the released confidence level. So let's get the low-hanging fruit first. We'll use this variable because we're using it in these if statements. So we can go ahead and just populate that. So let's go ahead and do this. We can increase the button confidence level, and we're going to use the ++, which is the same thing as saying button press confidence level is equal to itself plus 1. So it's adding 1 to this every single time that the pin has a 1 on it. We'll also want to reinitialize the button released confidence, because if it's being pressed, then it's obviously not being released. So we can say that's 0. Once the button press confidence is past the confidence level, let's do that. So we're going to have an if statement there. If that is greater than, we don't actually know a real threshold value yet. If it's greater than, let's say 5,000 or 2,000 or 100 or 500, we could introduce another variable. So let's go ahead and do that. And we'll call that confidence threshold. And we'll make that 200 to begin with. Probably way too low, but try that. The faster processors and the faster, more instructions you can run, the greater this threshold needs to be. So you can also use some code to determine the actual speed of the processor and use some divisor or some coefficient to determine this actual number. But let's just go ahead and hard code it for now and see what happens. So that will be confidence. If it's greater than the confidence threshold, then it will do, we don't know what this is going to be yet. Let's go ahead and update the button pressed variable to 1. Now let's work on the bottom part where the button pressed is equal to 1, but the pin is being passed as 0. So we want to increase the button released, and then the button pressed should be 0. And this way, if there was some up and down or bouncing, and it actually got in here, and then it bounced down to 0, then this is where it's actually reinitializing that variable, so it doesn't mistakenly think it's being pressed. So let's do this. Once the button level has been achieved, the threshold released confidence level is greater than confidence threshold, then we are going to update the button pressed variable to 0. You'll notice this is constantly increasing, whether it is above the threshold or not, but I don't want that to happen. I want, once it's gone above the threshold, like it's reached its 201, I don't want it to be increasing anymore. That may cause some unpredictable behavior, because we may be exceeding the level of the int, since this is going to be done in every single cycle of the infinite loop. So let's go ahead and put in an else here. If it's not beyond the confidence threshold, then it does the increment of the confidence levels. And we'll do the same thing to this. Now the only thing we need to do is toggle the LEDs. This is our last set of code statements to put in. So let's go ahead and we're going to need to introduce another variable here, because we don't know the state of the LED. We need to store that in some variable. So let's go ahead and put that in. LED lit state, whether it's lit or not. We'll use a car again because it's a small number. It's only 8-bit. We'll call that LED state, and that will be off to begin with. So let's go over here and say if the LED state is equal to 0, then we should turn it on. Else, if the LED state is on, we should turn it off. So let's go ahead and turn the LED state on. It should be equals. Else, if the LED state is on, is 1, we should turn it off. Now we need the code to actually turn on and off the LED. So turn off LED, and over here, turn on LED. Oh, sorry, turn on LED and turn off LED. So when the state is 0, we're going to turn it on. And when the state is 1, we're going to turn it off. So the code to turn on the LED, it's on the C port. So we're going to access the member of the BSRR. We're going to set a 1 in the pin 6 place. The bit set, or the bit, actually no, this is the bit set register. Now we're going to turn off the LED. It's the same, no, it's not the same thing. Access the member of the BSRR again, or the BRR, and we're going to find the BR for bit reset for 6. Okay, the microcontroller was programmed. When we press the button and release, the LED turns on. When we press it again and release, the LED turns off. Let's do this in many successions to see if we get any bounce. So far, so good. So 200 seems to be okay. Let's try decreasing the number and see what happens. Okay, let's decrease our threshold to 20. See what that does. Hit the button a few times. Well, I see the bounce. we will connect an LCD to the ARM microcontroller. LCD communication is no more complex than lighting up LEDs and testing button presses. The only difference to controlling an LCD is the way we turn on and off a pin and the timings between each bit going towards the LCD. The LCD that I'll be using is of the standard flavor. The LCD is powered by 5 volts. It has 16 characters per line and contains 2 lines. The LCD uses the standard 8 data pins, an enable pin, a read-write pin, a register select pin, and the standard contrast input voltage pin. The LCD can be used in either 8-bit mode or can be separated into 2 banks as 4-bit mode, and you'll only need to use 4 wires in 4-bit mode. You might be wondering how we're going to be using a 5-volt LCD with a 3.3 volt microcontroller. The ST-Link that we use to program the microcontroller contains a 3.3 volt output and a 5 volt output, so we can use that ST-Link programmer to also supply the voltage for the LCD. In a typical scenario where a microcontroller is communicating to an LCD, you would normally have the microcontroller using a single port, say port C for instance. And port C would have pins from 0 to 7. Those pins would go directly to the data pins of the LCD. And we would simply send a byte to that port because the byte is made up of 8 bits and the port has 8 pins. So the byte would be delivered to the port and each bit would be sent to each pin, each of the 8 pins. An example would be to send the character A, for instance, to the LCD. And the character A has a number, an ASCII code equivalent to 65 in decimal, or 01000001. And the bits that make up the number 65 in binary would be put onto the pins and sent to the LCD. But in the case of this particular microcontroller, we don't have that convenience because we need to find 5 volt tolerant pins. And the 5 volt tolerant pins will not give us a convenient 0 through 7 of a particular port. So we're going to have to send the byte to disparate pins around the microcontroller. So what we need to do first is we need to find out which pins are available to us that are 5 volt tolerant. You might wonder why we actually need to find 5 volt tolerant pins when we're sending characters to the LCD. But while we are sending characters, we also have to determine if the LCD itself is busy. So the only way to do that is to read the pins and determine if we get the busy code or not. This is not actually absolutely necessary because we could just extend the time that we deliver the characters to the LCD, but it's good practice to do this anyway. On page number 27, you'll find the abbreviations for the pins to determine whether it's a 5 volt tolerant pin or not. So you can see here, the FT is a 5 volt tolerant pin. The FT lowercase f is a 5 volt tolerant pin, and it is fast mode plus capable, which means that it's capable of turning on and off, sending ones and zeros at 1 megabits per second, which is 1 million bits per second. I'll probably not use this one because I may need that in the future, so I don't want to use those pins. I'm just going to go ahead and get the standard 5 volt tolerant pins. The table of pins actually starts on page number 28 and runs through 32, actually 33, but we're not going to be using this page since it's really only reserved for the ground and digital power supply. Or during this exercise, you're going to really get familiar with the pins on this microcontroller. You'll see that there's a pin number here. There's a column for each form factor of chip. We're using the 64 pin. In this column, this is the actual function, the primary function of these pins, which is generally input-output. The column that's really important to us right now is the I/O structure, which tells you if it is 5 volt tolerant or not. The alternate functions are also very important to us right now because we don't want to be using pins that we'll be using in the future. So we'll be taking a look at that as I mark the drawing to designate which pins are the 5 volt tolerant pins. The alternate functions and additional functions aren't super important at the moment because they actually have quite a number of options that you can use, and a lot of the USARTs and the I2C and the SPI, they're quite varied and you can use multiple pins for the same function. If you take a function for, let's say, the USART 1,
CK, you can use another pin for the same thing, such as here. So don't be too worried about that, and in the prototyping stage, you can always change the pins that you're using. So I'm going to use this table and I'm going to mark the pins that are 5-volt tolerant on my drawing. The first two pins that are 5-volt tolerant are the PF0 and the PF1, and then PF4, 18, and then PF5. The next one is all the way over here at number 28. PB2, the one next to it, PB10, PB11, PB12, which is around the corner here, and then PB13, PB14, PB15, PC6, and PC7. PC8, PC9, PA8, all the way through PA12. PA13 is SWDIO. That's the ST-Link programming I/O pin. It is a 5-volt tolerant pin, but I don't want to use that one because we use that for programming. The PF6 is the next one. PF7. Actually, PF6 can also serve as ground, so I'm gonna eliminate that one. PA14 is a programming pin as well, so we're going to leave that one alone. And that's the SWCLK, that's the clock. PA15 is one of them. PC10, 11, and 12. PD2, PB3, PB4, PB5. PB6 and PB7, those are the FTF, the fast mode pins. So we're going to leave those alone for the moment. So are the PB8 and PB9. And that is it. So let's take a look at pins that we can use that are 5-volt tolerant. And we have a pretty good number of pins that we can use. Just for the heck of it, I'm going to color the ports just so I know what port I'm looking at. So we'll start with the port F. Okay, that's all the port Fs we have. So let's go to port A or port B. Let's do port B first. Okay, the next one, let's do port C, port A, and finally port D. It looks like there's only one port D. Okay, so we have color-coded our pins for the ports. It looks like we have the most in the port B and port A. I think port B is our best bet. It doesn't really matter if we use multiple ports. I was trying to find if there was any way we could get some consecutive, and we can, but I think it's probably a better learning experience if we go with separate ports and pins just to give ourselves a challenge and send a byte over multiple pins and ports. And I kind of want to put them pretty close together, so maybe I'll use from 40 to 33. So let's check what alternate functions that I can use with that I may want in the future. Okay, so 33 through 40. This is a timer. We have timers all over the place, so that's fine. 33 starts here. There's SPI. There's an event out. There's a UART3, 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 timers, SPIs. Looks like I'm pretty safe if I use these pins. So I'm going to go ahead and do that. So I'm going to attempt to use these pins here. So what I'm going to need to do is, let's say we're using the letter A, and I need to deliver the letter A, a character, to these pins on, they're going to be 2 different ports and 5 pins on one and 3 pins on the other. This should be PCs. This should be another color. Let's say we're going to take the letter A. The 1 would have to be sent to this bit 0 at PB12, a 1 sent to the 7th bit, and then a 0 sent to the 8th. And to verify this, I'm going to put an LED on each one of these pins. This may seem like a lot of work, but it really does allow us to verify that we're sending the correct information to these pins, and they will be delivered to the LCD correctly. We're going to be focusing on pins number 33, 34, 35, 36, 37, 38, 39, and 40. We're going to put a resistor between these 2 tie strips here. For example, number 33, we'll put a resistor, a 330 ohm resistor from this point to this point. Then we'll put an LED from this point to the ground rail. Since the LEDs have such a large LED portion of it and the tie strips are pretty close together, these LEDs will get in the way of each other, so I went ahead and bent the leads in a way that the main LED can be staggered. These are all in the same direction, where the anodes are all on one side and the cathodes are on the other side. So let's go ahead and plug the resistors and LEDs into the circuit. Okay, so all of the LEDs are wired up through resistors to the pins that we need to test. So let's try it out. First thing I'd like to do is make sure all of these LEDs are working. So I want to output a 1 to each of those pins, port B and port C. The first thing we need to do is set up each of those pins for output, and we're going to be using the mode type speed that has a pull up or pull down resistor. And then we're going to just output a high on each pin. What do we need to do first for setting up the microcontroller? We need to first set up the RCC, which is the reset lock and control register, for the advanced high performance bus. So let's go ahead and do that. We're going to set that for port B and port C. We're going to be setting up each pin, which is 8 pins for out. It would be very tedious for us to add the mode, the type, speed, and pull up, pull down for each pin individually. So there's a couple ways we can do it. We can put it into a function and we can pass in the pin numbers and then run the function each time, setting each of the pins. But I would like to do this in a different way. We can take a look at the registers. The mode register for port B, we can plug in where we want the 1s and the 0s and just put in that number. So let's do that for the mode register first and see what's involved in doing that. If we were just wanting to set one pin for the mode, we would start off with going to the register, the mode register, and we would do an ORing of the first bit because we want a 1 in the first bit, and then to put a 0 in the next bit, or the second position bit, we would do an AND and a NOT for the second position. What we've essentially done with those 2 lines of code is we've put a 1 here and we've put a 0 in this position. So we're looking at pin number 12. Since this is one 32-bit number, we can just go ahead and put the 1 and 0 here for the pin number 13, the 1 and 0 here for pin number 14, and the 1 and 0 here for pin number 15. And then just put zeros in the remaining slots. So now we have an actual number we can just plug right into that register. Let's put this number into the mode register as a single line. So we're going to remove the second one, and we're just going to put a number in this place. We can write binary notation just by using 0B and then the number. So we know that that's going to be 0, 1, 0, 1, 0, 1, 0, 1. And the remaining will be 0. So we need 2 more sets. So that should be the number. You can see that this number is really long. So let's take a look and see what this number would be in hex. I'm just going to use a simple online converter. We can see that it's 55. So let's take that number, plug it in here. I'm just going to put it into a comment so we can use it later if we want to. So let's go ahead and do the rest of the registers that we need, the type, speed, and pull up, pull down. So let's take a look at the type register. This is a single bit register, so we don't need this top portion at all. And we can see that the reset value is just 0, so we can manipulate this however we need. So we're going to be using the output push pull, the reset state. We're not going to have the open drain state. So 12, in fact, this is going to be 0 all the way. So we're just going to put a 0 in this register. And we can just use the decimal notation for this. It doesn't really matter. Let's take a look at the speed register. We can see that there's a reset value for A, so we're not really worried about that. And the reason why you have the port A reset value is because of the programming pins are on port A, and that's setting those programming pins for that function. You can see that it's also in the mode register, the same location. The programming pins I'm talking about is the SWCLK and the SWDIO. Okay, so we're looking at 12, 13, 14, and 15. Okay, so we need these pins. We're going to go ahead and just put high speed. It doesn't really need to be high speed, but I'm just going to do that as my own default. The speed register, we have all 1s in that location. I'm just going to take this number that I have here, and I'm going to convert it to hexadecimal just to see what it looks like. I'm just going to replace the 0s to 1s since we're looking at 1s in those spots, and it looks like it's FF, which makes sense. So we can go over here, GPIOB speed register, it's O speed. And to put it in hex, you have to put a 0 and an X before it. We can do this in binary as well. I'm going to do the same thing with this one. I think it's easier to read personally, so I can just go over here and put in the 1s. I could do this one here too, but it really isn't necessary because they're just all 0s. All right, so let's look at the pull up, pull down, and we're going to use no pull up. It's going to be 0. So since this is 0, we can just put a 0 in all the positions, which means that we can just do the same thing like we did on the type. Actually, we don't want to do that. We want to just use the equals, because the OR will actually not produce the correct bits in the places we want them. So we have just reduced the code considerably. We could have had this 4 times. Let's do this for the port C now. Just going to do a copy and paste and replace all these with C's. And obviously these numbers are not going to be the same. So let's take a look at what we need to do there. Let's take a look at the mode first. So what pins are we using on port C? So pins 6, 7, 8, and 9. So pin 6, 7, 8, and 9. That's going to be 0, 1s. And all these are going to be zeros. Now I'm going to set up something that makes it a little bit easier for me to see which positions I need to set. 9, 8, 7, and 6. And it's 0 and 1. So this would be the binary number. So let's go ahead and copy and paste it here. Take out the spaces. All right, now we can do it to this one. And the speed would be the 1 and the 1. I could have just copied this one and put it down here and just put this 1s and 0s, but this is a little bit, for me, it makes more sense to do, just so I don't have any errors. Okay. All right, so we've set both of our ports and all the pins that we need to set for output. Now we need to turn on all the LEDs. To turn the LEDs on, we're going to have to set those pins high. We're going to use the BSRR register, which is the bit set and reset register. To set the pins, we need to put a 1 in the bit set location. And the port we're working with right now is port B, 12, 13, 14, and 15. Let's do that first. So we have that here, 12, 13, 14, and 15. And to reset those, if we ever wanted to do that, we would put a 1 in these locations. So let's go ahead and see what we need to do to set them. Just put a 1 in these locations. Zeros would be in these locations. 16 more. So we're concerned with these positions here. To reset these pins, you'd want to put 1s here. Let's look at what we need to do with the port C. So port C, we're using 6, 7, 8, and 9. So we want to put the 1s here. So we have zeros all along here and zeros in the beginning. Okay, you can see the two lengths are the same. So we have the correct number in there, and just hopefully we have them in the right positions. Theoretically, we should be finished with the program. And you'll notice that all of the LEDs are lit up. At this point, we don't really need this anymore because we're just using this as testing. These are the bits set and reset register, and we're just turning on the bits just to see if they work. So we can delete that. Let's create some pseudocode so we can know what to do in our program. So let's send a character or a byte to port C and port B. To be able to send a byte to disparate pins and disparate ports, we'll need to send bit by bit from the byte, from the character. So we're using the character A, and that's 0, 1, 5 zeros and a 1. And that's the byte represented as a binary notation. So you can see that we need to send each of these bits to the respective pins that they're going to be going to. And port B will be the first, port B will be these sets of pins, or these sets of bits. And port C will be this set of bits, because that's the way we set it up in the circuit. This will be 12, 13, 14, 15 on port B, and this will be 6, 7, 8, and 9 on port C. We need to test bit number 0 on the byte and send it to port B, pin 12. And we need to do this for each pin. And I'm writing it in longhand right now because by writing it in longhand and showing each test of each bit, you'll get an understanding of what's going on. And then we'll take that and we'll put this in a function. So all we're doing is we're putting the letter A to that function, and it automatically sends it to those pins and ports. Well, first let's actually set up a character. So let's call it a car. Character is equal to A. And this A is actually equal to this binary number. So we're going to be testing for this number first. But how do we test a single bit in a byte? That actually seems quite difficult to do, but it's not. We're just going to use bitwise operations and a mask to determine what this particular bit is out of this entire byte or this entire character. What we're going to do is we're going to take a number for the letter A, 0, 1, 0, 0, 0, 0, 0, 1. And we need to find out what this one is. So we're going to use a mask, which is putting a 1 where we want to figure out what bit we want to test. So the mask looks like this. And we are ANDing. This is a bitwise operation of AND. And the AND truth table says that a 1 and a 1 is going to always be a 1. A 0 and a 0 is going to be a 0. And a 0 and a 1 will also be a 0. So now we know that we have the number 1. So this is a true. So how do we write this in code? We're going to use that and in an if statement. So if the character, which is the same thing as saying this, and the mask of 0, 1, 0, 0, 0, 0, 0, 1, that's the same thing as saying this. This is the character, and we use the and we have our mask for the character or for the bit that we want to test. So in that case, we know that we're going to get a true result. So what do we need to put there? We need to light up that LED because we know this is going to be a 1, only if it shows true. But we also, if we have A here, we know this particular one is going to be true. So we'll use the bit set and reset register for B, and we're going to or equals, because we're going to be setting it. We're going to be putting a 1 in that bit, and we're going to use the bit set part of the register. And this is going to be number 12. If this position is a 0, then we want to reset that bit in the register. And we're resetting it. You might think that we want to do the and not to take the bit out of this or make this a 0. But we don't really want to do that because we're going to be putting a 1 in the bit reset register, which will automatically reset the bit set register to 0. So we're using the bit reset and then 12. Now let's move on to the next bit. So this would be bit 0. So bit 1, using the same number, 0, 1, 0, 0, 0, 0, 0, 1. We're going to and our mask will look like this. You can see that the one we're going to test now, bit number 1, has the test bit in the second position. So we can do the arithmetic, the bitwise operation, and we know that 1 and 0 is equal to 0. 1 and 0 is equal to 0. So that is a correct determination of this second bit. It is a 0. 0, 0 is 0, and 1, 0 is a 0. So now this is equal to false. So in this case, this particular bit and pin will not be lit up. It will not make the LED shine. I'm just going to copy and paste this code because it's the same thing. You can see that we only need to change a few things on this code, and that allows us to understand that we can also create a function to do the same thing. So we're creating the mask. This is not the right mask. I should be putting a 0 here. So we're creating a mask where the 1 is in the second position. In this one, it was the first position. So we're going to do that for the rest of the B. So the next one will be the third position, or bit number 2, and this will be affecting pin number 14. And we have one more port B to test. So it'll be the fourth position, or bit number 3, and this will be pin number 15 for port B. And now for the C. We're doing the same thing, we're just going to be changing the B to a C, and the first one is pin number 6. This is the position number 5, bit number 4, and this will be affecting pin number 7 on port C. We have 2 left to go, okay, and then 1 left, 1 remaining, which is the seventh bit. I think I had one too many bits here. No, I must have. That's the first, second, third, fourth. There we go. 5th, 6th, 7th, and 8th position. And then you change this to 9 because that will be the last pin we're using. Let's confirm those pins. 12, 13, 14, 15, and 6, 7, 8, and 9. Okay, so there's a lot of code cleanup we can do here. You can see there's so much code here that it starts to get unwieldy very quickly. I just want to show this as longhand so you can see what is entailed in delivering a single byte character. So let's go ahead and test it and see if it works. Build errors. I shouldn't have used the quotes. So used to using quotes in C#. So use a single quote or the car data type. Let's try it again. Okay, no errors, no warnings. Now we can download the code to the microcontroller. I just noticed something that I did wrong, and this I'm showing in just regular binary notation, but it's not code-wise binary notation. So I have to put a 0B in the front of each of these. You can see how this longhand code, repeating everything by hand, can get really error prone and messy. Okay, now let's do that again. Okay, the microcontroller was programmed, and you can see that bit 0, the bit position 0, the first position, is a 1 like we would expect. And then the second, third, fourth, fifth, sixth, those are all zeros, which is correct. And then you have the second to the last one, or the 7th position, is a 1, and then the 8th position is a 0. So this shows the letter A correctly in binary format on the LEDs. First thing I'd like to do is create definitions for these bits. This will also help us understand how the circuit is connected with the microcontroller and the LCD. So which pins and ports go to which data pins, and the enable and read write and register select. So let's set up the defines up here. I want to create something very understandable in the way that we have the circuit wired, and that would be LCD D0 through D7 would be my names for the define. So let's call this one LCD D0 pin, which will be 12, and we can define the LCD D0 port, which will be GPIO-B. We'll do this for each connection, so we can just do a copy and paste. So the next pin is number 13, and it's also B. That's going to be D1. D2 on pin 14, port B. D3 on pin 15, and this is port B. And now for the port C, D4 and pin number 6, 7, 8, and 9. For D5, D6, and D7. And the pins that I'm referring to are these pins, 12, 13, 14, 15, 6, 7, 8, and 9, going to these LCD D0, D1, D2, D3, D4, D5, D6, and D7. So it really tells you how the circuit is put together. And if you need to make a change in the circuit, all you have to do is change the pin for the D0, which pin it's going to go to, and what port it's going to go to. And none of the program will have to change because it'll always be set here. And the program will use these defines within the function. So we're going to take this portion and put it into its own function and use those defines in that function. Instead of making a prototype, I'm just going to go ahead and make the function up here. At this point, I don't think it needs to have a return. So we're going to have void, and I'll call it send bit to port and pin. And I'll have some inputs to this function, and it's going to be, if we want to pass in the port, we can get an idea of what the data type is by just hovering over one of the ports. And you can see it's GPIO type def, and you'll see it's a pointer. I'm just going to do a copy and paste of this, and then the pointer I'm just going to call it port. This will be the actual variable name. Okay, so the next thing we're going to be bringing in is the actual pin number. This number is only going to be a pretty small number. I'm just going to use an int for this. And then we actually have to send the bit, whether it's true or false. So we'll just call this will be actually I don't think I can use bool in this language. Use an 8-bit integer unsigned, and it will be, so I'll call it bit state for now. I don't know of a better variable yet. So we'll just take this condition and we'll copy it into that. All right, so we're going to replace the port here. So instead of using the port that we had hard-coded, we're going to pass it in. And then this, I think we're going to use the bit reset register. So we're going to try, because you can see this number is at the 4th position, 0, 1 to actually the 3rd position. And this one is actually all the way over here. So we want to use the same number, pin number, in the same way. So what we can do is we can actually just take out this S, and we have a BRR, and you can see it's at the same position because this is the bit reset register, and this is the bit set and reset register. And the bit reset register is only a 16-bit. It only uses the first 16 bits. And the bit set reset uses all 32 bits, but the bits 16 through 32 are the reset. Okay, so now we have to change this to the reset register, and we're going to actually put the pin number here, and we're going to use the bitwise shift operation and remove this number. So by putting the pin number, let's say 12, it's going to put this pin number into the 32-bit number at the position. So if the pin number is, let's say 9, it is going to come over here and go 0. It's going to left shift it. So it'll actually put a 1 right here where we want it, which we did for the setting and resetting when we were lighting up the LEDs initially. And for the bit reset, we're going to do the same thing. We don't actually have to make any changes to this portion of it because we want to reset at the same pin number since we're using the bit reset register and not the bit set reset register. Now the only thing we have to change now is the condition, and this is going to be the bit state. So we have created a much more tidy code for this bit of code here. So let's go ahead and invoke that. I'm just going to take my prototype function and I'm going to copy and paste it here. And for this one, we're going to use port B, GPIO-B, and we're going to use pin number is going to be 12, and the bit state will be this. Let's see, why doesn't this work? Oh, I have the void here. Okay, so this does the same thing as all of this. And we have made it so, actually I don't want 12 to be there. I want to use the defines. So the define would be, this would be for the port and the pin. Okay. That's what I really want. The D0 pin will be 12. You can see that it says here. And the port will be the port for, it's really difficult to read in this way, but you'll see that the 0, 8, and then the 4 in this position. If you look at here, should show the same thing, the 8 and the 4. Yeah, so it's the correct port as defined here. Okay, so we can go ahead and erase this portion of it. And we're going to just do a copy and paste of all of these. We should have 8 of them. This should be D0, D1, D1, 2, 6, and then the last one, 7 and 7. This is going to have to change as well. So we'll have the masks going up in bits. So we're testing for this bit within the character. We're testing with this bit with the character, this bit with the character, and so on down the line. So we have just taken out a lot of code and made it much tidier and more readable. And we can also tidy up this. We can put this in its own function, and we'll do that as well. But I want to test this to make sure it works first. And as you can see, we have the same result. The 1, 5 zeros, and then the 1, and then the 0. Generally, when we're sending characters or commands to the LCD, we do that in one line. We also send an entire string of text in one line as well. But we'll start with just sending character by character as one-liners. So we'll create a function that sends the entire character to all the pins of the LCD. This should be very straightforward. So let's start with creating a function. This function is not going to return anything, so we're just going to use void. I don't think it's going to return anything at this point. We're just going to say send a character to the LCD data pins. And then all we're going to be putting in is the character. And over here we're using a car, so we'll use that as a data type. We'll call it character. Now, all we need to do is actually take all of these and just move them into that location. So we have the character and it's being pushed into these lines. And to invoke that, we're just going to copy this line. And instead of putting character here, we could just do this, but that would be a waste of an entire line of code. So we're just going to put in the actual character in that line and remove this line that creates a variable and then stores the A into that variable. So now you can start to see how easy it is to actually just take characters and then send them to the LCD. I want to start by creating a function. This is going to be a non-returned function, and I'm going to call it set port and pin for out. And then what we want to bring in is our port and our pin. Let's see how we want to do that. I'm going to steal some stuff I had here, which is going to be the same thing because we're using the same defines. Since we're really focusing on a single pin in this function, we only care about the port and the pin number. Since we're going to be setting each pin one by one. You can already see from the first video of this LCD series that I told you to do it this way. This is one alternative way to shorten the way we're doing it as the longhand way, where we're setting the mode individually, the type and speed and pull up, pull down register. We're doing that individually for each pin. We're going to go back to that, but still it's going to be a much easier and clean code because we're going to be doing something very similar to this. But we're also making it so it's reusable because it's using the defines, and we can change only this if we need to change our circuit. So instead of using, let's say 9, we need to use 10 on the GPIO for C, or we need to use another port. We can just make that change and the entire program should work flawlessly. So let's take a look at these one by one. We're going to look at the mode. So let's go ahead and just type in port, and we're going to go to the mode register. We can see down here we want a 0 and a 1 in the mode register. And this would be position 31 and position 30 because this starts with position 0. So how do we get to that position when we're talking about pin number, say, 15? Here you have all of the positions for a 32-bit number. The row on the bottom represents the positions associated with the pin number, since the mode register requires 2 bits per pin. So for instance, if we're working with pin number 15 and we have to put a 0 in this position and a 1 in this position, we need to figure out how to use the left shift operator to make this happen. In this case, we're going to have to do a left shift. The 1, actually it's an AND equaling a NOT, 1 left shift and the 31 position. And in this particular case, we need a 1 in that position. So this was going to be an OR equals a 1 left shift in the 30th position. So for the case of the 0 in the 31st position, remember there may be a 1 here because of some other task that we had to perform in another part of the program. So we want to make sure that there's a 0 in this position. And the way we do that is we use the AND not 1 left shift 31, and the 15 is what we're given. So what times 15 plus what would equal 31? That would be times 2 plus 1. So we're multiplying 15 times 2, which gives us 30, and we're adding 1 to give us 31. The 30th position, when we're given the number 15, is actually easier. It's just 15 times 2. 15 times 2 is equal to 30, so that one is pretty straightforward. Let's say we were given pin number 10. 10 times 2 is equal to 20. That would be putting a 1 in this position, and then 10 times 2 plus 1 would be the other position, which is the same as this example. Okay, so we're going to apply two operators here, an AND and a NOT, and an OR. The AND and a NOT for the 0. So let's go ahead and do that one first. AND equals NOT. I'm going to put it in parentheses just to make it a little bit more readable and contain it. 1 left shift, and we're working with the pin number here. This is what we're given. So we'll start with the pin number, and we multiply that by 2, and we add a 1. For the next one, we're going to use an OR bitwise operation, and we're not going to add a 1 to it because we're not looking at the second position. We can do the same thing with the speed register because that's also a 32-bit number. So I'm just going to do a copy and paste here for the speed. This is where the information using the left shift and all the detail that I've given in the AVR series of microcontrollers and programming, this is where this stuff comes in really handy. So if the left shift and the bitwise operations and all that stuff really confuse you and you're not understanding it, I highly recommend going back to the AVR series and checking out those videos. Because really, you're doing exactly the same thing. All we're doing is manipulating numbers within registers. It's just like going to a large control panel and just switching switches, the ones that we need to use at the moment. So in this case, we're just doing the ORing on both of them because we need a 1 and a 1 in both positions. Since we needed a 0 in the other position, we needed to do an AND and a NOT. For the type register, we're going to be doing the AND and NOT. Now let's just rewrite it. Port, the O type, output type is going to be an AND equals NOT because we want a 0 in that position. We'll use the left shift bitwise operation, and we're going to be using the pin number straight. So we're finished with the type, and the pull up, pull down looks like it's the same thing. So we'll just do a copy and paste. PUPD register. I put a space here so I can read it. To execute all of this, we're going to have to use it in the main part of the program. And for the port, we're going to do the same thing as we did over here. The LCD D0 port, we'll start with that one. The LCD D0 pin. We're setting the port and pin for output for the D0 port and the D0 pin. Very simple. We'll do that for all of them. And we'll just replace these with the appropriate numbers. 0 through 7, we'll do that to the pins. Just as an aside, in this case, we have two lines. We can just put it into one line just by separating it with another OR because they're the same operation. They're both ORs. Okay, so we have all of our pins set. We can actually remove these, but I don't want to get rid of them yet just because in case this program doesn't work, I can use this for debugging. So I'm just going to comment out these for now. So let's take a look and see if it works. Okay, we do have an error, so let's take a look and see what we have. And this is really good. It's catching us on some simple math computation errors, because if I did a pin number multiplied by 2, I would get, say, if I started with 15, I would get 30, and then I added 1, and I would get a 31. But if I did 2 plus 1 first, which is 3, 15 times 3 is definitely not 31. That would be 45. So it's actually saying to contain the parentheses around the plus, but I would rather actually contain this. So it does this first or separately than the 2 plus 1. So let's go ahead and do that. So we're going to do it on all the instances where we're doing mathematical computations within a left shift. We're going to contain this portion. Let's see if we only need to do that. It might ask us to contain the entire thing as well. I'm not going to contain this because this order of operations would be fine. Let's go ahead and build and see what it says. It's still saying to do the same thing. So I'm going to go ahead and contain all of it. Okay. Let's try it again. Okay, we have no warnings. That's good. And the build is successful. So let's go ahead and program the microcontroller and see if we still have the letter A outputting to our pins. The microcontroller has been programmed, and you can see that the correct pins have been output as 1s and 0s. You got the 1 and then the 5 zeros, a 1 and then a 0. Let's go ahead and replace that A with a B and see what happens. Okay, so let's take this and put a B here. You can see that these two pins changed because the lowest bits, the first 2 bits in a change from a B to an A is only going to change from this being a 1 to this being a 1, because that would be 2. This would be 1, and then putting a 1 in this position would be a 2. A 3 would be both of these lit up. So a C should cause both of these LEDs to light up. So let's try that. Let's change this B to a C. And it looks like we got exactly what we expected, as these both lighting up to equal a 3. This one is of course going to stay the same unless we went way higher up in the ASCII code. I think at this point it's probably safe to go ahead and get rid of this. I can delete that since I know that the program is working. There are a couple of things that I still want to do with the program before we get into the actual looking at the LCD and looking at the timings and seeing what we need to do with the enable, read write, and register select and the data pins. And that is, we haven't really done anything with the reset clock and control register and making this automatic. Currently, we have to manually enable the GPIO-B and the GPIO-C ports. But what if we use another port? You know, we can, if we just use these 2 lines here and only enabling B and C, we can only use B and C in these defines. So let's take a look and see how we can make this more automatic. The idea that comes to mind to figure out how to determine the GPIO according to this address or this designation is to put it directly into this portion or this function. Because what we're doing is we're specifying the port here, and it could be any port. So we can put a condition: if port, this particular port, is equal to, say, GPIO-B, then we invoke this particular one. So we're going to have to do this for each port. So let's go ahead and try to do that. I'm going to go ahead and do a copy and paste. And I want to do it at the beginning because I want to make sure that I'm setting the reset clock and control register before I actually change the output state or the state of the port itself. But I also want to do another thing. Let's start putting the condition in first. Let's say if port is equal to GPIO-A. Let's do that first. Let's give some space here. Then I'm going to want to put the A here. But I think I also want to figure out if it's already done, if it's already set. Although actually I'm not really sure that's necessary. It doesn't hurt anything to actually just set it, because we need it set anyway, and we can do it every single time. Even though it's already been set, we can set it again, or just make sure that there's a 1 here, which is what we're doing anyway. Let's do this for each port. We'll do that for B. We'll do it for C, and D, E, and F. And if your controller has more ports, then I would add more here. Let's actually see how many ports there are on this particular one. Okay, so it looks like there's A, B, C, D, and F. There's no E. So I'm not going to be able to do this E here. Yeah, see, it doesn't. I put the E inside that to change it, and the options it gives me is all of them. So it's telling me that there is no GPIO-E, so pick from any of these, because that's the closest match. So I'm going to use the F. And with this change, we should be able to remove it here. So I'm just going to put some comments here just in case we still need it. And now what I want to do is put this into a function. I want the actual main to be very minimal and only calling certain functions to initialize the ports and to actually send the characters. Let's make another one here. I'm going to call it initialize ports for LCD because this is going to be under the LCD header file, and if we have to initialize other ports for other services or features, we can name it for that. There's not going to be anything passed in, so we'll just leave that blank. And then we're just going to take this and move it up. And we want to initialize the ports here. Okay. All right. Let's see if this experiment works. I'm going to just do a quick build just to see if we have any errors. It looks like we have an error. GPIO-E is undeclared. You see, we know we don't have a GPIO-E, and that's exactly what I thought. And we actually didn't change it here. So let's just change this to an F. And we should be okay. So you can see what we had in the beginning is the letter C. So let's go ahead and flash it and see what we get. And I see it right here. We're putting it in the wrong function. The function we're putting it in is where we send the bit to the respective pin and port port and pin. That's not where we want to put it. We want to put it where we're doing the initialization of the port itself. So we're going to cut it and move it into the set port and pin for output. I generally put initialization stuff at the top, and I put other functions below the initialization. So in my habit, I looked at the very top and I saw something with a port in it, and I put it in that location. And it looks like it works. If you look at the program, we don't have much in the main anymore. We have very little. We can actually take all of this stuff out right here, and you can see how small our main code is. We have pretty much everything above the main, and we can take all of this stuff out. We don't need this in this program at all because we're going to make a header file for the LCD. So let's go ahead and do that. The main.c will be under the app. So we're going to select the header extension, call it LCD functions. So you can see another file was added called LCD functions, and there's no code inside this. The first thing you want to put into this LCD functions.h in every header file that you make is using the if not defined statement, and then you want to end it. And this is a directive or a condition that I'm going to implement that will only allow the function, the LCD functions, to be executed once. Because we could have the LCD functions header file in many other files, many other sub files or other header files, other C files, as we make larger and larger programs and more sophisticated programs. We only want all that code that's within this, if not defined, to run once. So the way we do that is we create a define, and we're going to call this program something, LCD functions header. And we have to copy and paste that specification, that identifier, to the if not defined and the name of the define. And then all the code that we don't want to run more than once will be in here, because what it's doing is saying if the functions header is not defined, then define it, run the code, and then now it's defined within our entire solution. So now we can put the actual code within this location, and it'll only run once. So let's go ahead and cut the defines and paste it in. So now these defines will only run once. I'm going to do the initialization first. That's why I wanted to do it one at a time. So set port and pin for output. That's going to be the first thing I want. And this is not because they have to be run in a certain order. It's because for me, it helps me understand and make the code more readable when I put the initialization at the top and I put the simple functions after that and then the more complex functions after that. The initialize ports for LCD, this is a little bit more complex than the actual specific function to do that. So we have the initialize ports for LCD. Now we're going to go to the next one, send a bit to the port and pin. We're going to cut that and paste it here. And then we're going to take the last one, which is the sending a character to the data pins. Takes advantage of the function we just created. Cutting that, we're pasting it here. So this is the beginnings of the LCD functions. Go ahead and save. We need to include the LCD functions. So now we're including all of the code that we have here a single time. So let's go ahead and try it. And it looks like it still works. So success. Let's go ahead and put a D in there just to make sure that we're working with the right program. Okay, good. You can see that the A, B, and C use these two pins, and then D is 1, 0, 0. So that makes a lot of sense. I'd like to take a look at controlling the LCD by using the timing diagrams in a specific way. Here are the timing diagrams that I'd like to look at first. You have the LCD write operation, and you can see you have the enable, you have the read write, and you have the register select. And you can see that you have the actual high or low signal, and you have the required timings between when that signal has to be high or low with respect to other signals. For example, the enable cannot be used until the read-write goes low, and that a certain amount of time has been passed before the enable is high. And the same thing with when the enable goes low, a certain amount of time has to pass before the read-write can go high, or before the register select can change its signal state. So before we do an enable, the TAS, the RS, or the RW, the read-write or the register select, the register select or the read-write must be changed before the enable. So let's take a look at the TAS. symbol for the write operation. And most of these units are going to be in nanoseconds. And I think I want to write it in this way too, so I can write it as if it's code. So this is the position where the read-write or the register select must be changed. The read-write must be either on idle state, which is low, or it must have gotten from the high state to the idle state. The register select must have actually gone from low to high or from high to low before the enable goes high from its normal state of low. So I'm going to put in a sort of a dimension between here. And the TAS must be a minimum of 40 nanoseconds. So this is 40 nanoseconds. Okay, so the TER, the symbol TER, is the enable rise and fall time. I'm not going to worry too much about this. So the time the read write and register select where the enable is on, and then to where the enable is off, which is the PWEH. And the PWEH has a minimum of 230 nanoseconds. Now we know how long the enable has to be on. Actually, no, there is a number here. It's TEF, that's actually a maximum. The TER and the TEF, these two here has to be a maximum of 20 nanoseconds. So we can't have it going from low to high more than 20 nanoseconds. But we really don't have any control of that, so I'm not going to worry about that. So what I want to do is take a look at the next required timing, which is when we can change the data bits from a high or a low, or start writing the data to the data pins. And it looks like we just need to make sure that the enable is on when we start writing data to the data pins. So I'm going to erase this 230 nanoseconds. I'm going to put a line, and I'm going to say at these points, turn, and over here I'm going to put read write low and change register select. So first we have to make sure that the read write is low, and then we have to also change the register select at the same time, and then we wait 40 nanoseconds, and then we can turn on the enable. While the enable is on, we can start writing the data. It appears that the value here doesn't actually need to be set, or we don't have to wait any specific time. We can just start immediately sending the byte or the command. We have to wait a certain time after we start or after we output the byte that we can turn off the enable. So let's take a look. What is that DSW symbol? That is a minimum of 80 nanoseconds. So now we can turn off the enable after the 80 nanoseconds. After we've turned off the enable, we have to wait this long, the TH, before we can send any more information on the data pins, or before we can change the read write or the register select. Looks like TH and TAH are the same. Let's see what the differences are. TAH is 10 and the TH is 10. 10 nanoseconds. So this is 10 nanoseconds. So we know we have to wait 10 nanoseconds before we modify the data pins, or we change the read write, which is going into the read mode, or we change the register select. Actually, because the read write is always in write mode during the sequence, we shouldn't say change, we should say bring read write high. And then we have a final requirement here where we can't bring the enable high again to do another operation, to start another cycle. And this could be either a read cycle or a write cycle, because you'll have the read operation. You're also doing the same thing with the enable. You're bringing the enable high and then you're bringing the enable low again. And you have the same symbol called TCYCE, enable cycle. And for both of those, it's 500 nanoseconds. So in this section here, we have approximately 130 nanoseconds. So around here, you're going to want to wait probably around 400 nanoseconds minimum. I plan on putting the LCD along this area here, about 14 pins. On the breadboard, I have, including these two LEDs, 14 and 15. So I do have enough pins here. So the register select could be the first one. So the read write would be the next LED. Enable would be the LED that's on this pin here. And then after that, we can have these pins from D0 to D7 along this side here. We're using the pins number 33 through 40. And 33 is at this location of the breadboard, 33 and 34. So we'll need 3 more pins. And I think 41, 42, and 43 would be fine since they are also the 5-volt tolerant pins. I'm going to go ahead and apply some LEDs to those pins, and then we can test the enable, read write, register select, and the byte again. So let's get started. And I'm going to take these completely out. And I can easily just connect this VDD to this one here. So let's connect the VDD on one side to the VDD on the other side. Now we need to take the ground and put it to the ground rail on the other side. So we have the positive going to the positive, and we have the negative here going to the negative rail on the other side. So we have the positive supply, pin number 32, going over from this tie strip to number 11 tie strip and going to the positive rail. And we have the ground, number 31, pin number 31, going to tie strip number 10 here, and then going to the negative rail. Now we have more than enough space to put the LCD in. There, I'm going to go ahead and turn this on just to make sure that it has the last thing that I programmed and everything works as expected. We can go ahead and try putting another character. Let's go A again, compile it, and then program. Okay, it works. Now I'm going to add 3 more LEDs to this location. I'll probably reassign the pins where I'm outputting the byte to these pins here, and then reserve these 2 pins and the next pin here for the enable, register select, and the read write. Since we use defines, it should be pretty easy to reassign them. I'll go ahead and add 3 more resistors first, and we'll add 3 more LEDs. It's kind of hard to see which one is in sequence. I could share some holes on the negative side. Now that we've done that, I'm going to plug it in again just to make sure it works. And it works. Program. We'll go to the LCD function.h. Since we need to adjust the pin numbers, let's take a look at what new pins we'll need to use. We're going to be using 8, 9, and 10 on port A. So this will be for the byte, enable, read write, and register select. So we'll make this one for enable. This one will be enable, read write, and register select. The D0 pin is going to be going to GPIO B15. So D0 is going to be 15 on port B. D1 will be 6 on port C. 2 will be 7 on port C. And this is going to be 8, port C, 9, port C, and then we have 8 on port A. 9, port A, 10 on port A. Now let's set up our enable, read write, and register select. So we're going to put in 3 more defines. LCD enable, and we'll make that one 14. Wait, this is pin. Let's say the E pin. 14, and E port will be GPIO-B. So let's do the read write. Pin is going to be number 13. Read write port will be GPIO-B again, and then the register select is the last one. Pin number 12, port, and that's C, and the port here will be GPIO-B. Now we have the defines complete, hopefully. We can go ahead and initialize the ports for the new pins that we have. We should have 3 new pins. I'll go ahead and just do three of these. The enable pin, I'm just going to do a copy and paste. Enable pin, and then enable port. And we have the LCD read write port, read write pin. And the last one is register select port and the LCD register select pin. And we're just enabling those pins on the microcontroller to be set for output. Let's just see if those pins work. We'll light them up and make sure that we have correctly assigned the pins. We should get the letter A again as an output, but in different pins instead of the pins that we used to have. And then we should also see the enable. Let's go ahead and make the, we'll use this one, and we'll just set them to output. So we'll put this in the main.c, and we'll just manually set them to output. So let's do LCD enable port, LCD enable pin. And we'll just put a 1 here, true. Read write port, read write pin. Set a 1, and LCD register select port, and LCD register select pin. And since we're just putting 1 here so we can light up the LED, looks like we got the correct output. These 3 pins we wanted on, this one, and this one. This is the register select, this is the read write, and this is the enable. Those 3 are on. And we have the A, which is a 1 in this position, a bit high in this position, and a bit high in this position. So we have the correct output. Now let's turn these off just to make sure that we have it set correctly as well. Actually, I'm just going to comment out those so they won't be executed. We have the correct output showing just the A, and those are off. We can test the timing diagram and the code that we have to create. I plan on setting the read write and the register select. The register select is going to set between either writing a character or writing a command. So we're going to set the read write, change the register select. We'll wait the 40 nanoseconds and then turn on the enable. This will be in one function that I think would be most appropriate put in that function. We already have an output byte function, so all we really need to do is add the turn off the enable after 80 nanoseconds in that same function. So we can bring those together. So this one will be setting the read write, setting for read or write, or and register select for character or command. And the next one will be outputting the byte and simply turning off the enable. Now I'm going to also add this 10 nanoseconds in this function as well. So we definitely need to wait 10 nanoseconds until we do any more modification with the data pins or modifying the read write and register select. At first, we're just going to have this stuff running really slow so we can see it on the LEDs. And then I'm inclined to hook it up to the LCD to output some commands and characters and see if it works with just a slightly faster speed, because all of these numbers are minimums. And that way we may not have to read it to check to see if the LCD is busy. And we'll go faster and faster to see at what point it breaks, if we get to that point. But because we haven't gotten into the timing section of the microcontroller, we really can only use sort of just a time delay of our own choosing. So let's create a time delay within the header file. Put it up at the top. I'm going to call it a non-exact time delay. Pass in an integer of time delay, and we'll just do a loop. So all we're doing is we're creating a for loop with the actual time delay number here, and the integer can go pretty high. So I'm not sure, I don't think we have to put anything in here, but we can later on if we have to. Okay, so let's go to when we're sending the character, let's go ahead and put in the turning off the enable. So all we have to do in this case is access the enable port and then access the enable pin, and we're just going to put a 0 in here because we programmed it so if the bit state is a 1, it will set it, and if the bit state is 0, it will reset it. We need a time delay here, so let's go ahead and, since I automatically thought it would be not exact, I'm going to go ahead and put a not exact time delay. We'll just put 10,000 in here for now. And what we're doing is we're putting in this time delay here. Could put like 80,000 just to see what happens. Might be too slow, but let's do that anyway. So we have a proper proportion. If it's too slow, then we can knock it down to 8,000 or some fraction thereof. Okay, so we are outputting the byte, we're waiting some time, and we're turning off the enable. So let's create the function that sets the read write and our register select. Just a very simple function for that, and then I'm going to say void command mode. There's 1,000 ways to do this. I could actually have something brought in here that says command mode that's defined as a specific setting, or I can have simple functions that just specify what you need to do. Kind of want to do it this way, but we can try both ways. We'll see what happens. Command mode, and let's see, void character mode. Let's see how many things we're going to be duplicating here so we can make the code more efficient later. First, let's set the read write, register select. Command mode is simply setting the register select to 0. So let's do that. Go with the register select port and then the LC register select pin, and we're going to pass a 0 to it. This is command mode. Character mode, we're sending a 1. The read write, we should already know that. To write, we send a 0. We send a low. Port and the LCD pin, bring it low so we can write to the LCD, the opposite for reading. We need to wait for about 49 nanoseconds, so I'll just put an arbitrary, each one of these will have to have that. This is where things get repetitive, but let's go ahead and see what happens. We'll use 40,000. You can already see where I'd have to change all of these if we were going to automatically scale everything down to more appropriate time delays. So maybe what I'll do is I'll set we're going to turn on the enable anyway, so we can put both the time delay and the enable in there. So let's just call that enable. Pull this time delay into that location, take all the time delays out of here, and we're going to turn on the enable. So we're going to turn the enable on in this case. Replace the time delay. So now we can enable the LCD here at the end of each one. So we're going to take the time delay out of this, put the 40,000 here. Let's do the time delay up here actually. So let's define time delay before enable, and we'll call that 40,000. There we go. So now we can just change it in the defines. We should do the same thing to the 80,000 here. So that one is between the output byte and turn off the enable. So let's say disable. So time delay before disable. There we go. Okay, let's finish up enable LCD in each one of these. Okay,
So now we can, if we're going to send a character, we may not want to call this sending a character. We can, because that could be a command or a character. And we'll make a couple more, send a character and send a command. This can probably be cleaned up later on. So sending a character, we're going to have to pass in a character. So it's going to be a car. Put it into the write mode, set to write. You know, setting to write, I want to say set LCD to write, because I might have some other set to writes somewhere else. LCD command mode and LCD character mode. You know what, if I start them with LCD, that might be a better way to find things later on. So LCD set to write, LCD set to read, and every time I put in LCD, it'll give me all the commands nicely. And this can stay the same because I'm really just sending the bits to the ports and pins, so it's not really specifically for the LCD. Put LCD there. And in the main, we have to put LCD here. I might be missing some things, but we'll find out when we do the build. Okay, so we're setting it to write mode, and then we're setting LCD. Now we can look for the one we want, putting it into character mode. And now we're going to send a byte, and it will be the character. So LCD send a character will be the main sending the character to the LCD. And I want this at the bottom because I think it makes more sense for my more major, the ones that would be going into the main.c to be on the bottom, and the more basic specific only to the LCD should be at the top. So when we run this, this should actually be, the LCD should not be lit up, the read write should not be lit up, and the register select will be lit up. You know, why am I'm not going to be enabling the LCD after the read write, because it's doing that in the command or character, because I want to just write it, set the command or character, and then I'm going to delay after that. I'm wondering if the delay should be actually over here. That makes more sense. So this is where I'm enabling it. So I'm setting the read write, setting the character, enabling it with the time delay, and then I'm sending the byte, and then disabling at the same time within this. Let's put the LCD in the front. All right, I'm going to do a build just to see if I have everything correct. I'm expecting to get errors because, yeah, too few arguments. So sending a byte to the LCD data pins. We have a character here. Oh, look at that. And actually, I'm not going to be putting this one here anyway. I'm going to be doing send an LCD character. I'm going to use the A like we did before. We can remove this one. So we're just doing LCD send a character. Functions. I still don't think that I have this all right. I'm not sure if I want to do it in this way, because I could, for the read write, I could just put set read write pin and then put in read or write. But it's a little bit more difficult to understand how to do that as a person going into the main and just trying to do it for the first time. If they take a look at the LCD and everything that's in here, setting it to read, setting it to write is a lot easier to understand than setting read write and then what to put inside of it as a parameter. So let's take a look and see what outputs to the LEDs when we do this. I just noticed an area that might cause a problem. And in my previous programs, what I would do is I would do a volatile int for the I in this for loop, because if I didn't do this, then they would optimize this whole thing out. I mean, it wouldn't actually run it, because when it does the compiling of the program, it doesn't think that this is a changing variable throughout the program, then it won't actually use it and it'll be optimized out. So by making it volatile, it knows that it needs to keep that variable going in the program for the time delay. You can see that it went pretty fast, probably too fast for us to see it clearly. We can definitely see the enable LED flash on and off. So let's slow that down quite a bit and see if we can make it a little bit more discernible. And I'm going to multiply these by 2. So I'll do this 8,000 and I'll do this one, or 80,000, and I'll do this one 16,000. Yeah, it's still pretty fast. So I'm going to add another 0. I'll go back to 40,000 and I'll make it 400,000. I'll go back to 80,000 and I'll add another 0 for 800,000. Okay, that makes more sense. Okay, so the register select turns on, and then you can see that the enable turned on and the byte was sent, and then the enable turned off. So it looks like it works correctly. Just for my own purposes, I want to show this in a loop. I'll probably pause it between the loop, or the beginning and the end, 10 times or so. So I want to see it over and over again just to make sure it works correctly. I'll put a time delay before it, or after it actually. Why not? There has to be a time delay after it anyway, so this may not even, I mean, we have to put this in the LCD, and we'll probably change this because this doesn't seem like it's LCD related, but we'll keep it in there anyway. And time delay can be 1,000,000.
Let's see what that does. Really cool to increment this every time, like A, B, C, D. Let's see. Could do that. Car letter is equal to A, and letter plus I. So this way the letter can be A and then it'll increment. It'll be B and then C, D, E, F till it exits this for loop. This while loop is here. It's just keeping the microcontroller on and not exiting out of this. Looks like it's working. We should be able to go ahead and add the LCD. I'm going to remove these two LEDs. I'm going to go ahead and put the LCD from pin 30. So we're going to need to find out where we're going to put a potentiometer. All these tie strips are going to be reserved. And also we have these two pins here that are going to be brought over as the register select and the read write. So I think the only place to put the potentiometer is over here. So let's go ahead and do that somewhere over here. Probably as close to these wires as possible so I can utilize as much of this board for other purposes later on. This side still needs to be put in. So we can see that we have the 5 volts just below the 3.3 volts. And I have the 3.3 volts right here. So we can just plug one more in and we'll have a 5 volt. Before I connect it to the breadboard, I'm going to test it with a voltmeter, just to make sure it's outputting 5 volts. Okay, I got 5.14 volts. That's good. To convert my female header into a male, I'm just going to take a header, even this out a little bit, plug it into the one end of the potentiometer. Before I connect the power 5 volts to the LCD, I'm going to connect the ground coming from 31. I'm going to connect this ground to the ground of the LCD so I know where the first pin is that we need to use, because these two are not connected and this can confuse me on where to start, because I often think that this is the VSS pin or the ground pin, but the third pin is actually the real ground pin. So I'm just going to take a jumper and put it from this position, which is the 31 on the controller card, and that's the ground pin. And it's going to go to the ground pin of the LCD. So now I'm going to take the 31, the ground, and I'm going to connect it to the potentiometer. So the potentiometer will have a ground and a 5 volts. So now we have the potentiometer connected to ground to the 31 pin. I'm going to go ahead and connect the wiper pin here from the potentiometer to the V0, which is all the way over here. You have the wiper pin connected to the V0 pin of the LCD. That will be now the 5 volt pin. The VDD will be the next one. And we'll connect that one to the potentiometer lead here, which is also connected to the 5 volts. Okay, now for the 5 volts. So we wired up ground, 5 volts, and the V0. So we can actually turn this on and see if we can adjust the contrast. We'll probably just get a bunch of boxes along the display. So let's see if that works. Right now we don't see anything, so let's turn the potentiometer. There we go. So the contrast is working correctly. .33 is our next pin we can connect, and that's going to be register select. So we can connect that over to the next pin here. 33 to the RS pin. Pin number 34 to the read-write pin. Okay, now we need to take all of these pins, connect them to these pins. So I'm going to take these out first. The enable will be connected from 35 to the enable. Now we're going to connect the data pins. D0 will be connected to pin number 36. D1 will be connected to pin number 37. D2 is connected to pin number 38. D3 is connected to pin number 39. D4 is connected to pin number 30 to 40, actually. D5 is connected to pin number 41. D6 is connected to pin number 42. And the final one, D7, is connected to pin number 43. So we have all the data pins connected. I want to take a look at the data sheet and show you that they're emphasizing that you should make sure that the LCD or the chip that is on the LCD is not in the busy state when we're trying to send data to it. It's also saying if we don't check for the instruction, if we don't check for the busy state, then the time between the first instruction and the next instruction will take much longer than the instruction time itself. So it looks like it's just a function of taking a longer time, but in our initial tests of the LCD, we're not going to be checking the busy state, and we're going to be increasing the time quite a bit anyway, so I'm just not going to worry about it right now. And following that, they have a list of instructions that you can use with the LCD. On table 13, it shows some of the steps you have to take to write characters on the LCD. And this is table 13, and it shows a 2-line display, which is what we're using. And you have to go through a certain order of operations here. You have to initialize, which is just turning it on. And this will set the LCD to 8-bit operation and selects 2-line display and 5x8 dot character font. And then we turn on the display and the cursor. You can see the cursor there. And this command is telling the cursor to increment to the right 1 every time we send a character. Sometimes I don't actually like to put the cursor on here because when you're putting out information really, really fast, that cursor will be flashing all over the place. So you might want to turn that off in your application. And we may do that in this tutorial as well. And this is writing data to the LCD. And they're calling it the CG RAM or DD RAM. That's just the memory within the LCD, and it's just writing that to the display, whatever is in that part of the memory. So it's actually this part right here. So if we look up 01001000072, let's see what it is. Yep, that's an H. So you can see that these bits create an H in binary. And you continue doing that and keep writing data to the LCD. So let's go ahead and start putting in some of this information in the program. We don't need any of this stuff anymore. First, we need to make sure that it's going to be in write mode. Let's first create a function to write a command. We'll just do a copy and paste of the character and send a command. Well, they called it instruction in the data sheet. But I've been using command for so long. Yeah, I'm only using it in 2 places. Send in an instruction. And I'll change the LCD instruction mode. Yeah, that's all I'm using, I think. So we want to make sure that it is set to write. The LCD is in instruction mode. Let's save first. Better write the whole thing again. Okay, so we set it to write, set it for instruction mode, we enable, and then we send the byte to the LCD data pins. So the first one is, actually, I don't think we want to do that. We don't want to, we want to make sure the instruction mode, the RS is low. Okay, so in the main, I'm going to go ahead and keep this as an A, because eventually we're going to be sending a character anyway. LCD send an instruction, and the instruction is going to be in binary form. I'm going to use 8 zeros, and I'm going to put the ones where they need to be. In the data sheet, where you see these stars, just means that it doesn't matter what you have in here. It sort of ignores those. So we have 2 zeros, 3 ones, and 3 zeros. And this one is set to 8-bit mode and 2-line display. So let's create another instruction. And the ones in this one are located right next to the last one. And this one is turning on the display and cursor. Sending another instruction, we need to set the mode to increment the address by 1. And now we can start putting in the letters. Let's try newbie hack. It put ABC in there first, which is kind of weird. I have no idea why that happened, but we'll find out. You'll see how slow it's going on. So let's reduce the time delay and see. At this particular point, I don't know what's going on, but I'm going to try this instruction to make it go to the second line, just to see if it goes to the second line or it creates some character that would be associated with this binary number. So I'll put the hack on another line. Go to the next line. 1, 1. Okay, so let's see what happens with this. Reduce these 400 and 800. It should be instantaneous. Okay, it did go to the next line, which is kind of interesting, but it shows an A. It didn't clear the screen. Let's see what is the command to clear the screen. Generally, when it turns on the display and it resets, it should do all that. Clear display. There's just a 1 on the end, so let's do that. Let's clear the display. All right. There we go. Reduce the time delay just to see what happens. Okay, so that's too fast. Increase the time delays and okay, newbie hack. All right. Instead of sending characters individually, I would like to send them as a string. Pointers are just pointing to a specific memory location, which are called addresses in programming terms. So in the microcontroller, you're going to have a specified location for memory. Memory is actually the main component in microcontrollers and computers, and there's addresses for almost everything and to control everything, even registers and things like that. And the memory is like little boxes. You can think of it as like a grid. So let's say this is just a portion of that memory, and we specify a character pointer, which is specified like this, and we store a set of characters within that car data type. It really is only specifying the location of the first character because the car data type is only one character. It can't hold all of this. But by putting the pointer there, it is specifying where the first one is located. So let's say that in our memory, the location is here. And by using the pointer feature of the C programming language, it specifies this location, but it also not just specifies the location, it knows what's inside of that location. And this data type, of course, is going to have some kind of name. Let's say we call it text. Well, text is the actual variable that we use to access this location. And if you increment text equals text plus 1, then it will know what's inside of this location. So this is plus 1, and this is plus 2, and so on. The cool thing about specifying pointers over arrays is that you don't have to declare a specified number of locations, because at the very end, it will add a null character here. So we can have a loop that iterates through all of these locations, and then at the end, all we do is we either test for null or we see if the character within that location is greater than 0. I know that way works because I've already done it. I haven't really done a iteration that tests for null in this particular type of context. So let's go back to the program and add another function into our LCD functions. We're going to go to the LCD functions and let's go to the end here where we actually send a character and send an instruction. This function doesn't need to return anything, so it's going to be a void, and we'll call it LCD send a string. So what we're going to pass in is a car data type and a pointer, and this is where we name the variable that we're going to be using within this function. And here we can say string of characters. Within this function, we're going to be sending a character multiple times until it gets to the end of that string. So we're going to go ahead and use the LCD send a character, and then it's going to be waiting for a particular character. So we're going to be using the string of characters. We're going to use the pointer because it needs to know where it's located and what is inside a string of characters. Okay, so that's actually looking at the very first character. So if I actually ran it right now, it'll only, if we're using the word newbie hack, it will only show the first character, n, and then the function will be completed. Let's see what it would look like if we did this in longhand. So if you wanted to show this without a loop, then we can do this. You might find it strange that I'm putting the plus plus on the left-hand side of this variable, and that's because this is actually the first character, and if I put a plus plus on the left-hand side of it, it would increment first, so it would be actually looking at the second character. If I put the plus plus on the right-hand side, then it would look at the first character and then add 1 to itself after it has passed in the first character. If I do it this way, then I'm going to have to do that way all of it. So we just need a way to do this multiple times and stop when it finds that null character. If we want to try using the null as the condition, let's go ahead and see what that would be. So let's use the while. We'll take this line and put it inside the while loop. And this is exactly the way it needs to look inside the loop. It still needs to be in this form with the plus plus at the end. So the first time it goes through the loop, the first instance of this, it'll only be considering the pointer and string of characters and not the plus plus. So it'll look at the very first character. So what do we put inside here? Well, why don't we just put this inside there? Because what I've learned is that a condition is true if it is either non-zero or non-null or not null in the ANSI C language. So if this is not 0 and it doesn't contain a null character, it should be able to be true and go into the loop. So let's actually see if this works. Let's go ahead and put this into the main.c. What I want to do is I want to do the character by character on the first line and then the string on the second line. So I'm going to put this above the, I believe this actually clears the display. So I'm not sure if we actually need this because we're turning on the display and cursor here, and it may actually do the clearing as well, but let's keep this in here. All right, so I'm going to introduce the new function. I didn't save the file yet. Send a string, and then we're going to send the string newbiehack in lowercase so we can actually see the difference. It worked. And it looks like the condition that searches for a null or only accepts either a valid character actually works. So that's awesome. Okay, let's see how we can send numbers to the LCD. This is our skeleton code, and we have the LCD Initialize and the LCD Setup Display. When we were looking to send a number to the LCD, we can't just send a number by itself, like LCD send a string, and then type in the number 200. This is an actual number, and this function doesn't accept numbers. It only accepts strings. And another way we would want to do this is to have a variable, let's say an integer, and it's equal to 200. We would want to be able to send a variable to the LCD as well, but obviously we know that we can't do this because this is not the correct data type in this function for send a string. So let's see how we can do this. First, we need to take this integer and we need to convert it into a string. So the LCD send a string will be able to handle this. So the way we do that is using another function called sprintf, but we don't have that available to us right now because we don't have the proper include for that library. And the include is stdio, which is the standard IO library for the C programming language. So we're going to include stdio.h. So we're going to use the function called sprint. You'll notice that there are some inputs that it's requiring. And the first one is a car. So let's go ahead and set up a car variable. And let's say this is string number. We'll just call it string number. And then we'll leave it at that. So we should have the variables set up for us. So we're going to start off with putting the string number here as the first input. The second input will be a format. So this is going to be in the form of a string. And the first character we're going to put in there is the %sign. And then the following character will be a letter determining what format the next variable will be. And in this case, it's going to be D for integer. I believe you can also use the letter I, but we'll use D because that's commonly used. And then the next input will be the actual integer. So we'll just do a copy and paste of that. And you'll see that there doesn't seem to be any errors. So let's go ahead and do let's go ahead and put this one in the send a string, because this is the actual string that will contain the converted number. So if I create that as a pointer, let's initialize it with an empty string. Sometimes it's actually good to have an array initialized because in the LCD, you don't want the number of characters to exceed a certain amount because you only have so many characters available on that LCD. So sometimes it's good, but I'm going to try it like this. And we know that like an integer, if we know what the maximum minimum values are going to be, then it shouldn't matter. Okay, so let's go ahead and flash the microcontroller and see if it works. And it looks like it did not work. Just to make sure that we're able to actually do something on this. Okay, we can't even output it 200. It looks like I am unable to use the pointer type or the pointer to a variable. It just doesn't work. And I'm wondering if it has something to do with memory issues. So we have to make this an array. I'm going to use 5 characters. This is only 3 characters, but it doesn't really matter in this particular case. That's just in case I have a number that goes up to 20,000, an unsigned number. I can actually put that on here. That's only for numbers above 0, unsigned. Unsigned means it's not going to be negative. Let's flash the microcontroller. Let's see if we can create another function that only outputs numbers. So in the LCD functions, we're going to essentially place this in the function. So I'm going to copy this, and we'll create another function that outputs numbers. So this is going to be something that doesn't require a return. And we'll call it LCD send an integer. I guess we could make it so it sends other variables like doubles and floating points, but I'm going to make this simple at first. So we're just going to make it so it sends an integer, and we're going to want to receive the actual integer. So we'll make it a signed integer just in case it has to be a negative, and we'll call it integer to be displayed. And that should be all I need to pass in. All right, so let's go ahead and paste
what we had. So the string number can be just, I would like to make this a little bit more. You know what? There's another number we need to pass in, and that is length. This is going to be an unsigned integer. Actually, it can be a, let's see, length of, do I have this variable type available to me? Well, we'll find out. We'll call length of digits. That should be easy enough to understand. I'll use that here. And then the integer will be equal to this, but we don't really need to actually use that line. We're going to copy and paste the actual integer to be displayed in the sprintf function. And that should be it. So it should just go ahead and send that string. So let's try this out. I'm going to do a copy and paste of this. Oh, why not just do it the right way? Save all this. LCD, send an integer. There we go. I don't like that big N. Okay, so integer to be displayed. Let's just call it 150. And then I'll need 3 digits for this particular number. I didn't put the include in the function, so I'm going to do that here. I got an error that said that it didn't know what the sprint command was, or the function was. So I need to actually include that in here, because you'll notice that I did this include after the LCD functions. And since this LCD functions uses this command, or this function, I really do want to put it in this header file. Okay, we got the number 150. That's good. You might be wondering, well, why do I have to put a specific number here? This actually should be a max number. I'm going to change the input variable to say max length of digits. And generally, when you're making something for the LCD, you have, let's say, 16 characters on the first line. And let's say you wanted to show a particular number, let's say pressure. And now you know that you have 6 characters remaining on that line. So you can just go ahead and put in 6 because you're going to use the rest of that line. Or you can not have a space here and you can have 7. And now you'll know how many characters or digits you can have on that line. And you want to also make sure that this number is not going to exceed that number of digits. So we have created a new function that outputs integers on the LCD. You can easily just go into the LCD functions and create this for any type of number, let's say floating point. All you would have to do is replace floating point. Yeah. LCD send a floating point number, and this is going to have to change to float, and this can stay the same. Remember that the max digits needs to consider the actual decimal point and the negative sign if one is going to be there. And the next thing we'd want to change, obviously, is the floating point number to be displayed, and we would replace that one. And the reason why I'm changing this variable, we really don't need to, but when we're actually using the function in the main file, or in the main code, it'll tell us what this is, what it's asking you for. So we want to make sure that we have that correct. And then this format has to change from D to F, floating point. You can also use the %E for the shortest representation of the floating point number. I'm not sure what that really means because I haven't really delved into that yet, but you can go look at the specifier for the printf under the AVCC specifications, and you can see all of the output types for, say, integer, octal, hexadecimal, floating point, scientific notation, even pointer addresses can be shown. So you have the possibility of creating as many types of numbers or representations that you want. And it doesn't have to be just these 2 characters. You can actually create going to the next line and all kinds of other types of formats that you want if you feel that it's necessary to put that in there. Okay, so let's go ahead and use this one and see if it works. I'm going to change this to F, save the files, and maybe I'll go to the next line. So which one is that? Let's see, send instruction. Go to next line. Okay. And then we'll send a floating point. Okay, and the number can be, let's say, 256.67. And then the max number of digits would be 1, 2, 3, 4, 5, 6. Let's say 10. We have 16 to work with, but actually, let's go ahead and put in something before that. So there's 6. Let's make this 7, just in case there's more digits we need later on. And LCD send a string, and we'll call this float. Let's see if this works. Build. Okay, length of digits undeclared. That's
183. Let's see what we did wrong there. Oh, max length of digits. Yeah. We have to do the same thing here. We changed that. All right, let's save the files and do another. And it looks like we have no errors. Let's go ahead and flash the microcontroller. Okay, we have 150, and you can see that the float, it actually gave us a few more numbers on there. So it's odd that it did a conversion and then added some more digits, 0.670013, and that's 10 digits. And I only asked it to print out 7, so I wonder what's going on there. After a bit of research, I found that the function snprintf is actually a better function to use because it allows you to restrict this number of digits that it stores in this particular array using another input parameter. And I'm just using the max length of digits that I'm passing in anyway, which is going to be the size of the array. And after a little bit of testing, and you'll see on the next portion of the video, that adding the +1 will provide the correct number of digits for what you specify in this input parameter. I haven't used it in the integer function. I'm only using it in the float function. Since the integer was working in the previous attempts, I'm going to keep it this way until I see a problem where it is outputting something that I wouldn't expect. A really good indication of how well this idea works would be to actually show the numbers changing on the LCD. So let's try to do that. I'm going to create a for loop that counts up from 0 to, let's just go to 10,000. So we want to put the function inside of this loop. We don't need the go to next line, and we'll take these out. So we'll just replace the 150 with I, and 10,000 would be 5 of them, but that doesn't really matter. 7 is fine. And we need a time delay in here, don't we? Let's do 10,000. Let's flash the microcontroller and see what happens. Oh, it's not clearing the display or going back to a specific place on the LCD. And that actually brings up a good point that we don't actually have a command that specifies the location where the cursor should go. So let's do that. I guess for this small task, just to see what happens, we can put clear the display on here, but it could make it so it looks more like a ghosted image. So let's see what happens. Okay, that looks like it works. The reason why you can see the numbers so clearly is because it first clears the screen and it sets up the display, and then it shows the integer on the screen, does a time delay, and the time delay gives it some time to show on the screen, on the display, and then it does a clear again. The only function that we're really missing to add to the LCD functions is to insert characters at any location on the LCD. Let's say we want to have a number to be placed in these 3 digits, and we always want those digits to be in these 3 locations. So you'll need to know what location that particular digit is. The alternative would be to always clear the display and start from this location and then start writing whatever we need on this line, and then going to this line and writing whatever we need to go on this line. And in the case of just putting a number in this location, we would have to first clear the display, go to the next line, and then have this many spaces to this point, and then write the number. But fortunately, there's a nice little command that you can locate the cursor in any of these boxes or digits. And it's called the DRAM address. Each one of these is a DRAM address. And to be able to access this instruction to position the cursor at any one of these DRAM addresses, it is 0x80 in hex, and that's the beginning. So you have actually, this is the binary number you have to maintain. It's a 1 at this location. And this, by the way, this is at D0 through 7. So this is the data pins, and you are just sending a byte. This would be considered the byte, as we all would know. So the instruction would always be 80, and then these remaining 7 digits, we know that 8 digits, or an 8 binary number, would be 256 as the maximum value, but 7 digits would be 128 as the maximum value. But you know that there are not 128 display positions, but we're talking about accessing a controller for standard displays, which may be displays of many different types of, let's say, multiple lines and multiple positions per line. So you could have almost any configuration as long as there is not a maximum of 128 positions for an LCD display. So this initial number would correspond to this address. But we don't actually know
what number would correspond to this address. So let's find out. We can do this by making a little program that loops through each of these digits. I want it to iterate through the entire display, but if I miss something, then it'll start all over again. So I'm just going to make a simple loop as long as I is less than 128 and I is incrementing. So let's first position the cursor. So we're going to send an instruction, and this one is going to be 0x80. 0 would be 1. That's the equivalent of 0x80. And then we're going to send a character, send a string. We want to send an x. Actually, I think I want to send a space and then an x. So what this does is it erases the x before it. So it looks like it's a walking x. If I'm going to do this, I'm going to think that the x is actually one step ahead of it. So I'm going to start out with -1 here. I'm wondering if that's going to cause a problem with my sending instruction. Okay, now I want to actually show the number of that position, the variable I is, so I know where that location is. So I'm going to position it at the same location. That's here, which is just the beginning, the first position on the LCD. And then I'm going to actually print out the I. I'm going to send an integer. I'm going to display I, and it's going to be 3 characters max. You know, I don't have to do this -1 here, do I? I can actually show it here as a +1. And it's going to start on the second one, but I'm not really worried about it because this would be the I. This position here would be I, and this position here would be I +1. So we want to show I +1 at the first position, what the actual number is. And now I want to add a time delay. And I'm putting the time delay at the end because I want to first show it, and I want it to be on the screen for a little while so I can read it and it won't disappear. I'll put it there for 100,000. That should be good enough. It might be too slow, but we'll find out. Okay, let's see if this builds. There are no errors, so let's go ahead and flash the microcontroller. Okay, I flashed the microcontroller, and it doesn't seem to be doing what I expected it to do, so let's see what happened. Oh, I see my problem. I didn't add the I to this. Let's try it again. And I needed to, because this is going to be adding I to this number, we'll just add it to here since this is already a 1 in this position. We're just adding a number to it. This is just a number. So by adding the I to it, it's just incrementing this number. So let's flash the microcontroller again. Okay, that seemed to work. It looks like it's a little bit too fast, so let's slow that down a little bit. I'll make it 500,000. Okay, that looks better. So we know the top line is from 0 to 15, so that makes sense. It would be like indexed from 0, so it would be 1 to 16, so 16 positions. You can see that it's still counting up, but it hasn't gotten to the next line yet. Now 40 was the next line, so 40 through 55. So let's take a look at what we need to do to create our function. So we know this is 0, and the next line was 40 and 55. So I want to make a function that, let's say, LCD set cursor position. And I want my inputs to be X and Y. But how do we make an X and Y coordinate if we have these numbers? So say I wanted to have the position be here at 46. Well, my X value I want to be 6. And my Y value I want to be, do I want to have the index from 1 or 0? So if I'm going to make this one 6, this one has to be 1. I think I'm going to make it indexed by 0. So this would have to be Y equals 1. So if I have X equals 6 and Y equals 1, then the formula would be position is equal to X plus Y times 40. Let's plug in the numbers. So if X is equal to 6, X 6 plus 1 times 40 would equal 6 plus 40, which is 46. If it was at the 6th position on the first line, it would be 6 plus 0 times 40, which would equal 6 plus 0, because anything times 0 is 0, and that would equal 6. So that all makes sense. So let's go back to the program and see what we need to do. So let's do another for loop, but I'm going to do a nested for loop where I have a Y, or X actually, X, and this will go up to 15. And then I nest it with a while loop. Y is less than or equal to 1 and Y++. So now I can cycle through the entire display using a nested loop, and it'll only show on the points that I need it to show. So let's send the instruction.
I'm going to do this with the hexadecimal code, and I'm going to add x plus y times 40. I'm going to contain the y times 40. Okay, so let's put a string. I'm just going to put an x in this one, and then I'm going to have a time delay. I'll make that 500,000 again. And this time, instead of putting that space behind the x, I'm going to erase the x on the next one. So I'm going to use the same position and delete the x just with a space. And since there's no time delay afterwards, it will erase this x immediately and then put the next x on the next location. So it should look seamless. Okay, the microcontroller is programmed, and it looks like I got the nested loop backwards. So that makes sense. It's going up and down the y and then the x. So I'm going to reverse these. Okay, let's try it again. Okay, looks like it's doing the right thing. It's going along the x on the first line, and right when it gets to the end, it should go straight to the next line. And it looks like it didn't go to the last position, and I probably have it because of the less than. Yeah, it should be less than or equal to here. So let's do that again. Let's test that one. 0, 1, 2, 3, 4. Will it get to 15? Yes. Okay, so it looks like the formula is correct. So let's go ahead and make a function. So I think the function is going to be, what did I say last time? LCD set cursor location. And then I'm going to bring in an x. I can make this a u, 98t, x, and y. Okay. Well, it's going to be a void. We're not returning anything. And the first thing we need to do is send an instruction. And this will be 0x80 plus the x plus y times 40. And this is for this particular LCD. So you'll need to plug in the correct number here for what position the next line starts. You can make a define macro that has this number in it. Let's go ahead and try that, see if it works. I didn't save it yet, so it's not coming up. So I'll just put x and y here. Actually, these are ints. I wonder if I can put u int. I don't think I've tried this yet. See if that works. So I'm going to do the same thing on this next line. So if this works, we are successful in making that function. Still works. So now you know how to set a particular cursor location on any part of the display. Let's talk about analog to digital conversion, or ADC. Analog to digital conversion is where the microcontroller will take an analog signal or an analog voltage, specifically in the form of a waveform over time. So this would be time, and this would be voltage, let's say 0 to 3.3. And you have a device that outputs some kind of voltage over time. So you can take the output of this device that is showing a voltage. Over here it's 0 volts, and over here it's 3.3 volts. You can take that voltage and you convert that to a number that you can use in computation. And you have to think of it in a way that something that you want to sense, like something in the environment, will most likely give you an output in a voltage, and in a voltage between two specific reference voltages from 0 to, let's say, 3.3 volts. So let's say this is 60 degrees here, and this is 70 degrees. This would be the voltage at 60 degrees here, and this would be the voltage at 70 degrees. It means that the voltage here, this would be around 2 volts, and this would be around 2.3 volts. Microcontroller is not going to take a voltage and then give you 60 degrees unless you create a computation for that. It's going to give you an output of 0 to, if it's an 8-bit number, 255. And if it's a 10-bit number, this would be 0 to 1024. In the 8-bit case, this 60 degrees would be around 153, and the 70 degrees would be around 179. So you could take this number, or these numbers, and use them in some kind of computation that would yield the actual temperature, or whatever you would need to do with that particular number at that temperature. You don't really need to convert it to a temperature if you're really going to use it in some other kind of computation. So you can have the microcontroller constantly reading what this temperature value is, or whatever this device is reading from the environment. And this will happen through time. So when you turn your microcontroller on, you can start reading the signals here from the analog device. And it'll start out at 0, and then these would be like 8-bit numbers here.
And then you'd have another one here. That would be around, let's say, 102 in 8-bit number. I'm basing this on about 40% or 0.4, 40% of the 3.3 volts, which is about 1.32. So I'm just taking 3.3 and multiplying it by 0.4. Or you can also take the 255 and multiply that by 0.4, which is 102. And then you can get the next conversion here, and that would be somewhere in between 153 and 179, let's say 165. And then here, so it'll keep doing these conversions. And I'm showing it to you in this way because a conversion happens between two periods of a time frame. And this is important because the ADC, the analog to digital converter, needs to be connected to a clock source in your microcontroller. And that clock source has to be pre-scaled or scaled in a way that it allows time for a conversion to happen. There could be a whole bunch of clock cycles between this, but it needs those clock cycles to do one conversion. I believe that number is 17 microseconds, which is what I'm going to start doing in the beginning programs. Is I'm going to use about 17 microseconds, which is actually a long period of time and is one of the periods of times you can use in the analog to digital converter. So what can you use analog to digital conversion for? Some of the applications I can think of are sensing, which are generally environmental sensing or sensing things from the environment. And that could be temperature. It could be tilt from an accelerometer. It could be angular velocity or the speed at which something is tilting. And that would be from like a gyroscope. This temperature would be obviously from something like a thermistor or a thermocouple. It could be used for sensing distances, either through laser or sonar, radar, or infrared. You could even use it for controlling, like with a potentiometer. When you turn the knob of a potentiometer, the voltage goes up or down, and you can take that number and you can apply it in various different ways. Maybe controlling a menu system or controlling the volume of some audio output. You could also use it for recording audio, which is probably in the sensing application or sensing category, because that would be a microphone. You can convert these analog variations to a set of numbers for each point. Each of these points could be a number that is stored as a digital recording of audio. The list of these applications go on and on. There really is an endless list of how you can apply analog to digital conversion. With the microcontroller that we're using, there are 16 channels of analog to digital converter pins that are located along the microcontroller. And there's also one channel within the microcontroller that actually has a temperature sensor. And then there's another channel for voltage reference. And this is a voltage reference that is absolutely accurate. It is a band gap voltage reference, which means that it's a constant voltage reference no matter how much variability you're having in your supply, in your power supply to supply the microcontroller. And this is important because the voltage reference must be very accurate to be able to give you a good reading constantly on a analog to digital conversion. You might notice that I use the word channels. Channels is the way you would specify the analog to digital controller's separation from one analog device to another. Pin 15, for instance, is the ADC in1, which is considered channel 1. And pin number 16 is ADC in 2. And being that these are channels and not just regular input pins, you cannot have a conversion on the number 1 at the same time you're doing a conversion on number 2. This has to happen one after another. And let's say we have an analog signal coming into 2 and into 1, and you want to read both of those and use both of those numbers in some kind of computation. There is a thing called scan direction, and it will do either this one first and then this one second, depending on how you program and how you set up your channel register. Number 17 is ADC in 3. Number 20 is ADC in 4. Number 21 is ADC in 5. Number 22 is ADC in 6. Number 23 is ADC in 7. Number 26 is ADC in 8. Number 27 is ADC in 9. All the way to number 8 is ADC in
10. And these are the alternate functions, by the way, of these pins. These pins are used for general purpose input-output, but they can also be used for the analog to digital converter. And pin number 9 is ADC 11, and pin number 10 is ADC in 12, and pin number 11 is ADC in 13, and pin number 24 all the way back over here is ADC input number 14. And number 25 is ADC in number 15. It looks like we only have 15 inputs or 15 channels. And the ADC number 16, I'm just going to write it over here somewhere, is the internal temperature sensor. And the ADC number 17 is the VREF. Now you know how the microcontroller is set up and what input pins you can use for inputting voltages between certain voltage minimums and maximums, or what steps do you need to take in programming analog to digital conversion. There are certain steps you have to take to actually set up the analog to digital converter to start doing the conversions, and then the actual conversions themselves. So let's see what those steps are. The first one is called calibration. And what this does is each microcontroller that is put out in the factory is calibrated to in a certain way. It has a specific setup that when the calibration is done in the analog to digital conversion setup, it calibrates according to what is set up in the factory for that particular chip. So when you do the calibration, it calibrates the voltage reference and the converter so that it's going to have a repeatable reading every time, meaning that a particular temperature will give you a specific number and it'll always be that number every single time. And then you have connecting the ADC with a clock. And the clock source for the ADC is the HSI 14. And we'll get more into this later on as we program it. The next step is to enable the ADC. And then the last step, you establish the conversion, where you set up the channels, specify the scan direction, establish the start of the conversion, and then you can grab the data. And the conversion can be in an 8-bit number, a 10-bit number, or a 12-bit number. The resolution, which is the 8, 10, or 12 bits, can be dependent on the actual application, whether the sensor or whatever you're controlling requires that amount of resolution, or if it even can give you that amount of resolution, where the analog doesn't really need that much resolution because maybe it's controlling sprinklers or something like that, or if it requires a lot of resolution where it may be connected to some kind of safety application or a mission critical application. Now you should know a little bit about analog to digital conversion. In the next video, we'll take a look at how to set up the circuit, which is extremely easy, and we'll start getting into the programming. For our first circuit, we're going to be using the internal temperature sensor. So we don't actually have to plug in anything to any of the ADC ports. We're going to be using channel 16, which is the temperature sensor. But first we need to provide power to the analog power supply and the analog ground. So we'll connect pin number 12 to the minus rail or the ground rail. And we'll connect pin number 13 to the plus rail. So I'll have number 13 plugged into the positive rail and number 12 plugged into the negative rail. Let's go ahead and create a new project. I'm going to call this ADC tutorial. Okay, I'm going to make some pseudocode that I can use to tell me what I need to actually program. So we're going to do an ADC calibration. And then I'm going to select a clock source for the ADC. I need to enable the ADC. And then start the conversion. I think I want to put the conversion within the while loop because I want it to convert continuously. All right, let's start with the calibration. In calibrating the ADC, we want to make sure that the ADC is not enabled. And we can do that by looking at the register ADC1 and the control register for that, which is CR. This is the control register for the ADC. And we want to make sure that there's a 0 in the ADEN portion of that register. So we're going to use the AND equals and then the NOT. And we're looking for the ADEN bit from the register. So this should make sure that the ADEN or the enable is 0 or off. So now we can start doing the calibration. Calibrating it, we're going to go back to the control register. We want to write a 1 in the ADCal bit of that register. To make sure that the calibration is complete,
we have to wait until there is a 0 on this bit. When we turn this to 1, we're actually telling the microcontroller to do the calibration by itself or automatically. And when it's done calibrating, it will make this part of the register, this bit, a 0. So we need to wait until this is a 0 before we can go on and do any other processes. So the way to do that is we're going to use a while loop, and we're going to wait until that bit is a 0, and it's under the CR register. And to test it, like you've seen in my previous videos, we would use the AND here, and we would test it with this particular bit. While the bit here is not equal to 0, it'll continually run, and then when it finally hits 0, it'll jump out of that while loop. If you take a look at the control register for the ADC, you'll notice that the ADCal bit is on the 32nd position. So if you had the control register is equal to, let's say, 1, and then you have 31 more zeros, that would be the 32nd position here. And the ADCal is 1. So this actually is the number for ADCal. You can see that it's a 0x8 and then the rest zeros. That's actually that number in binary, because it's at this position. So if the actual control register looks something like this, then because of this and this would be here, and the control register is here. So this and this, it's only looking at this particular position, the first position here, or the 32nd position here, and the 32nd position here. And that shows it would be false or 0, because 1 and 0 is equal to 0. But if there was a 1 in this position, because in that particular binary number for here, which is this and this would equal 1, because it's only looking at this position here. So this and this is equal to 1. The ADCal would be the mask. So this is the mask. So we're testing it to make sure that if it is not equal to 0, if it is a 1, because we put a 1 in it, we're going to wait until the microcontroller puts a 0 back into this bit to tell us that it's completed calibration. And we don't actually know when this is going to happen, or if it's going to happen. So what if it actually gets stuck here? We don't actually know if we put a 1 here and it stays a 1 forever. We won't even know if the microcontroller is working or not. We can't really test that. So let's go ahead and put something on our LCD that tells us that it's working on the calibration. So let's first set our cursor position. And we'll start with 0, 0 position up at the top left. And then we'll send a string to that location. And we'll call it start AD calibration. When it prints that out and then it does the next thing, it'll erase whatever was there. You know what? I need to give me a time delay as well. We'll put about 500,000. 500,000 should be enough time to see that we have this string on the LCD. So let's put at the end of that string, or at the end of this process, ADCal success. So when it gets out of this while loop, we know that there was a success in performing the calibration. If you just see the microcontroller say start ADCal and then it just stays there for forever, you know that it didn't get past this while loop, and we can start to debug that portion of the program. I'm going to separate this a little bit. And this is a lot of lines of code. Let's make something in the LCD functions that does this a little bit easier. I think I did something actually in previous. Yeah, I think I did this one here. Delay, string for character line 1 and string for character line 2. So let's go ahead and do that one. Let's use that instead of all of these lines. LCD send 2 lines. There we go. So the first one is here, first line, and then the second line is just really nothing. We don't need anything on the second line. Although on the next one, I can do that on the second line, success, when I need to specify a delay here too. So when it runs, it'll show start ADCal, but nothing will be on the second line. And on the next, after it completes this, it'll show ADCal success. Okay, so let's take a look at selecting a clock source. We first need to go to the the APB peripheral clock enable register number 2, which is this one we're going to call in our code. And in that register, we have a bit that is ADCEN, or analog to digital converter enable. It's bit number 9, and it shows in the description that this is the ADC interface clock enable. So we need to first enable the clock for the analog to digital converter. So let's do that first. And we want to write a 1 in that bit. Now I'm going to use the ADC1EN since we're using the ADC1 control register here. The next thing we need to do is to start the HSI14 RC oscillator within the chip. We have to select an actual clock source for the ADC, and the control register here has clock sources and has a clock source called the HSI14, and this is where you're controlling that particular clock source. The one clock source that the ADC uses specifically is the HSI14, and this is the bit we need to use to turn it on. We're going to enable the HSI14 clock. Once we enable it, the clock source will become live for our ADC to be able to use. RCC CR2. So let's go ahead and type that in. And we'll need to write a 1 in that register as well. And if you notice that there was a few other parts of that register that has a ready, and we can use this HSI14 ready to test to see if the clock has been enabled and is ready to function. So let's go ahead and write a while loop to make sure that there is a 1 written automatically into this bit by the microcontroller, because the microcontroller, when the clock source has been started, the ready bit will be written a 1 automatically by the microcontroller. So let's go ahead and create a while loop for that. And we're going to use the AND. We're going to use the RCC, the same CR2, and then the HSI, the ready bit. And we're going to make sure that we keep the while loop going while it's equal to 0. And when it becomes a 1, it'll escape out of this while loop. This is kind of the opposite of what happened in the calibration, because we wanted to make sure that the calibration, when we wrote a 1 to it, the microcontroller automatically wrote a 0 to it when it's been calibrated. We want to make sure we keep this while loop going until there is a 1 in this bit. So let's use our LCD. Okay, so we're going to start clock. And over here, we're going to say clock started. We haven't actually finished with the clock yet because we still have to connect the ADC to that clock, to the HSI14 clock. And to do this, we need to use another control register, which is called the configuration number 2 register. You'll see that there is a CK mode, and you have 3 choices, but we're going to be using the synchronous clock selection. Let's take a look at what selections we get when we type that in. So we're going to set it to 1, the CK mode. So let's see what we get. So we get the CK mode 0, and CK mode 1. Let's see what CK mode gives us. And that is C. Let's see what that is. Control C. We have this number, and it looks like it's both 1s. So just by putting CK mode, we would actually invoke this selection, which is actually what I had in my test code, and it worked. So maybe I can try different ones and see what happens. So now we're finished with starting the clock. Now let's go on to enabling the ADC. Enabling the ADC is very similar to actually the starting up the clock. We have an enable and we have an enable ready. So we can test for a ready bit. So let's go ahead and go to the control register for the ADC. That's where the enable is located. And we know this because we used it up here. But now we're going to do the reverse of this. We're going to actually turn it on. So we're going to put a 1 in that bit. And to test to make sure that the ADEN is in fact ready and ready to do a conversion or start doing a conversion, we can go ahead and test that to make sure the ready bit has been set. So we're looking for the ready bit, ADRDY, and that is in the ISR register, ISR ADRDY. And that needs to be equal to 1. So this is going to have a while loop while it is 0, and when it is 1, it'll get out of that while loop. So now we're turning it on, and we're waiting for it to get ready. So let's go ahead and put our LCD in there as well to inform us if it is ready or not. So enable ADC, and then call it ADC enabled. We want to make sure that we provide enough time for the ADC to do its sampling. The way to do this is to go into the ADC sampling time register, the ADC SMPR. And we're going to be adjusting these bits here at 0, 1, and 2. And in this demonstration, I'm going to be using the slowest sampling time. So it gives us the most sampling time possible to do the conversions. So we're going to have to place 1, 1, 1 in the 0, 1, and 2 bits of the SMPR register for the ADC. So to access the SMPR register, we're going to our ADC1 and the SMPR register. And we're going to use the OR equals to write ones in the 0, 1, and 2. We could just put in a binary number to put ones in those positions from 0 to 2. But of course, there are macros already defined for us in the header file for the microcontroller. So we'll just use those. So we're turning on bits 0, 1, and 2, the SMP sample bits. Now we need to set the channel for the ADC, and this is the internal temperature sensor, the channel select register. And the one we want is number 16, because number 16 is the channel for the internal temperature sensor. But this is not the only thing we have to do. We still have to wake up the internal temperature sensor, and that has its own bit. And the ADC in the CCR register has a bit called TSEN, and that will tell the microcontroller to start the temperature sensor. Now the next line of code, I'm not sure if I really actually need it, but in the documentation it says to use this if you're using the temperature sensor. And it's the voltage reference, or VREF, and it's also under the CCR register. And you'll see that VREF enable is here. We are finally at a point where we can start converting. To do this, we need to start the ADC. So we're going to go to the ADC1 control register, and we're going to write a 1 to the AD start bit, AD start. And we need to make sure that the conversion has been completed. When we actually write a 1 to the AD start, it's going to start converting. And we need to allow the microcontroller to wait until it has completed that conversion. So we're going to create another while loop. And within this while loop, the condition is going to be in the ISR register. ADC1 and the ISR register is the interrupt and status register. Status is the key here. As we looked in the ISR register up here, we looked at the status of the ADC being ready. We're also going to look at the status of the conversion being complete. And that bit in the status register is the EOC bit, which means end of conversion. So when the end of conversion flag has been set, then we know the conversion is complete, and we can go ahead and grab the data. So let's keep this while going while it's 0, and then exit the while when it's 1. So where in this microcontroller is this data hiding? If you take a look at the data register for the ADC, you'll notice that from bits 0 all the way to bit 15, which is 16 bits, is available. The resolution has a maximum of 12 bits, so even though it's reserved for 16 bits, you're only going to be able to see 12 of those bits. But they use the 16 bits because you can actually left align or right align the numbers within these bits. And to do that, you can use the configuration register 1 for the ADC and select these bits. I'm not going to do that in this particular demonstration, but it's available to you if you find the need to do that. So we have the possibility of storing that data in some variable or just printing it to the LCD. That's what I'm going to do. I'm going to set the cursor location on the line 2, or the second line, and I'm going to send an integer to the LCD, and this is where I'm sending the data. And I'm going to give it 7 characters for the length. I would like to put somewhere here on the LCD that the conversion has started, or showing that there is some kind of label showing that this is a temperature sensor. So on the first line, you will see temperature sensor, and then on the next line, you should see the data. Let's build it and see if it actually works. Looks like we have some errors here. Let's see what we did wrong. I used ACD, not ADC here. So all the way up here, the first thing I did. Looks like we do have one more error. Too many arguments. Should be integer here. Okay, I flashed the microcontroller, but I noticed that it was just giving me a blank screen. The reason why it did that is because I didn't put in these 2 lines of code to initialize the LCD and set up the LCD display. Okay, the microcontroller is flashed and you can see it's working, and it went through all of the initial verifications and validations. Let's take a look at that again. Okay, so it's starting the calibration, started the clock, enabled the ADC, and now it's reading the temperature sensor. And you can see that it has a value of 1743 to 45, 46. I'm going to put my finger on top of the microcontroller to see if it changes. I'm putting my finger on it, and it looks like it went down to in the teens. Now, the 1712 doesn't really mean much in temperature, and I have to check to see if this is a valid 12-bit number, but we definitely know that it's more than 1024, so it's more than a 10-bit number. So in their reference manual, they actually have some code examples at the end of their manual. They show you a temperature computation code example, but in the documentation, they'll actually show you a formula to compute the temperature in degrees. And this is what this is supposed to be doing as well. So let's take a look at that other formula. And this is the formula that they say, calculate the actual temperature using the following formula. And this is the data that we're given. And it says to divide that by 4095, but we're multiplying it by the 3.3, or not sure what this actual number is, if it's the 3.3 or if it's the digital form of that number. We're taking that V-sense we've just calculated and we're plugging it into this formula. And then we're using the average slope, which is the actual temperature degree change between the voltage references of 30 degrees and 100 degrees, but they don't tell you that here. And you add 30 degrees Celsius to it because that's what is computed at a particular calibration from the factory. So let's go back to the code example, and you'll notice that there are a couple lines here, defines, and these are calibrated. They actually store the calibrated temperature at 30 degrees and at 110 degrees. So they actually put a number and they store it in the microcontroller at the factory, because every microcontroller is different in its calibration. You can use this in calculating the actual temperature. So we have the low and we have the high, and we can determine the average slope from these two numbers, computing it. And I think that's what they're attempting to do here. I could not get it to work successfully, but let's figure out how to get it to work for real. And we'll use the standard slope-intercept formula. So we're going to look up this number right here, Control C, and we're going to go back. And really, this is just for your information, because you really don't need to go to this data sheet to find this information, but it does give you a good, handy data sheet to maybe find other things that you might find that are very helpful or important. So you can see it says TS-Cal1. That's this temperature sensor, calibration 1. And there would be a calibration 2, but they don't list it in this data sheet, unfortunately. But it shows that the TS ADC raw data acquired at a temperature of 30 degrees Celsius. And here's the key. To improve the accuracy of the temperature sensor measurement, each device, microcontroller, is individually factory calibrated by ST. The temperature sensor factory calibration data are stored by ST in the system memory area, which is here, accessible in read-only mode, so you can't change it, obviously. And notice that they don't give you the other calibration. This one is the one for 30 degrees, but they're not providing you with the calibration for the 110 degrees. And I'm thinking, well, maybe this is an error in their data sheets, or maybe they only provide one bit of information for this particular line of microcontrollers. I looked in other data sheets and I did see both of them in there. And I did do some testing before recording this particular video, and I did notice that both of these values are in fact located in the microcontroller. And they would really have to be, because you need 2 points of reference to be able to find out a range and to be able to determine an average slope for use in a slope-intercept formula. So let's first take a look and see what these two values are. You'll see that in this program, they're using a pointer, and all they're doing is they're giving you access to that memory address. And the way they're getting the value in that memory address is they're using the pointer asterisk symbol to do that. Since the number is only a 12-bit number, probably, they're casting it as a 16-bit number. They don't really need the 32-bit number of that memory address, because the 16-bit number is sufficient, and it's probably right aligned within that memory address anyway. So let's plug these defines into the program and see if we can access those numbers and see what they are. So let's go ahead and put it on the top of the program, and I'm going to take out these LCD lines because I only use these for debugging, and we really don't need these anymore because I know that they work. In fact, I noticed that this needs to be right next to the enabling. So right when we enable it, we need to turn it on. 1. So these two things should be happening at the same time. And in here, I want to show some information here. So I'm going to just say temp. I'm going to show this number right after temp. So it's going to be on the 0y, and then x, it's going to be 5. So let's put it at the 5th position. Or I'd like to put a colon instead. And I'm just going to put an x, because it's going to be a 4-digit number. I'll put this to 4. And over here, and this XXXX will disappear once the number takes its place anyway. So that's a good way to sort of reserve certain portions of the screen. So I'm going to put the 30 degree calibrated value, and that will have 4 numbers there. And then the one that was calibrated at 110. 1, 2, 3, 4. Exactly 16 characters. So let's take a look at this here. We're going to use this address and put it in another location. So this one is the 110. Let's start with the 30. So the 30 would be, we put the pointer symbol before that. So we're looking at the contents of the address, not the address itself. And we want this to be on the second line. And let's see which 1, 2, 3, 4 or 0, 0, 1, 2, 3. So 3. And then the next one will be the 110 calibrated value. And this will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12th position on the second line. Let's take a look and see if we have a good compile. Okay, so we got a warning here. I had this in there when I was doing my research, so we don't really need that yet. Let's go ahead and do this again. Okay, no errors. So let's go ahead and flash the microcontroller and see what happens. Okay, success. So you can see that the digital voltage value is at 30 degrees is 1764, and at 110, it's at 1336. So, and we can see that our temperature is lying around 1728. So you can tell that it's closer to the 30 than it is 110, obviously, because it's not very hot in here. The chip isn't giving off any significant heat. Since this is probably going to be a linear relationship between the 30 degrees and 110 degrees and the 1764 and 1336, it should be a straight line between those 2 points. So let's see if we can draw something up and see if we can figure out this formula. Okay, so the slope intercept formula is y is equal to mx plus b. Okay, b is going to be an offset. The m is the actual slope itself. M is equal to the slope, which is equal to the rise over run, which is also equal to the delta y over the delta x. And all that means is 2 y positions and 2 x positions. So you have a line that has, a line is always going to have 2 points, and they're going to have 2 y's and 2 x's, or xy and then xy. So let's go ahead and take a look at a little graph. We should probably draw a graph and kind of understand what we're doing here. So let's say that this is temperature on this, and on the y-axis, and the x-axis will be the digital voltage values. Okay, so let's take a look at the different values. Let's say that this is the 30 degree mark, and this is the 110 degree mark. And you're going to find this very interesting here, because you'd think that in the temperature sensing, you'd have the high value as the 110, but really it's the low value. So right here was, what was the number? Okay, it's 1336. That's the 110. So if you draw a line, we have our first point here, and then the other extreme is the 1764, which is our 30 degree mark. So we could actually just draw a line from here to here, and somewhere along this line is our actual temperature digital value. And you know it was somewhere around 1728 of 1727. So let's just say that's somewhere around here. So where that meets here, that would be where that temperature is. We don't know what that temperature is, but we're going to figure that out. We're using the slope-intercept formula. So let's find out what the slope is first. So first we're going to take the difference of the y values, and the y values in this case is the temperature. So it's the difference in the temperature. So the difference in temperature is equal to 110 minus 30. This was correct in the data sheet. So this value would be 80, right? So we have our delta y. So our delta x is equal to the delta of it's actually the V30 minus the let's just call these voltages. The delta of the voltages, which is equal to the V30, which is this one right here, and this would be V110. Okay, so the answer to that would be 1764 minus the 1336, and that would be equal to 428. So then our slope will be equal to 80 over 428, which is equal to, I'm actually going to flip this this around because I want to have a value more in line with the specifications in the data sheets, which is around 4.3. And that just means that I'm making this part the temperature. I'm just going to put that on the x-axis, and then the digital voltage would be on the y-axis. And that's just essentially me just rotating the graph around 90 degrees. So I'm going to make it 428 divided by 80, and that's going to be equal to 5.35. So for each degree of temperature between 30 and 110, there is a change of 5.35. If we divided it, this particular axis, and each one of these is 5.35 width apart, and that would be each degree on that scale. So now you know we can take the 1764 number right here and the actual data that we're getting from the temperature, and we can get the difference between 1764 and that temperature reading and determine what degree it is. Because we have the number of degrees, we can divide that by 5.35. Another way to think about this is we're going over 5.35 and we're going up 1 degree. Going over 5.35 and we're going up 1 degree. If we did this the other way, like 80 over 428, let's see what that would equal. We get a value of 0.1869. So for each change in this number here, like this between 1764 and 1763, that would be 0.1869 degrees. That might actually be a little bit easier to determine. And the reason why I'm trying to figure this out is because I'd have to do extra work to find out where this crosses the axis and where this one crosses the axis. Because we need to know where those cross the axis for the slope-intercept formula. And we really don't need to know that because we have what is a particular degree. So let's say we take the 1764 and subtract it with the 1727. So let's see what we get. So that would be 7, 14. So that would be 37 point difference. So if I multiplied 37 by 0.1869, that would equal the number, the amount of degrees Celsius. And that would equal 6.9153 degrees difference between the 1764 and the 1727. So if the 1764 is 30 degrees, and we added the 6.91, so let's plus 30 degrees to this, so that would be 36.9153 degrees. And that sounds like a reasonable temperature for my microcontroller within its environment. So I think at this point we have enough information to write our code. So first let's see if we can calculate a slope. We don't actually have to do that within our while loop. Our slope is always going to be set no matter what. That doesn't have to be recalculated over and over again. So let's find out our slope, and we're going to make this a float, and we'll call it slope. In fact, the data sheet calls it average slope, so we'll call it, I think it's called average slope. No, I'm just going to call it slope. So this is going to be equal to the difference in temperature, which is going to be 80. And then we're going to divide that by the difference between the voltage at 30 and the voltage at 110. And we're going to subtract that with the 110. So this should be our slope. Let's go ahead and see if we get the correct number. I'm going to go ahead and just delete all this, and we'll call it slope. So we're going to take one of these out since we don't need those numbers. We're going to change this to a 10. And we're going to display our slope, but we need to do it with a float. We're just going to do this as a new line. Floating point number. So this is going to be slope, and it's going to be 10 characters. And let's see what 6, position number 6 on the second line. Okay, so let's see what our slope is. Hopefully we did it right. We don't have to keep showing this either because it's always going to be a constant. So we'll just show it from up here. And this has to be inside the while loop because it's always grabbing the data from the controller. And I believe when I'm dividing two numbers, I have to be very explicit with my casts, meaning that I have to sort of declare what this number is going to be, and I have to declare what this number is going to be. And in this case, I'm going to declare them as a float. So what I'm essentially doing is I'm telling the compiler what this number is going to be, and it's going to be a float, even though it really isn't going to be a float, but I want it to be a float because it's going to end up being a float anyway. So I want to keep all of the casts consistent, and this one also will be a float, even though it's just the number 80. So let's go ahead and try this and see if it works. And you can see that it does work. I can take away all these X's on the display. Okay, so now that we have our number, we have our slope, we can go ahead and calculate the final number. Because all we're going to be doing is taking our slope and we're going to multiply the difference. So we have our slope here. We can use it over here at least. we'll call it temperature. And that's going to be equal to the slope times the difference between our calibrated 30-degree temperature digital value. And we're going to subtract the ADC value of the temperature. So that's going to give the difference between from 30 degrees to the value of what the temperature is right now. So we're just finding what's the difference between those two, and we're multiplying the slope to find out what the degree difference is. So then what we can do is we can add 30 to this. Go ahead and make sure that order of operations are done correctly, because I want this slope to be multiplied by the difference here first, and then 30 is added to the end. So let's go ahead and see if we get the correct temperature. And we're going to want the floating point number here instead. So we're going to be displaying a floating point number, and let's go ahead and give it 10 digits as well. So let's see what happens. No errors. Go ahead and flash microcontroller. We should have around 36 degrees, and that's good. Looks like it works. Let's take a look at how we can look at an external voltage connected to a pin of the microcontroller. We might want to measure some kind of voltage coming into the microcontroller, voltage using a potentiometer, where we can take a potentiometer and use it as a voltage divider to bring in different levels of voltage between 0 voltage, which is ground, and to VCC, which is the 3.3 volts. So we're going to use this potentiometer to vary the voltage between those two ranges. On the microcontroller, generally the ADC is in this area. The voltage for the ADC is located here on these pins. Then the following pins in this location are where the input pins are for the analog to digital converter. When you turn the potentiometer, the wiper will either be on the top of the resistors or the wiper will be on the bottom of the resistors. What this is doing is it's changing the values of these resistors when you move the wiper. So in this scenario, you'd have the two resistors looking like this. And in this scenario, you would have a little bit of a resistor on the top, and then you'd have a lot of resistance on the bottom. So you have a large resistor top, small resistor on the bottom, and in this scenario you'd have a small resistor on the top and a large resistor on the bottom. And if the wiper is in the middle, like in this case, you'd have an even number of resistors in this voltage divider. You can use the Ohm's law formula to solve for this, but instead of going through all of the formula to figure this out, I'm just going to give you the voltage out is equal to the source voltage, which is 3.3 volts. And then you'll have there's two resistors in this scenario. There would be R1 and there would be R2. So to get the voltage output from in between those resistors, you have the R1 on top and the R1 plus the R2. So let's say that the R1 is equal to 0.5, like the wiper is near the top. We have 0.5 here, and I'm not using I'm just gonna say 0.5 ohms just to make this simple. And on the bottom we would have, let's say, 5 ohms. So we have half of an ohm resistance on the top here, and then you have 5 ohms resistance on the bottom, and that works out to 0.3 volts. Now let's look at a scenario where the wiper is on the lower end. So let's say we're using 3.3 volts, and the R1 would be the larger one, which would be, let's say, 5 ohms. And on the bottom, you'd have 5 ohms plus 0.5 ohms. And that works out to 3 volts. So you can see that is lower, and there's higher resistance on the top, but lower resistance on the bottom, that you have a higher voltage, closer to the maximum voltage you have on the circuit. You can never actually go over the amount of voltage you have. You can only go between the 3.3 volts and the 0 volts. Let's take a look at what pin we can use for the analog to digital converter. You can see that those pins are here. We've already set these up. We have the power going to the power rails, which is the VDD and the VSS. I forgot to put this one in. This is ADC IN0. And I'm going to use this pin here, the IN1. The IN0 is really close to my power pins, and on the breadboard it's very difficult to get the potentiometer in that location. So I'm going to use the IN1. And at the IN1, we'll have that connected to the wiper, and we'll have the resistor, potentiometer, one end going to ground, and the other end going to 3.3 volts, the power rail, or VCC. The IN1 is pin number 15. So I'm going to take the potentiometer and plug it in right at that location. I'm going to directly connect these pins here to the power rail. But you might want to use a resistor just in case you go to one end. The wiper pin is actually on the back
at this location, which is on the same tie strip as number 15. So I'll just take, it doesn't really matter which pin I go to, what ground or VCC, just as long as they're the opposite. I'll take one pin and go to positive, and I'll take the other pin and go to negative. The programming for this is really simple because we've already created the code that we need to do this measurement. And all we're going to do is we're going to remove any of the temperature sensing code that we have in here. We won't need those anymore. This is actually the temperature sensor, the ADC channel that it uses. We're going to change that to channel 1. IN1 matches with channel 1 for the pin number 15. We won't need the VREF either. I'm just going to comment that one out because we may need that one at another time. And I'm going to remove the slope and the temperature. Let's see, maybe I can change it to something else. I'll call it POTS, or pot reading, potentiometer reading. And this one I'll just keep it blank. So we want the actual number to be in this location here. I can put a space after that since I have some room. We're not going to need this slope formula anymore, and we won't need to be specifying it on the LCD either. We won't need the temperature computation. So we'll put this is at this is X5, let's see. So we're going to put the sixth position here. And we actually need instead of temperature, we need the ADC DR data register. So we're just going to put the data register reading directly onto the LCD, which is the reading from the pin number 15, the IN1. I don't see anything else I need to change. Let's go ahead and compile the code and see if we have any errors. Build failed. So it looks like I took something out maybe. Oh, I'm not using ADC, I'm using ADC1. We need to change that. Let's do it again. Okay, the build was successful. So the microcontroller has been flashed. It looks like I was off a little bit on you can still see an X there, but we can still take a look at the results. I'm going to use a screwdriver in the potentiometer and I'm going to turn it up. We can see that the number is climbing, and you can see that there's the decimal and the zeros, and that's because I use the LCD float, send a float, not send an integer. Let's see how high I can go. I don't want to go all the way. I might have gone there. So I got a 3830 something reading. So if I go all the way down, I should go down to almost 0. I don't want to go all the way to 0. I went to 0. Okay, let's take a look. Let's get a closer look at this. Okay, you can see that the number is there. So I'm turning the potentiometer. I'm barely touching the potentiometer. I'm just wiggling the screwdriver. Makes it move quite a bit. And it looks pretty stable, actually. So you can see we got all the way to 4043 or something like that. 4040 something. And then all the way down to 0. So let's take a look at what a 4040 would be in a binary number and see what bit resolution we're getting. Let's take a look at the decimal to binary converter, and we can see that 4040 is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. So we do have 12 bits of resolution. Let's do the reverse. Let's see. Let's take a look at a binary number with 12 ones and see what that number is. So that's 4095. So we were pretty close to 4095. And there's going to be a little bit of resistance at some point in the voltage divider. Even the wires produce resistance. So I think we had a pretty successful attempt at using the analog to digital converter from one of the input pins. I'm going to demonstrate the use of timers and counters. In many cases, when working with microcontrollers, you'll need to use counters. And counters are connected directly to the clock source of the microcontroller. The microcontroller has an oscillator that's built in. And in this specific microcontroller, the default oscillation is at 8 megahertz, which is 8 million pulses per second. If you've been watching the LCD series, you know that there's already a place where I needed to use a counter because I had a time delay that was built in so the LCD would be able to wait long enough, or actually the microcontroller was able to wait long enough for the LCD to do whatever it needed to do to end its busy state. But we simply used a loop just to make it pause for a certain time frame. But that time frame was very inexact. It was not exactly what the datasheet called for. So in those cases, you might want to use the timers and counters because they're based on a specific
value of oscillation within the microcontroller. If the datasheet calls for a pause for 100 microseconds, then you'd be able to specify 100 microseconds as a pause. We'll be getting into just basic counting with a prescaler. We'll be getting into input capture, which is bringing in a pulse and measuring the width of the pulse. We'll get into measuring the widths of the PWM signal coming in, and we can also output a PWM signal with specific periods and duty cycles. So let's go ahead and start with the first feature. I'm going to simply create a program that all it does is it counts to the maximum value that it has. And I'm going to change the prescaler to different values to see what actually happens with the speed at which this counts. When you're counting, you can count with a prescaler. The prescaler, all it does is it skips a specified number of oscillations in the internal CPU, because the oscillations, you're oscillating at 8 million times per second, and that's a lot. And you might not want to count at that same speed. You might want to slow it down. So we can skip some of those oscillations and have it count, let's say for every 1,000 internal oscillations, it counts 1, and then another 1,000 internal oscillations, and it gets to number 2. 1,000 oscillations gets to number 3. In this specific demonstration I'm showing you here, the prescaler is at 1,000, and you can see how fast it is counting up to 65,535, which is the maximum amount, or the maximum for a 16-bit binary number. The counter register that holds this number is only a 16-bit register. So let's go ahead and include the LCD functions. .h. When we're using the LCD, it's to initialize, and we're going to set up the display. Now we're ready to use the LCD. In this program, we're going to use the timer 1, TIM1. So the first thing we need to make sure is that the advanced peripheral bus has the timer enabled. And within that register, you'll see that we have some of the timers enable switches. The one we're going to be using is time1 enable, which is bit number 11. And the time1 is the advanced control timer. And the advanced control timer and the general timers are very similar, but we'll get into more of that later on. So let's go ahead and click on that, and you'll see that in the timer 1, advanced control timer is a 16-bit auto reload counter, and it allows you to use a programmable prescaler. And generally, most of the timers are very similar, and we'll get more into what the differences are later in these tutorials. But let's start off really simple and just use a counter and prescaler. So first we need to enable this timer. So we're using the clock control register and the APB2ENR. We're going to make sure we enable the time1, the timer 1 enable. With a timer, you have a register that holds the actual counter number, and that is called the TIMXCNT for counter. And the X can be replaced with the actual timer number. And in this case, we're using timer 1. With a prescaler of 0 or no prescaler, the oscillator would look like this. The microcontroller is constantly creating a pulse, and these pulses happen 8 million times per second. So for each pulse, the counter with no prescaler, the actual counter register will have 0, 1, 2, 3, 4, 5, all the way to 65,535, which is 65,536 positions. And this conforms to a 16-bit binary number. However, when we're counting up and trying to show this counter on the LCD, it's going to go by so fast that you won't be able to see the numbers. In fact, it'll probably count up to 65,535 more than 100 times before it actually gets to the 8 million in 1 second. So that's where the prescaler comes in. So if we said the prescaler, we're going to shorten this to PSC, and that allows us to skip some of these oscillations. So let's say the prescaler is equal to 2. The prescaler has its own little counter, and it starts with 0, 1, and 2, 0, 1, and 2. So every time that it gets to 2, the counter will change. So in this scenario, with the prescaler at 2, the counter will have 0 here, and then 1 here. Let's go on just a little bit more. So the counter will count on every third pulse. So you have 3 pulses because it starts at indexed at 0, 1, 2, and starts again 0,
1, 2, and it'll count for every 3 pulses of the oscillator. In the example that I showed in the introduction I had the prescaler at 1000, so it'll actually skip 1000 of these oscillations before it gets to the next counter number. The oscillations stay at a constant speed, it's 8 million oscillations per second, but by skipping 1000 of them, that means you have a lot more time between the counts. Prescalers are sometimes difficult to understand when it's being written in a data sheet. But really, if you think about it, prescalers are very, very simple. In a lot of features of microcontrollers, not necessarily this particular microcontroller, the prescaler is only allowed to be a specific number like 2, 4, 8, 16. It really confuses a programmer, but it really doesn't need to. I mean, it's as simple as just skipping oscillations. So let's get back to the program. So the next thing we need to do is set up the prescaler. To access the prescale register, we're just going to use time 1. That's going to be our main register for our advanced control timer. And the PSC is the prescaler register. And we're just going to make it equal to whatever number we want. And in this case, we'll make it equal to, I'm going to make it 10,000 this time. So it'll show a little bit slower on the LCD. And inside the loop, we'll access the timer 1, the CNT register. And all that does is it stores the actual count. Let's make this a comment for now because we need to show it on the LCD. We'll send 2 lines with a 0 delay, and we'll put on the first line the counter, colon, and on the next line we'll put in prescaler. So we'll display the prescaler that we're using. We'll set the cursor location for the second line, 10, 11. We use 11. And then it's going to be the second line, which is 1. And inside the loop, we'll set the cursor location, 10, and it's going to be on the first line. And we'll send an integer. And the integer we're looking for is the time 1 counter. And we'll make it 5 digits because it can't go up above 65,535. I forgot the 2 in the APB. All right, that works. See if we can find it. Yeah, time 1. Okay. All right, it's currently showing the previous one that I had, so it should show 10,000 in the prescaler. So let's go ahead and flash the microcontroller and see if it works. And it did not work, and I think I know why. Let me take a look here. I forgot to actually enable the counter within the timer 1 control register. And the CEN is the bit that actually enables the counter. Counter disabled and counter enabled. So we need to enable the counter. So let's go ahead and do that. I'm going to put that right after the RCC. It's timer 1, control register 1. And we're going to, or equals, we're going to put a 1 in the bit for the enabling the counter. So let's try this again. Okay, now it works. PSC. And I'll make it 5 digits again as well. So let's build and then flash again. Okay, we can see that the 10,000 is in this space. So let's start playing with this number. Let's change the value of prescaler to different values and see what happens with this number. You can see it's moving up relatively slowly, but for every 10,000 oscillations, it is counting up each digit. So let's try the maximum number, 65,535. Okay, you can see that it's going up far slower. It's going to take quite a long time to get up to the 65,535 on the counter. So you can see what a difference the prescaler makes on the counter. So let's try changing the number to just 0 and see what we see. It should go so fast that we won't be able to see it. So you can see now it's just a blur. I mean, you can see it changing, and it's pretty obvious that we're not going to be able to get every single digit on this LCD because the LCD works very, very slow. So it's going to be skipping a whole bunch of digits, but it's just going to be putting at whatever the counter is at that particular time when the LCD is not busy. So let's try another prescaler, and we'll go with 500. Let's see if we can actually see the numbers change, or discern that is at least going in upwards counting. Okay, at 500, you can start to see it moving. Yeah, you can see that the numbers are counting up. So let's go a little bit farther down and try 100 and see if we can still see it. Yeah, you can still see it. I'm going to show you how to affect the counter's maximum value and how to count up and count down. Currently, we're counting up. What if we don't want the counter to count all the way up to 65,535? Maybe we want to count up to a particular number, like say 1,000. So let's go ahead and try to do that. But first, we want to make this number climb up a lot slower. So we're going to increase the prescaler. So let's do that first. That's 65,535. That's a 16-bit, the maximum 16-bit number. And another thing I want to do is, because we have that trailing 0 and the trailing numbers in the 5-digit number, I want to clear that portion of the screen so we can see the actual number of digits on the screen. So I'm going to clear it first. So I have 5 spaces. We'll make this the LCD send a string. And we'll take this 5 out of here. So it's just going to be putting in 5 spaces at the same location. And in that 5 spaces, it will put in the number. So let's see what happens when so we have the prescaler of 65,000. Build and flash mark. Get rid of those parentheses. Let's try it again. So you can see that we have the correct number of digits shown. And every time we are clearing the screen and then showing the number, causing a haziness. It's not allowing the number to show up for a long enough time. So let's put in a time delay, just one of our non-exact time delays, just so we can see this number on the screen. Okay, I'm going to put the time delay in just after where it displays the number. So it can display the number, have a time delay, and I'm going to start out with 10,000. Let's see what that does. 10,000 really is a very small amount of time. Okay, it looks a little bit better. The number looks a little bit more clear, but it's still kind of hazy. And it's really not necessary to see the numbers like counting up that fast. You know, our eyes are not going to perceive it anyway, so we might as well slow it down even more. So let's make it 50,000. Let's make it 70,000. Okay, that's far better. We will notice that the number is probably skipping a lot. We're showing the correct number at a particular time at displaying the number, but we're not seeing all of them. So let's see if we can stop this counter at a certain point. And let's stop it at 1,000. And then when it stops at 1,000, it'll start all over again at 0. So the register that we're going to be looking at is the auto reload register. And the auto reload register will contain a number, and that will be the highest number. You can also think of this as a counter overflow. So we're going to create the auto reload register, a number in there, and we'll use 1,000. So let's go ahead and just try this out and see if it works. Okay, so now it's climbing to 500, 600, 700, should stop at 1,000. Okay, it did, and then it started all over again. But what if we want to count from 1,000 to 0? Let's see what we have to do. We can see in the timer 1 control register, there is a direction bit. So we'll access this direction bit, and it shows that there's a counter uses an up counter. This is the default value, obviously, because it's counting up. And the 1 in this bit, the counter is used as a down counter. So let's check that out. According to the datasheet, it says that the counter will start at the auto reload register, which is this, and it will count from this number to 0. Let's go to the CR1, and we're just going to add this to the end of this one here. So we'll go timer CR1 and then the direction. So we should have a 1 in that bit by invoking this macro. Okay, it looks like it started at 1,000, but we only saw the 900s. And it's counting downwards, so it counted down to 0, and now it's starting back up at the 900 to 0 again, 1,000 to 0. So that worked successfully. So let's look at a scenario where we can count up to the ARR value, which is the auto reload register value, and then count down to 0. And the control register gives us that ability to do what is called center aligned mode. So let's take a look at the datasheet again, and you'll see in CMS, we have a few modes we can use. Edge align mode is the current scenario, which is 0, 0, and it is guided by the direction bit, which is over here. But the center align modes, and there are 3 of them, these modes focus on how the output compare interrupt flag is used when it's counting either up, counting down, or counting up or down. We're not going to get into that at this moment, but understand that you could have something counting up and then counting down and having an output compare, or counting up with an output compare, then counting down, or counting up with an output compare, and then counting down with an output. And we'll get more into that in later videos. But let's keep this one simple and just change the center line mode. And we can use any one of these, I think. Let's try it out. So we'll go with 0, 1, the CMS 0, 1. So let's see how we can do that. And you'll probably see that we have a few of the CMSs because there are 2 bits. Let's see if we can. So the 0 and the 1. So which one is in the 0's place and which? So the 0 place is the one here. So we want the 1 in the 0 place. So let's use the 0. So let's see if it counts up and then counts down. Good, we have no errors. Flashed. Let's see if it worked. Okay, it's counting down, then it counts up, and it counts down. So we are getting a zigzag counting up, then counting down, and then counting up and counting down. So we do have the center align mode that we were looking for.
I'm going to show you how to output PWM signal from the ARM microcontroller. PWM stands for pulse width modulation. So in pulse width modulation, you need a pulse from 0 volts to some other voltage, let's say 5 volts, and you need a width, and the width specifies the width of the actual pulse, and modulation, meaning that you can change the width of the pulse. The pulse width modulation, the PWM signal, is a way for a digital signal to output a specific voltage other than the specified voltage of a standard digital signal, like 0 to 5 volts or 0 or 3.3 volts. In digital signals, you generally can only have either the 0 volts, which is ground, or the 5 volts, which is the high value. And then within that digital signal, you'll have, say this is 0 volts and 5 volts, you'll have a threshold in the middle that is considered like the no man's land. So if you have a 0 volts and then you change it to a high and it doesn't get quite that high, and maybe it comes up to a high because of some physical phenomenon in electronics, and then it finally gets to that high. This portion right here is not considered any signal at all. It's just another state that would not be recognized. And the microcontroller would maybe default to a specific 0 or 5 volts depending on how the microcontroller operates. But to make let's say a digital version of a 2.5 volts, you wouldn't be able to do that just with a digital signal. You would need to be able to pulse the digital signal so it is outputting a 2.5 volts, turning the digital signal on and off very fast. For example, if I was going to pulse on a line like this, the pulse is equal width as the width of it not pulsing. So if this is a 0 to 5 volts, this would equal 2.5 volts, depending if the pulse was fast enough to provide an output that is discernible by a meter, or even maybe if you're dimming an LED, it would be fast enough so you wouldn't see the actual flickering. And that's where a couple of the aspects of pulse width modulation come into play, and that is period and duty cycle. I'm going to draw a larger pulse width modulation here. In this pulse, the period is measured from where the pulse begins to where the flat part meets the next pulse. And the duty cycle is the percentage of the width of the pulse in relation to the period. So this would be a 50% duty cycle. Let's take a look at a couple duty cycles. For example, you'd have a 25% duty cycle if the width was 25% of the period. So if each of these graph lines, there would be 4 parts within 100% for 25%. And it would continue this way until you've changed the width of the pulse. So it would be 5 volts times 0.25, which is 25%, and that would equal 1.25 volts. In the 50% version over here, this would equal 5 volts times 0.5, and that would equal 2.5 volts. Another example would be 0.75, and this would equal 5 volts times 0.75, which is equal to 3.75 volts. And the reason why the voltages equal the voltages they do is because this is 0 volts, this is 5 volts, and you'll see, like in the 50% example, it is 5 volts for 50% of the time being the period, and then it is 0 volts the rest of the time. This being a pulse width modulation signal that's fast enough, you would discern this specific voltage, say on a multimeter or watching an LED being dimmed. So 5 volts for an LED would be its full brightness. 0 volts would obviously be off or not showing any light at all, and 2.5 volts would be between that. In the 25 volt version, you can see that at 5 volts, it is only on for 25% of the time. So it's not on for a very long time, and it's off most of the time, which is 75% of the time it's off. So it's obvious that the 1.25 volts would be closer to the 0 volts rather than the 5 volts. And the same is true with the 75%. It's on more of the time. It's at 5 volts more of the time than it is at 0 volts. So you'd have 3.75 volts of output in this case. So what registers do we have to adjust in the ARM microcontroller to achieve a pulse width modulation? The first one is the timer. We're going to use the timer 1, the ARR register, which is the auto reload register. That was the one we can specify the maximum number of counts before it went back to 0 count. Like when it was in the up counting, it would go from 0 to the ARR value and then back to 0 and start by all over again. It would look like this, counting up to a particular point, and then it would stop and start all over again. Counting up, go back down, counting up, and going back down. The ARR determines the period, and the duty cycle is determined by the timer CCR register, which stands for the capture compare register. The one after the CCR actually corresponds to the channel that we'll be using to output the PWM. This is something I actually got wrong while I was testing the programming off camera. So whenever you see me using CCR1, you'll actually need to use the channel that you will select to output your PWM. And just like the ARR register, the auto reload register, the capture compare register is a 16-bit register, and it'll accept a number just like the ARR register will. And you might be able to surmise that since it is, or the period is determined by the ARR register, that the period is also dependent on the counter. It's based on the counter, not the actual oscillator that's in the microcontroller. So you have a little bit more control, and you can cause the period to be relatively long because you can use a prescaler to increase the number of times the oscillator is skipped for every count. Let's take a look at some examples. Let's say that the oscillation, or the oscillator, pulse of the oscillator, looks like this. This is the base oscillator that's within the microcontroller, not the counter. And you specify that the timer 1 prescale is equal to 2. So right there you know that the counter is going to be considering this would be 0, 1, and 2. The count would happen like this. The count would actually skip, would happen on every 3 oscillations because it's based on a 0-based index. Some devices require PWM signals to be relatively slow, like in the servo motors that I demonstrated in the AVR series. And some devices, like laser power supplies that determine the intensity of a laser, requires a PWM to be relatively high. Some devices are very loose in their requirements, meaning that you can have a large range between periods, widths of periods. So you can have very slow to very high PWM signals due to its tolerance. And there are some devices that require precise periods for their PWMs because they may actually have circuitry that will measure the PWM to determine a value, especially when that device is an instrument that requires extreme precision and resolution. This type of PWM that I'm demonstrating here is called the edge-aligned PWM, meaning that the period starts at the edge of the PWM signal. You also have center-aligned modes. That was also called phase-correct mode in the AVR series, but we'll discuss that in a later video. So where does this PWM out? The timers have channels, as you can see here. You see timer 3, channel 3, timer 1, channel 2N, timer 3, channel 1, timer 1, channel 2, timer 1, channel 1, timer 1, channel 1, channel 2, channel 3, channel 4. We have a timer located at pin 44, which is timer 1, channel 4. The pin that I want to output the PWM signal out of is pin number 44 because these pins 43 and down, these are being used for the LCD. So the one that I have immediately available is pin number 44, which is the timer channel 4 at my disposal. So there's probably a couple things we need to do. We need to make sure that the alternate pin function is used for the pin number 44 because we don't want it to be used for general purpose I/O. We want it to be used for one of these, specifically the timer 1 channel 4. So let's take a look and see how we do that. Let's go to the data sheet, the reference, and the way you select the pin that you want to use is the CCMR1 pin, which is the capture compare mode register. And that's kind of misleading, but the electronic engineers out there will probably find that this is a normal thing. So you can see that you have output compare 1, output compare 2, and you have these PEs and FEs and CEs. And these are explained underneath the table, specifically for like the CE would be clear enable, the M would be the mode, the PE is preload enable, FE is fast enable. And as we get deeper into using these modes, these will be explained. The hint that this particular register has to do with the output or the input channels is that in the description it uses the channels can be used in input capture mode or output compare mode. So when we specify the timer 1 channel 4, this can be used for input or output, and we'll be using these channels for receiving PWM and measuring their widths and periods. We can also use it for receiving other inputs for timing. You'll notice there's only a 1 and a 2 here, so we may have to go to another register to find the 4 and the 3. Here we go. Okay, so it's the CCMR2 that we need to use for the
the 4th channel. And for this experiment, we're going to set the mode, which is the OC4M. This specifies the mode for this particular pin, and it has 3 bits, 0 to 2, 0, 1, and 2. And we're going to set it to 1, 1, 0. And it doesn't give you any information on this particular part because this is showing the 4th channel. And if you want to know more about these modes, you have to actually go to the 1st channel, because you can see that the output compare 1 mode, M mode, and you'll see that 110 is for the PWM mode. And all we have to do is replace all these channel 1s with channel 4. So PWM mode 1 in upcounting, channel 4 is active as long as the timer count is less than the CCR1 value. And remember that the CCR1 value is the duty cycle, and the count is just the timer counting. So the channel 4 is active as long as the count is less than the duty cycle, else it is inactive. And since we're not using down counting, we don't have to worry about this portion of it. And really, these two modes are the same except for the down counting mode. So we could probably use this, but I'm going to stick with this particular mode, mode 1. Now that we know this, let's take a look at the program that we had before. In the PSC, we're going to make this a lot smaller. I'm going to go with 100. We can see what happens with that. And the ARR is the period. So I will use 100 as a period as well. So it's an easy number to understand percentages with the duty cycle. So let's put in the duty cycle number, and that's under the CCR register. Let's make it a 50% duty cycle, or 50 counts. This isn't actually 50%. If I wanted 50% of, let's say, 200 period, that would have to be 100. So I don't want you to I don't want to confuse you and think that this is actually a percentage. It is, if it's 50%, it would be half of the ARR value. So 25% would be 50 over here. So let's go ahead and keep this at 200, and let's make this one 100 so we get a 50% duty cycle. So let's put in the 110 for the PWM mode. This is 0 is at the 0-bit location, and this is at the 1 and the 2-bit location. So it's the OC1M. Let's go ahead and put that in. CCMR2, that's where the 4th channel is located. And we're going to OR equals, because we're dealing with bits here. Let's see what it would be called. The OC1M. Oh, I gotta use CCMR2, OC4M. And we want the 1 and the 2. Before I forget, we need to enable the GPIO. So let's do that over here. First, we need to use the reset clock control register and the advanced high control bus. Let's see. Yeah. So we're going to be enabling the A GPIO port, because the pin that we're looking for, the channel 4 pin, is PA11, so it's under the GPIO A. And now we have to find its alternate function mode. So this is it here. It's 10 under the mode register. So all we need to do is turn on the number 1 bit and turn off the number 0 bit. Let's go ahead and do that. So first we're going to turn off the 0 bit. We're going to use the AND bitwise operation and the NOT bitwise operation, which is the tilde. We want it to be 0. Number 11. Let's find number 11, and that's the 0 place. And we'll do it again for the ones. Okay, so we've set the GPIO PA11 as the alternate function. The next thing is to select the actual pin, or the way it's going to be outputting the PWM. And it states in the datasheet that you must enable the corresponding preload register by setting the output compare for PE. And we can see that the output compare for PE is preload enable. So looking at that particular bit, you can see that if we put a 1 here, preload register on timer 1, which we're using timer 1, CCR1 enabled. Read-write operations access the preload register. The value in the CCR1 is loaded in the active register at each update event. So what I see is the main difference between not using the preload register and using the preload register bit is that when you have a preload register, it is updated at the update event. But if you don't use that, this can be updated immediately. It can be written anytime. So let's go ahead and add that to our code. Actually, I think it's in the same register. CCMR2. Yeah, that's there. So I can just simply add it to the end here. Need that other one. One really interesting aspect of this PWM is you have incredible control, and you can actually output a particular polarity if you want it to be active high or active low, which means that when you start out with a PWM signal, you can have it start out high, and you have the duty cycle high, and then it goes low to end the period for the PWM. Or you can have it start out low and then climb up to the start of the duty cycle, and then go
across to the period and then go back down. So we can output the polarity using the CC4P bit. So let's take a look at the CC1P description. So if we keep it at 0, which is probably at the reset, it'll be active high. If we wanted to start as a low signal and then go up to its duty cycle portion of the pulse, you'd want to set the 1 on that pin. Since that's already on the way I want it, it's reset for that particular pin, I want it to be a active high. So I'm going to keep this at its reset value. And the other thing we need to do is the CC4E, which is the output enabled. We want to make sure that's self-explanatory. We want to make sure it enables the output on that pin. Let's see what the description says anyway. So we can see that 1 being the on state, we want to turn it on. The OC1 signal is output, which is the OC4 signal, is output on the corresponding output pin depending on the MOE, OSSI, OSSR, OIS1, OIS1N, and CC1NE bits. We will be discussing the MOE in a little bit. So this is a dependent aspect for this particular pin. So let's go ahead and turn on the CC4E in this register, the CCER register. Looking for the CC4E. Here we go. Okay, now we've set that to output. Okay, so now we need to enable the MOE, which is the main output enable. By setting 1 in that bit, the output compare outputs are enabled if their respective enabled bits are set. The CC4E, which is what we just set, the CC4NE, in the timer 1 CCER register. The break and dead time register description is kind of misleading, but I guess they needed a place to stick this, so this is where it is. So we'll put it right below here. We want to enable the MOE. Here we go. And I think the last thing we have to do is set the UG bit in the EGR register. And this is initializing all of the registers before we start using the preload registers. And I wouldn't be too concerned why we're using the UG bit in the EGR register. Just know that this is sort of a requirement that's needed for this function to work. The UG bit we're enabling here. I'm not sure if I really need to show anything on the LCD, but we need to set the alternate function. And we're first going to need to go to the main data sheet for that particular microcontroller, find alternate functions. So we're looking for registers, or for the port A. So we'll look at the port A and we have PA11. Let me see what I have on see if it's correct on the alternate functions. So I have PA11. So I have USART 1 CTS and then time 1 channel 4. Let's see, looks like the AF0 is event out and then the USART 1 CTS and then time 1 CH4. So you want to go to this sheet to determine which alternate function you need. And this specific one is AF2. And then you can go back to the reference manual and check to see what code you need for the AF2. And you'll see that there are 2 registers. There's an AFRL, which is the alternate function low register, and the AFRH, which is the alternate function high register. And these are the pin assignments. It's 0 through 7 for the low register, and it's 8 through 15 on the high register. So there's 16 pins for each port, and we're using pin number 11. So we're going to have to select this AFR11, but it's not going to be as easy as doing that. The AFRH is actually written as AFR open bracket 1 close bracket in programming. So let's check that out and see what we have to put in. I'm disabling the LCD just to make sure this is going to work correctly. So I disabled the Initialize, Setup Display, and all the LCD stuff that we have in the program. So let's take a look at using the alternate function, GPIOA, and we need the AFR. And you'll see that a bracket showing an array, the size of the array is 2, which is 0 and 1. So we'll go ahead and select that, and then we're going to use the 1, which is the high. We have a couple of options in this. We can use the, just using a binary number, and let's go back to the data sheet to see how many zeros we need. So we would need 0, 0, 4 zeros, 4 zeros, 4 zeros, and for AF2 it's 1, 0. So we need a 1 here. So it's going to be 1 with 13 zeros. So 1 and then 13 zeros. Or we can do it this way. You have a couple of options. Actually, the data sheet shows in its programming examples doing it in this way. Let me see if I can find that. So in this case, they're looking at the low because they're looking at pin number 5. In this case, they're looking at the high and they're going to pin number 9. But because it starts at 0, they have to subtract it by the number of pins that would be in the low. Since this is a little bit more confusing, it's easier just to look at the data sheet on this section here where you're wanting to shift it to the left and you're shifting it 4 1, 2, 3 times 4. So you have 4 positions on each one. So you're multiplying for each pin 4 times. So let's take a look at how to do that. I'm going to use the equal here. And we can use the 0B10, or we can use 0x02. And we're going to left shift that number, the 02, which is 10. Again, that is 10. In binary, it would be 10. In hex, this would be the number 2. And we're shifting it 3 times 4, which is also 12. So we're shifting 02, 12. And it puts a number 2 at that location. I'm going to keep the binary just to make it a little bit simpler and easier to read. And I'm not using the correct duty cycle register, the CCR register. by me saying number 1, I'm actually specifying channel 1, and I don't want to do that. I want to use channel 4. So we're putting that duty cycle, this number on the channel 4. And if you don't do this, it's not going to work at all. So let's go ahead and see if this program works. To determine if I'm actually getting a PWM signal, I'm putting a multimeter to pin number 44, which is the PA11, and I'm also putting the negative pole or the ground to the negative rail. So we should be able to get a PWM voltage as per the duty cycle that we specify in the program. So if we have a duty cycle of 50%, we should have a voltage coming out of here approximately at about 3 or 1.5 or thereabouts volts. You'll also notice that I changed my ARR value and my CCR values. I used to have it on 200 and 100, but I noticed that I needed a little bit more granularity to get the voltages that I desire. I also changed the prescaler to 0 because I wanted the fastest possible timing here. So the prescaler is at 0 and it's just going at the microcontroller clock speed. So let's take a look at the multimeter output. This is a voltage that I got from using the two values of 2000 to 2000. So let's go ahead and change it to 1000 and let's see if we get a half duty cycle. Should be around 1.5 volts. Okay, so 1.6 volts. That looks right because you saw the other voltage was 3.2, so half of that would be 1.6. So let's try a 25% duty cycle. We got 0.8. That looks really good. So let's see if we increase the ARR value to, let's say, 20,000. Make it a lot larger, and let's make this one 5,000. So to get a 25% of 20,000, let's see if the number changes to see if more resolution will give us a more accurate number. It didn't change that much. It was 0.803, I think. Now it's 0.805. So it might have increased a little bit. Let's look at the full 100% and see if that is actually a little bit higher than the previous 3.2 value. No, it's about the same. So I think in this particular case, I'm going to keep it at pretty low value, relatively low. But these values are going to change for your application, so just keep that in mind. So that is a not so brief look at PWM. This is the edge condition. I plan on using the analog to digital converter from time to time, and I also want to add code to it as well from time to time. So I want to make a header file like I did with the LCD functions and make it so we can quickly initialize the ADC and then start grabbing data from whatever channel that we desire. So let's create a new header file and make some convenient functions for us to use. For now, I'm going to actually eliminate the temperature portion of it because I don't see me using the temperature within the microcontroller for any application, but it's available on video, so you can use it whenever you want to. So I'm going to actually take out any reference to those parts. So let's create a header file. Let's see, make a new file, and we'll call it adc.h. Actually, I don't want to put the .h there. I'm going to use it. Select it this way, and then we'll save it. I think it saved it under timers workspace. Let me see. Let's just go new file. Yeah, look at that. I don't want it under the timers and counters. I want it under, I'm going to do this the manual way, or I could actually delete it. Let me do that. I'm going to delete it here. It's a little bit easier. Okay. And I'm going to go to new file, and I'm going to change the workspace to ADC tutorial. So I'll know that that's going to be the main place for the header file. I'll go to the app because that's where all the files are. .h and ADC. Save. All right, we want to do the same thing that we did in the LCD functions, where we create we pretty much state that this is the LCD functions header, this is the ADC header. So I'm just going to copy and paste that. We don't need the stdio on the ADC, so we're going to release or remove that. And I think it's end if. Yeah, end if. Okay, so all of the code that I want to put in here, it's going to be called ADC functions header, ADC. All the code will reside between the define and the end if. And the next time it tries
to open up this header file. If it's already been defined, it won't run any of this again. All right, so let's start copying stuff in here. We'll start with a calibration. I could probably take all of it and do it one time, but I think it's just a little bit easier to do it one at a time, just to make sure that I might want to put them into separate functions. I might not. So let's see. I'm going to start out with, I'm going to peek over at the LCD functions just to see what I'm doing here. I don't think I need to return anything. I'll call this ADC Initialize, and I'm not passing anything in, I don't think yet. So we're calibrating. I'm going to put everything in the Initialize. And then if I need to separate it out, I can just take something out and make like ADC calibration or whatever. So it looks like we are pretty good here. We're doing just making sure that it's calibrated. So let's keep that the way it is. All right. I'm going to go ahead and put in ADC Initialize. Well, we have to include it first. There we go. And I'm going to put in ADC Initialize. So we're initializing. We know that the calibration is already in here. So if I ran it from this point, it would probably work. So let's go ahead and take in the clock, selecting the clock, paste it in here. I'm cutting and pasting. So select the clock source. Let's see if there's anything in here that we need to modify or make as a selection for an input parameter. And it doesn't look like it. So I'm going to save that. Now the ADC enable, cut, paste. All right. So we are just enabling it here, and we're making sure that it's ready. All right, that seems to be pretty easy. Now this one is different. This may change the sample rates and the channel select. This is very important here. So we might want to put that into a separate function. Okay, so let's go ahead and I think I might want to put the sample rates and the channel select in the same function. So let's go ahead and cut this. And I don't think I'm going to be outputting anything from here, so it can be void. And let's see, ADC channel select and sample rates. Maybe I want to separate those two out, but let's do this first. And I'm not sure what I need to input as the channel select yet. So let's take a look. Well, let me go ahead and put the code in here. Channel select is going to be just a simple number, obviously. And we can see that it's an unsigned integer of 32 bits. So we can go ahead and just put that in here. UINT 32, UINT 32T. And we'll call that channel. And then all we would have to do is put in this. So let's go ahead and, you know what, I want to do this first. I want to copy this because make it a little bit smoother for me and less error prone. I'm going to actually put in the channel that I have here. I'm going to cut it because I don't want that in there anymore. I'm going to paste it here, end it with a semicolon. So I'm just going to replace this with channel. On second thought, I would like to just say channel 1 or channel 2 or channel 3. So let's look at the differences between the channels and see what main differences these are. So let's make a few of these. Channel 2, channel 3. I don't know how many channels there are actually. Let me see. Let me do this here. Here we go. So it looks like we have 18. Channel select. Here we go. Looks like we have 18 of them. And we know one of them is voltage and one of them is temperature. But we'll go ahead and allow it for the 18. So let's start with 0. That's going to be, no, it's not going to be syntax here. So that's good. I'm doing it this way because I want to look at an alternative way to going to the data sheet. We don't really need to go to the data sheet if we have these variables or defines macros here. So you can see it's upping it by 1. So you got 1, 2, 4, which is the bit next to it, 8, 10. So all we're doing is we're shifting the bit 20, 40, and 80. So all we're doing is we're moving the bit over 1. So that's pretty simple to do. And this is just using the left shift. So if we take a look at the hexadecimal number 1 and 2, 4, 8, let's go ahead and do a conversion from hex to binary, and you'll see how the 1 is shifted from 1 to the next. So 0x1 should be in the 1's place, and then if you do 2, it's in the next place. You can see how it moves. 4, which was the next one, it's just moving to the left. 8, there you go. So all we're doing is with a particular channel, this would be channel 0, this would be channel 1, this would be channel 2, channel 3, and all we're doing is we're doing a left shift operation. So that's pretty easy to do, obviously, we know that. So in the channels, for the channel select, let's just go ahead and put in very simple UINT. Is there an 8 here? Let's see. Okay, so there was a fast 8. I'll try it out. What the heck? Okay, so if we put in channel 0, then we should expect channel 0. So we'll make that the UINT fast 8, whatever that is. I've never heard of that. But we're going to put the channel in there, and this is going to change because we want the 1
We want to left shift channel. But when channel is 0, we have to say channel +1. Actually, no, we want to keep it 0 because we want it in the 0th place. So let's keep it that way. To keep this video simple and to ease your way into ADC and the more complexities of ADC, I'm going to keep the sample rate the way it is. I believe I'm using the slowest sample rate. So I'm going to put this into the initialization area because we're probably not going to be changing this very often. And we'll only when we really want the microcontroller to work in an extremely efficient manner. We don't really need to work with it right now. And the sample rate is going to be determined by a lot of different factors anyway. And that would be circuit factors, not necessarily programming factors. And having the knowledge of the circuitry of the ADC that's going into the ADC pin, resistance and things like that, these sample rates may be able to change. But let's keep this simple and we can scaffold the way into the future. So let's keep it this way first. So this one really is the only thing we're going to be messing with is the sample, is the channel select. Let's see. Let's make channel select. And you know, this UINT fast 8T might actually, I'm not sure if I should keep it or not. If I just use a standard int, it might actually make it a little easier to know what to put in when you're actually putting in the function or using the function. So let's see what it says when I try to put something in here. Yeah, you can see it says UINT fast 8 channel, and that gets a little bit confusing. And then you can see that it's expecting some variable or some number of UINT fast 8T, which I don't think I've ever used myself. And it'll be interesting to see what happens when I use it. I'm going to keep it the way it is, but I might change it later on to just int or something a little bit more understandable when you're trying to put in a number here. All right, let's see if this still compiles or builds. Okay, good. All right, so this is kind of bugging me a little bit, so I'm going to take that out. Channel select is 0. We have initialize and we have channel select. You can see that I'm using the same components using the potentiometer to provide a voltage onto the pin number 15. So everything should be the same as before. So I'm going to plug it in. I'm going to flash the microcontroller. All right, looks like we have something on the display. Let's see if we can get a better shot of this. Okay, that's better. Okay, so we have the potentiometer and it doesn't look like it's changing. I wonder which channel I actually used. Did I use channel 0? Let's try channel 1. I think I used channel 1. Yeah. Let's do another build and flash. All right. Looks like it's a little more stable. Let's see. Yeah. Okay, that's the one. I'm turning the potentiometer, so we are getting a change of numbers there. Okay, so now we have the ADC in a very convenient little package up here in a .h file. So we don't really need to see that code anymore. All we need to do is initialize it, select the channel, and then read what the contents is on the ADC. I want to try a couple experiments. The first one is I want to just go ahead and plug in the PWM signal coming out of the PWM pin, I think it was PA11, and stick it right into the ADC channel 1 pin and see what measurements we can get from the ADC. So let's try that. First, I need to get the ADC.h into this project. So we have it available here, and we want to add it to the include ADC.h. You can see it's available, and I'm going to go ahead and make the LCD work as well. I think we have no conflictions, but we'll find out. I do want to change what's being sent to the LCD, obviously, because I'm not going to be considering the counter and prescaler. I'm going to be considering the ADC. So let's just say ADC output, and I'll put nothing on the next line. So the ADC outputs would be 0, 1, 2, 3, and then 4 and 5. So I'll put it on the 5th location. And this one will be, we're not going to put anything here. But over here, we want to put in the ADC. I think it was the DR. I think it was ADC1. Yeah, the DR. Okay, so we got that right. And it's going to be 5, position number 5 on the first line. All right, so we're going to connect pin number 44, PA11. We're going to connect that to pin number 15, is PA1, which is channel number 1. So the potentiometer from the previous project was removed, and the wire going from pin 44 to pin 15. This is the ADC input. This is the PWM output. Let's see what the ADC shows from a PWM output. But we also have to add the ADC initialization in here. We haven't done that yet. So let's go ahead and initialize the ADC. And we're going to select the channel select, and we're going to select channel 1. Okay, so we've selected ADC channel 1. Okay, I'm back over here at the ADC project that we were doing before. Copy this portion into the other program. So let's go ahead and put that in here. Okay, so now we're starting the ADC process. and checking to make sure we're okay. You can see that the readout, if you look at the, it's going from 0 to 4068, pretty much at the top end of the voltage. It's doing exactly what it's supposed to be doing. It is taking in a PWM signal, and PWM is a square wave, and the ADC is actually working a little bit too fast to take in a voltage from a PWM signal. It is actually taking in the square wave, and that's not what we want, obviously. And the only way to be able to get a voltage out of a PWM is actually to add an RC circuit, a resistor capacitor circuit, to smooth it out to a nice smooth voltage. Without an oscilloscope and a little bit of research on what capacitor and resistor I would need to smooth out this, let's go ahead and do the reverse. I'm going to hook up the potentiometer again and take the ADC number that we have, the digital number, and we're going to plug it into the PWM so we can cause the output voltage on the PWM to be variable according to the potentiometer setting. So let's go ahead and add the potentiometer back to the ADC pin here. This is pin number 15. So it looks like the ADC still works with the potentiometer. So I'm turning the potentiometer and we get a pretty good readout. So I also want to connect the multimeter to the PWM output so we can see what the output will be when we change the PWM duty cycle according to the analog to digital converter. So I still have the PWM connected to the 44 pin. And I'm going to take my multimeter and just connect the positive lead to that pin. And I'll connect the negative lead. This is the positive lead going to that pin. And then the negative lead, I'm going to put to the negative rail. So I have the duty cycle at 50%. And on the multimeter, it shows 1.5, which makes sense. So let's change the PWM duty cycle and just to make sure everything is working correctly. So we'll make it 2000 and we'll make this one 500 to get a 25% duty cycle flash. And it should be around 0.8. There we go. Good. So now let's take the analog to digital conversion, the ADC1DR, and let's plug this number into the CCR4. But we also have to understand that we have to look at the duty cycle limits from the ADC, because the ADC is a 12-bit number. So if we go back to binary to decimal converter, let's see what a 12-bit number would be in decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, it's 4095. So that makes sense. So let's go in here and make the period 4095, because that would be a 100%. If the CCR4 value was 4095, that would be a 100%. So we want to take the CCR value. Let's keep one here just to sort of initialize it. We'll make it 50%. So that's around 2000. And let's take another CCR and bring it in here. And I'm going to, actually I want to put it above the time delay, actually in the first part of it. No, I want to make sure that I have the ADC DR available to me when I'm using it. So I'm going to take the ADC DR, I'm going to copy it and put it right into the CCR4, which is the duty cycle number. And we'll see if we can change the PWM, the voltage coming out of that, by modifying the potentiometer. Let's check it out. Let's see if I can get everything in frame here. So we know what the ADC signal is. So we can see that the ADC is about 2480. Let's turn the ADC, we'll turn the potentiometer. Let's go up. It looks like we're affecting the voltage. So we are changing the PWM signal by turning the potentiometer. And I'm turning it down now. So we're almost at ADC 400, 300. We're almost to the 0. I don't want to go all the way to 0. So you can see we got 0.142 volts. So let's turn it up again. You can see that we are getting, I'm going to go up all the way. So we got 3.1. Okay, so I turned it down. So it looks like we were successful in one portion of this video where we're affecting the PWM signal coming out. And you can just imagine the applications we could do with this by, say, having a servo connected to the PWM signal coming out, and by turning the potentiometer, we can move the servo. So that's one application. I'd like to show you a short demonstration. Since we have a PWM output on pin number 44, showing the voltage from a multimeter really isn't that interesting. So I'm going to add an LED to this pin so you can see the dimming of the LED controlled by the potentiometer from the analog to digital converter. In last video, we used this potentiometer to control the PWM duty cycle, causing the voltage change in a digital way. What we'll do in this experiment is just connect an LED to pin number 44 using 330 ohm resistor and the LED to ground. The PWM will be essentially blinking on and off extremely fast, making the LED look like it's dim, but really it's just switching on and off extremely fast. In the program, the first thing I want to do is take out the time delay for the LCD, because the time delay actually makes it cause flickering with the LED when you're changing the ADC. It doesn't cause any flickering during the PWM because the PWM is constantly being output on that pin, and that is not being affected by anything in the program except for the modification at the CCR4, which is the change of the duty cycle in this case. So let's go ahead and add the resistor and LED to pin number 44. Okay, after building and flashing the microcontroller, we can control the LED's brightness by turning the potentiometer. You can also use a more automatic approach if you wanted to have an LED dim up in brightness, smoothly get brighter, and then dimmer and brighter and dimmer. You can do that with the duty cycle and the PWM as well. One of the examples that I like to use to demonstrate PWM, pulse width modulation, is on how to control a Hobby Servo. And this is specific to analog servos. Since there are digital servos and analog servos, digital servos only require a specific communications protocol where you're just sending information via some protocol like I2C. But with analog servos, they require a PWM signal at a 20 millisecond period. So what is a 20 millisecond period? You can think of this as a portion of a 1 second period. So let's draw a 1 second period. A 1 second period has 1000 milliseconds. So if this line represents 1 second, this would have 1000 milliseconds along this line. So 20 milliseconds would be represented by each tick represents 40 milliseconds. Because if we take 1000 milliseconds and divide it by 20 milliseconds, we would have 50 parts. And in this 1 second, we have 50 spaces between the ticks. So the servo is going to require us to create PWM signal with a pulse between each one of those ticks. The pulse is actually going to be relatively narrow, and the width of this pulse here will represent the rotation of the horn on the servo. And we learned from the other tutorials that the ARR determines the period, and the CCR, and the number after the CCR is the specific channel we're using for the timer, determines the duty cycle. And the duty cycle in this case will determine the rotation of the servo's arm, the servo's horn. So our first task that we need to do is we need to determine the period. Okay, so first we need to start somewhere to figure out this ARR value. The data sheet of the microcontroller that I'm using states that the clock speed at reset is 8 megahertz. So what does that mean? This second here, from this point to this point, is 8 million cycles. And we know that we have 50 partitions. So 8 million divided by 50 partitions, because we need to figure out how many cycles is in a single period here. And this equals 160,000. Well, this value is actually too high for an ARR value. The ARR value can only go up to 65,535. So this is where the prescaler comes into play. If we use a prescaler of 1, that would essentially divide this 8 million by 2. So let's just, for the sake of argument, divide this by 2. That would be 4 million divided by 50. And that would be 80,000. That's the same thing as taking the 160,000 and dividing that by 2. So if we have a prescaler of 1, we're dividing this by 2. If we have a prescaler of 2, it's dividing this by 3. So let's see what that would be. Okay, that's 53,333.33 repeating. I'm not sure if I like a number that has a decimal in it. So let's use a prescaler of 4 and see what that gives us. And that would be 40,000. So that works. So if we kept the prescaler at 4, that's the PSC number, we would use the 40,000 for our ARR number. But we're just assuming that the microcontroller is 8 megahertz. We're just hoping that the data sheet is correct. So let's go ahead and do some tests to make sure that 40,000 done 50 times would equal 1 second. So we could actually have a routine in the microcontroller in our programming, and we can have the microcontroller only when this is counted up 50 times. It would maybe show a count up on an LCD, and we can determine our sort of human sense of what a second is and see if it does look like a second. And that would verify that the 8 million or 8 megahertz is an actual correct number that our microcontroller is set. Let's make a library from our PWM code so we don't have to keep rewriting all of this stuff. In the beginning, we'll just make a simple library. So we'll first a new file. I guess we can call it PWM functions.
and we'll use the .h header file, and let's go ahead and save. So now we have PWM functions. We have our blank screen here. So let's go ahead and take a look at the LCD functions and see how I did the if not defined. So I'll just copy that in. I don't need this stdio. I'll just take that out, and then I'll end if. So anything that happens inside of here will be executed once. So let's take all of our stuff that relates to the timer and the PWM, and we're going to copy it or cut it and then paste it here. Let's wrap a temporary function around it. Void PWM function. Doesn't really matter what I'm going to put in here yet. And then I'll just put everything in here. Okay, at this point, I don't want to make it any more complicated than what it is. But I'm going to change this to setup, I think. PWM setup. And I want to try to keep everything in this order. So that's one of the reasons why I don't want to do anything more complicated. Because I could have in like maybe an input for a timer number and timer channel. But I want to just maintain the order and the way it is now. So I'm going to put PWM setup channel 4. We can add more later. I know I need to change these numbers here. The prescaler, period, and the duty cycle. So let's go ahead and put those in first. We're going to make them regular integers because they actually have a pretty high number. They can go up to 65,535. So the prescaler, we'll just call it prescaler. And we'll have an input for period and an input for the duty cycle. All we'll do is just come in here and place these, period, and the duty cycle. Okay, so I think we can go ahead and start using this now. So let's just go ahead and I'm going to copy it and paste this. And then PWM functions, header, and the PWM and timer setup stuff was over here. So let's go ahead and put it right here. Take out the void because we don't need that anymore. And let's create a prescaler. And we're going to use prescaler of 4. So we'll put 3 there because it's 0, 1, 2, and 3, which makes 4 counts in the prescaler. In the period, we wanted 40,000. So let's go with 39,999. So that should be 40,000 with a 0 index. And the duty cycle, we don't know that yet actually. So let's just put in 2,000. It's not really necessary right now to put in the correct number because we're just going to see if we got the timing right. Put a semicolon at the end. Let's keep the ADC stuff with the LCD, and I'm just going to put in count on the next line for the LCD so we can see how it's counting up. Let's remove this because we don't need this anymore. I think I'm going to remove this here. What this part of the code is doing is we're putting in the ADC into the duty cycle to change the duty cycle, but we're not going to do that right now. And we don't need to look at, well, we can look what the ADC is showing. It doesn't really affect that. What we're about to do, so what we want to do is show the count of the timer. Put on the second line here, 1, and let's see where on that line, 8. Actually, I think it's 7 because it started from 1, not 0. So I'm going to include this at the end. PWM functions. Well, now that we've changed the PWM, or we've set it up to output a PWM the way we want it to, this is probably not what we're going to need to look and see if we have the proper timing using the 40,000 as the period, because we need to see what the timer, we want to just confirm that 40,000 is the right number, but we need to actually be able to see it with our own eyes and look at it in the LCD. And the only way we're going to do that is to actually put the 40,000 in the prescaler. And the ARR value, because we have a prescaler of 4, when it gets up to 200, because if we're looking at multiples of 50. So when it goes up to 50, we know that we've covered 1 second if there was a prescaler of 4. But since we can't do 4 times this number, and it would go above the capacity of that type, of that data type, we're going to have to put 200 here because that's 50 times 4 would be 200. So for every 200 counts up using the ARR, that would be 1 second. Let me put this down to like 10 or something like that. We don't want to cause any problems with the duty cycle being any more than the period. So the ARR number is what's going to be resetting the counter. It's going to be counting up to 200, and then it's going to go reset back down to 0. So when we take a look at this, we could actually see it counting up to 0 or up to 200 and then down to 0 every single second. Let's go ahead and see what that looks like. Okay, we flashed the microcontroller. You can see it's counting from 0 to 200 every second. So if I just count like I would normally do for each second. So if we count normally like 1, 2, 3, 4, 5, we can see that it's counting for every second. But that doesn't give us enough clarity and understanding whether it's doing it right or not. So let's see if we can have it actually count seconds, just to make sure that we're confirming that our 8 megahertz is really 8 megahertz.
we're not going to be able to go in here and just do a conditional statement with the count, because we're not going to be able to capture a specific count, because this program is working a lot slower than the counter is working. So if I said like if timer counter equals 200, then increment a second, we would miss that 200 some of the times. So the only way to actually look at incrementing for each second, we're going to have to look at interrupt. And there is an interrupt flag that we can access for this timer, and it's called the UIF, update interrupt flag. And the way it works is, if you look at one of these diagrams, you can see it counting up. When the counter is reset at 0, the update interrupt flag is set. And once it's set up high, I can count 1 second, and then I can reset it by software. I can actually put a 0 in this flag. So let's go ahead and do that and see what that would take. So I know I have to look at this register, or this in the register. It's in the SR register, I believe. And I also need to make sure that the URS bit is set as well. So let's take a look and find out where that URS bit is located. The URS bit is located in the control register for the timer 1. See it right here at the second bit place. And let's see if we can find out more about it. The update request source. This bit is set and cleared by software to select the UEV event sources. And I believe it really doesn't matter, because we're looking for the underflow or overflow. So it looks like it'll work with either 0 or 1. If I wanted to get the UIF to be high on the UG bit, then I would want 0, or for the slave mode controller. But that's not really important to me. I'm really concerned with the counter overflow and underflow. So let's see if this works. So I shouldn't have to update this at all. So let's go ahead and just look at the UIF flag and see what happens. So if the time 1 SR the status register, and there we go, the SRUIF. Then, so this is where we want to increment the second, and then we're going to set it back to, we're going to reset it. So let's create a new variable called seconds counter. We'll make it 0, and we will increment that whenever this flag is invoked. And now I'm going to reset the flag. Okay, and we still need to display it on the LCD, so let's go ahead and do that. So instead of doing this, showing the timer counter, we'll show the seconds. So this should show us seconds. Let's see if this works. And we have no errors. Flash the microcontroller and see what happens. Okay, it looks like we have correct output. It looks like it's going up 1 second. So we have just confirmed that we have an 8 megahertz microcontroller. It's set at 8 megahertz, and that is what it says in the data sheet. And it is counting up 1 second at a time. So we know that putting in the PWM the way we want to for the servo would work fine. So 40,000 is the correct number. So let's determine what the duty cycle needs to be. So let's take a look at the data sheet for the servo that I'm going to be using. So I've got a high-tech HS322HD. So let's see if we can find some information on that. Okay, so I found the specifications for the PWM pulse data for the high-tech servos, and this is for all their analog servos. And the duty cycle needs to be between 0.9 milliseconds to 2.1 milliseconds, with 1.5, which is right in the middle of the 0.9 and 2.1 as the center. And the pulse refreshes every 20 milliseconds. We've already established this. So now we need to create the duty cycle between 0.9 and 2.1 milliseconds. So if 40,000 represents 20 milliseconds, 1 millisecond should be 40,000 divided by 20. So let's see what that is. So the low end of the duty cycle is 0.9 milliseconds. And with our 2,000 counts per millisecond, that would be 0.9 times 2,000, which is equal to 1,800 milliseconds, or 1,800 counts. That would equal the low end duty cycle. I'll put this on another line here. And 2.1 milliseconds is equal to 2.1 times 2,000, which is equal to 4,200. So you can see that our low end is 1,800. That is the horn at 1 position, and 4,200 is at this would be the minimum position, and this would be the maximum position. And I think this would be maybe, let's say, 0 degrees and 180 degrees. So let's go ahead and set up this. I think what we need to do first, we need to work on this library just a little bit more, because I think we're going to have to separate out something to make it work, because I don't want this to be repeated all the time when I'm making a change to the prescaler, period, and duty cycle. I don't want to have to keep putting this code in or running that code. So I'm going to create another one called void PWM channel 4 set period and duty cycle, or set, no, set parameters. I'm going to say set parameters. That's a little bit easier. And then I'm going to take the parameters in here. I still want this to stay because when I'm initializing it, so we can take this prescaler period and duty cycle and just copy it to this one. And so what we're doing is we're going to replace this portion here with this. So we're not repeating the code at least. So whatever we have set here, we're going to pass it into this function. And we can also have this function available to us to set parameters in the main. So let's go ahead and do that. But we don't need to do this anymore. We can take this out. All right. So let's go ahead and put in the PWM channel for set parameters. And I'm going to put in the same things that I have here. Actually, I need to change this to at least like 1800. So let's do that. Okay, so now I have it at this location, and then I want to change it to 4200, so it swings in the other direction. But it's going to do this so fast that the servo is not even going to move or it may jitter because it's trying to change the location too quickly. So we need to put a time delay right here. So let's make it 100,000. That may not be enough. So let's go ahead and put it 100,000 between them. So we should have the servo turning from 0 degrees to 180 degrees and back. So it's just going to go back and forth. Let's see if that works. First, we need to connect the servo. So we'll need a 5-volt connection at the red. We'll need a ground at the black. And at the yellow, we can have our PWM. I don't think the yellow needs to have 5 volts as its pulse. I believe I remember seeing in the data sheet that it can be 3 volts. I think it was like 3 to 5 volts. So let's go ahead and try that. We'll put the signal in on the PWM here, 5 volts in the middle pin and ground on the end. Before I actually connect the servo, I want to build and flash this microcontroller first, just so it can be in the right state, so I don't cause the servo to go to any extremes. And it looks like I have okay, I'm not even using my variable. Unused variable. I'll just take it out just for the fun. Something else. Okay. I see the problem here. I put this function after I actually am using it. So it needs to be before this, or I need to create a prototype. I like to do. All right, this is like sort of a programming thing. I'm sure there are opinions both ways on this. All right, so let's go ahead and try to pilot again. Good, it worked. I'm going to go ahead and flash it. Okay, so the microcontroller's flashed. Let's go ahead and connect the servo. Okay, just plugged it in, and you can see that it's going a little bit too fast for the servo to handle the instructions, going all the way back and forth. So let's increase the time delays and see if that helps. Okay, we can see that we have successfully been able to connect the servo to the PWM. We were able to modify its position by using the PWM. The one thing I did have to do is I had to change the location of my 5 volts because I was causing the LCD to reset every time the servo was changing its position. Rather than applying the 5 volts from my ST-Link, this is the 5 volts here, I've elected to use a battery pack instead because I don't want any interference or back EMF from the servo affecting my circuit. So in this type of situation, you want to have the battery pack plugged into the red lead, and you also want the black lead from the battery pack, which is the ground, to be plugged into the black lead. But you also want the ground from the circuit to be plugged in to the servo ground lead. I'm actually having a difficult time getting both of these wires into this small connector, so it's just as good to put the ground from the battery pack into a ground on the circuit. And then you can take the pin from the PWM and put that into the yellow lead of the servo. And that way you'll have a voltage source that's external from the circuit, and the servo will not interfere with the circuit in any way. And as you can see with the external battery pack and the flashed microcontroller, we have a functioning circuit, and the external voltage source is actually what's recommended from the manufacturer of the servo. They recommend using battery cells to... I'm going to use a potentiometer to control a servo, where when you turn the potentiometer, the servo horn
will also turn in synchrony. The potentiometer is connected to the ADC, the analog digital converter. The number that is captured from the analog to digital converter is fed into a PWM signal to modify the duty cycle that will control the servo's horn. We first need to include the STM32 F0XX.h file, and that will contain all the registers that we need to control the features of the microcontroller. Next, we need to include the LCD functions. Next, we can include the ADC.h file, and finally, we can include the PWM function. In the main function, we're going to add some initialization functions from the LCD and setting up the LCD display, the ADC, and we want to select the channel for the ADC, which is specifying a specific pin that is going to be receiving the analog signal. And the PWM has to be set up with the proper Prescaler, PWM duty cycle, and the PWM period. In this case, we're using a Prescaler of 3 and a period of 40,000. To make sure that we're not going to start off the servo in extreme position, we're going to start off with the duty cycle at 1800, which is the low end for the servo. Let's go ahead and set up the LCD so it can display the number that is converted from the ADC. In this part of the program, we just need to add a label signifying on the LCD what we're going to be showing. I'm going to simply just put ADC on the display and nothing on the second line. Within the while loop, we need to capture the ADC conversion. And to start the conversion, we'll use the control register and the bit called ADC start. Right when you invoke the AD start bit, the microcontroller is going to start to go through a process of conversion. So we want to look at a particular bit that will be set by the hardware that is called the end of conversion. So let's put in a while loop that tests for this bit. The conversion has been completed. After this while loop, the conversion is ready. So we can actually use the number that is stored that represents this conversion. Specifically in this case, potentiometer's position. So let's go ahead and display this number on the LCD right after the ADC colon on the display. And that location is 5 on the first line, which is line 0. The converted number is stored in the DR register under the ADC1, and that is called the data register. We can simply just take that number and display it. Since the number will be a maximum of 4095, I'm only using 5 digits. Let's see if our conversion works and the number correctly displays on the LCD. You can build the program and then flash the microcontroller. It looks like there's an error, and it looks like it has to do with the LCD send an integer function. It looks like I used a parentheses around the actual parameters, which makes it look like there's only a single parameter. So removing these parentheses will hopefully fix the error. Let's try building it again and see if it works. There's no errors, so we can go ahead and flash the microcontroller. The microcontroller was flashed. Let's see if it works. The ADC number seems to be changing when I turn the potentiometer. Let's see if the range works from 0 to 4095. So it looks like it goes all the way up 4095. And it goes all the way down to 0. Now we want to do a little bit of math to make sure that the ADC number is not going to go outside of the constraints of the PWM duty cycle that the servo will accept. The ADC has a range from 0 to 4095 from one extreme of the potentiometer to the other, and the servo has a range from 1800 to 4200. That comes out to 2400, so our width of our PWM cannot exceed 2400, and it has to start at 1800. So we want to take the 4095 and reduce that range to 2400. So let's determine the coefficient we need to establish this range. So it looks like it comes out to approximately 0.586. So if we multiply 0.586 by 4095, we should get the correct range. Let's go ahead and plug this into our code where we show it on the LCD so we can determine if this coefficient is correct. Looks like there's no errors in the code, so we can go ahead and flash the microcontroller and test the output. It can immediately be seen that the number is different in the 800s, where it was before. It was in the 1300s, I believe. And let's go ahead and go all the way up and down on the potentiometer, and it looks like we have the correct range. It went to 2399 and down to 0. Now we need to add the 1800 to this number. So let's contain the multiplication we just did and then add 1800 to it so the order of operations is done correctly. This should shift the value on the ADC up 1800, so the range now will be 1800 to 4200. So let's test the range of the potentiometer. Let's see if we get 1800 in the low end. Yep. And 4200 on the high end. There we go. 4199 is close enough. So now let's use the servo as our output device. The new computation number, the ADC multiplied by the 0.586 plus the 1800, can be plugged into the PWM duty cycle portion of the function. This is a sub-function that I created just to modify the prescaler, period, and duty cycle. So let's plug in the 3, the 40,000, and we can copy and paste the number that we are displaying in the LCD, plug it right into the duty cycle input on that function. Even though I don't have the servo connected to the circuit, I want to build and flash the microcontroller anyway, so the circuit will be ready for the servo. To connect the servo to the PWM output, I'm connecting hookup wire from the signal in of the servo to the PWM out on the microcontroller. Connect the ground of the servo to the ground rail on the breadboard to serve as a common ground. This will provide the ground that the PWM signal will need. The servo will get its power from 4 AA batteries. Positive side will go to the servo, and the negative will go to the common ground. After plugging in the programmer to provide power to the circuit should function correctly. When the potentiometer is turned, the servo should turn with the potentiometer. If the outer potentiometer leads were wired in reverse, one going to VCC and the other going to ground, then you might have the opposite happen. When you turn the potentiometer one way, the servo may turn the other direction. I hope you enjoyed this experiment as much as Snickers did. Interrupts are probably the most important feature of microcontrollers. An interrupt will stop the main code from processing and switch over to a function that is responsible for the interrupt. When the interrupt function completes its task, the main code continues from where it left off. Right. Let's pretend that I am the standard program flow, which is the code in the main function, and each word that I speak is a piece of code in the never-ending while loop. My wife here is obviously the interrupt function. Her only responsibility is stopping me from processing or talking, and for her to process a few lines of code. In this scenario, she is responsible for receiving characters on the RX line. For each character that is on the RX line that reaches the RX buffer, the main code, me, will stop and her code will automatically begin. Once she has received the character from the RX buffer, she can store it in a variable, so I, the main code, can use that variable in some way. You need to be really careful with the code that you add to the interrupt function. In the scenario just shown where my wife serves as the interrupt function, the function simply reads the character in the RX buffer and adds that character into the global variable. The global variable would be something like an array or a pointer that stores all of the received characters, at least the ones that haven't been used so far by the main code. The code that stores the characters can be as little as a single line of code inside of the interrupt function. Remember that the interrupt function only fires if there's a character in the RX buffer, so you are ready to read that character immediately. You don't want to add a lot of code to the interrupt function. In the interrupt function, you may be tempted to take the character and send it out to a terminal, or worse, add it to an LCD, which is super slow. Here's an example of what could happen if the interrupt function tries to take the character and put it on an LCD. The lines of code to get a character on an LCD is not few. And if you have my book, you would know that because I teach you how to communicate with the LCD. So the time it takes to process that amount of code, and that the LCD requires a lot of wait time to communicate to it, you could miss characters coming in on the RX line that's coming into the RX buffer. Instead, let the main code handle the slow stuff. You can be assured that no characters will be missed if you simply add the characters to a global variable. that can be accessed by the main code. I talked about polling in previous videos on my channel and in my book, so if you've watched those videos or read that section of the book and tried the projects, you can see how much better interrupts can be. Can you imagine not using an interrupt routine and the main code having to wait for the RX buffer to be full? The time it takes for a character to be received by the RX buffer could be a long time if the characters are produced by a human on a computer or a terminal. We would never know when a character would be sent to the microcontroller. This would be a problem with using the polling technique. Your main code can handle a lot of different tasks, and when an interrupt happens for whatever the interrupt calls for, your main code can be swimming along freely doing its thing. But in the polling technique, it's just waiting for that character to be received by the RX buffer. The types of interrupts you have for microcontrollers spans the breadth of features in the microcontroller. That is to say, if the feature exists in the microcontroller, it probably has an interrupt for it. How do you access these interrupts or make them work? They're called interrupt vectors, which is just saying the location in the microcontroller that you can access the interrupt. It's like an address. With the microcontroller that I'm using in this series, the interrupt types include signals from external pins of the microcontroller, microcontroller exceptions, where you may need to handle an issue that your program is having, your own self-created interrupts, the independent watchdog for program robustness, timer interrupts, including the system timer, real-time clock, and all of the specific timers in your microcontroller. This can even be associated with features like PWM signals, infrared remote sensing, which is actually related to timers, and the many other ways you may want to configure your timers. Communication interrupts, including USART, which is Universal Synchronous Asynchronous Receive and Transmit, SPI, which is Serial Peripheral Interface, I2C or IIC, which is Integrated Circuits, which we'll be getting into later, and others, if your microcontroller has those communication features, such as CAN, which is Control Area Network, and USB, for example. ADC, Analog to Digital Converter, where the interrupt fires when the microcontroller completes a conversion from an analog signal, say 0 to 3.3 volts, and converts it to a number to, say, 0 to 1023. This is how many sensors will be set up in this series. You can have an interrupt trigger for almost anything you need in your program. I'm going to be showing ADC conversions, analog to digital converter conversions, from channel 1, which is this potentiometer's location on the microcontroller, and it will be showing its output on the LCD. The difference between this implementation of ADC and the previous one is the previous one did single conversions and it was polling in a loop. In this implementation, I'm going to be using interrupts, so we don't have to continually poll the ADC in the while loop. Instead, the microcontroller is going to know when the conversion is ended, and it can go to another part of the program to show the contents of the ADC, the data register. So let's see how we can do this. Let's go ahead and add the include files. And the first one is going to be the one for our chip, the STM32F0XX.h file. We'll include the LCD file, LCD functions. And the last file that we need is the ADC file. Before I continue, let me explain a little bit about interrupts. You can think of interrupts like an intention grammar for microcontrollers. So far, you've seen me use the while loop. The while loop will run these instructions over and over again, infinitely, while there's power going to the microcontroller. You may actually have many instructions within this while loop, and the while loop will continually run these instructions, and it'll start all the way back over again and continue going. This is probably fine for most circumstances. But with microcontrollers, a lot of these instructions cause the microcontroller to stop until this instruction has cleared some kind of flag. For instance, the ADC EOC, the EOC end of conversion flag, has to be true to continue on to the next instruction. So the microcontroller is actually stuck at this location waiting for the end of conversion flag to be set, and nothing else after this can be run. There could be really important operations happening after the waiting of the end of conversion flag
that the microcontroller will never see until that end of conversion flag is finally set. So when programming, it would be good to only add the important operations that need to continually execute within the while loop, the never-ending loop, and let the microcontroller execute the interrupts when it thinks it's ready. The way this works is that when the while loop is running these operations, so let's say it's at this particular operation right now, and then it's about to go to this operation, and then it runs this operation, and then right before it gets to this operation, the EOC flag, or the end of conversion flag for the ADC, is set. So what it does is it goes to the ADC interrupt function, and it processes all the ADC code that you need it to run. When you get to this particular point within this interrupt function, you'll already have the number in the data register, and you can use that number however you need within this particular interrupt. But as I mentioned in the AVR series, it's best to keep this portion of the code, the interrupt code, relatively small. So what you can do is you can take this data register information and you can put it into a variable, a non-volatile variable, so you can use it in the main code where you have the important operations. So when this code is complete, it will go right back to where it stopped processing and then continue, and then go all the way back to the beginning again and do all of the operations until it sees the end of conversion happen again. Just to drive this idea home, while in the while loop, it'll execute the important operations and it'll go back to the beginning. And let's say the EOC happened here, end of conversion. It'll go to the ADC interrupt. When it's done, it'll go right back to where it left off. It'll do the next operation. And let's say it happened again here. It'll go back to the interrupt and it'll go back to where it left off, and it'll continue over and over again. Let's say it happened right here. It'll go to the interrupt, come right back to where it left off, and then go back to the beginning and start all over again. So it doesn't matter where in the while loop it happens, where it'll pick up the ADC interrupt. It'll go to the ADC interrupt and then go right back to where it left off in the program. This is one of the coolest things you have with microcontrollers, because you can have some incredibly complex code within the while loop controlling a very sophisticated robot or whatever device that you are creating. And the microcontroller has a separate process that considers interrupts, whether it's a timer interrupt, an ADC interrupt, an external interrupt, or a software interrupt. It can handle that as a separate process and then remember where it was in the never-ending loop and continue exactly where it left off. So let's go back to the code and see how this works. Before we go to the code, let's add the components to the circuit. We'll start with the potentiometer, going to pin number 15. Connect one leg of the potentiometer to the positive rail and the other leg of the potentiometer to the negative rail. Make sure you have the programmer plugged in. You'll be ready to flash when the code is complete. So this is our never-ending loop here. This is where important code is going to be. The microcontroller is going to continually run this while the microcontroller is on. As you know, it first executes whatever is before the while loop. So we're going to be doing our initializations for the LCD and the ADC here. And interestingly, we're not going to actually put any code in here at all, because when you're using interrupts, you can have code in here, but what we're doing is we're only going to be converting the ADC value and executing that within the interrupt function itself. So we can add code into the while loop when we want it to do other tasks. Let's go ahead and put the initialization code in, and we'll put in the ADC initialization code. We won't have to make any changes to this initialization for the ADC. If you look at it, we're doing the calibration, we're setting the clock, which is required for the interrupt, and we're enabling it, and we're creating a specific sample rate. We also have the channel select, so let's go ahead and do that. And we're selecting channel number 1, which is where the potentiometer is located. In the ADC code we did previously, we did it in single conversion mode, which means that we had to start the conversion, that would be AD start, setting the AD start bit, and then we wanted to wait until the EOC, the end of conversion, is set. And this is the kind of thing we don't want to do. We don't want the microcontroller to wait for anything. We want the microcontroller to continually go and do important code in here and not have to wait. We want this to be done in another part of the program. So this is what we did before. And then what we did is we used the contents of the ADC data register. And this would happen over and over again. And that is called polling. We're polling the ADC. So instead of doing single conversion mode, let's go ahead and make it continuous conversion mode. So it'll always do it by itself internally and always convert without us having to poll it. And to do that, we need to access the ADC configuration register and set the CONT bit. And the CONT bit, we didn't set it, so it automatically went to single conversion mode before. So in this case, we want to put it into continuous conversion mode. by typing ADC1, accessing the configuration register, and we're going to set the bit for continuous conversion mode. Now we need to enable the interrupt. We have to tell the configuration, the ADC, that we want interrupts to be enabled, which is located in the ADC IER register, the interrupt enable register. And we have a few choices. We have the EOC IE, which is the end of conversion interrupt enable, and we have the EOSEQ IE, which is the end of sequence conversions interrupt enable. We also have the OVRIE, which is the overrun interrupt enable. From my current understanding, this is the EOC, which is single conversion mode, or single conversion, which doesn't mean it's single or continuous. It means that it's going to do a single channel. And if you have the EOSEQ, which is a sequence, it is going to fire, the interrupt will fire when a sequence of conversions is completed, which means multiple channels are finished converting. So you can process all of the channels at one time in this interrupt. So if you have two channels, this will fire twice, so you can process each conversion separately. And if you have this one set and you have two channels, this will fire only once, and you can take care of all the channels at one time. The overrun is if there is a conversion happening, and in the middle of that conversion, another conversion wants to start. So this will fire if that happens. I'm not going to be using this one, but I will be using these. And since I only have a single channel, I'm going to be using this one in this particular tutorial. So the register is the IER register, and we're setting the EOC IE bit, the end of conversion interrupt enable. So when the interrupt has completed, it'll go straight to the function that handles that interrupt. We're at this point. Let's go ahead and put in that function, and that is the handler, the interrupt handler. The name that is used for this interrupt handler is very important, because if you don't name it exactly this, it will not find it. When the microcontroller fires the interrupt for the end of conversion, it's going to find itself within this particular function. So let's keep this here and get back to it after we do some more setting up for the ADC. Now there are two more instructions we need to add, and that has to do with the nested vector interrupt controller, the NVIC, which is actually a part of the CMSIS core library. We have to add the NVIC functions because all of the interrupts are handled by the NVIC. The two instructions you'll need is the NVIC enable IRQ, and we're going to be using the ADC1 IRQN. You notice that when I was typing this, you'll see the comp IRQ, and you have the one without the comp. And if you use the comp, all it does is it defines this anyway. So you can put in the comp if you want, and it'll do the same thing, because it's just going to replace the comp with IRQN. And if you look at what the IRQN is, it is just equal to the number 12. That's it. You could actually put the number 12 in this spot, and it'll do the same thing. Let's go back to that. So let's put on the next one. NVIC, and this one is going to be setting the priority. And we're going to put the same IRQN in there, and we're going to set the priority to 0. And I don't have any other interrupts going on around here, so I can use a 0 here, but you want to change this number to what priority you believe that the multiple interrupts will have. And since I'm only using the ADC, I'm going to put it to 0, but if I was going to, say, set the timer interrupt or other interrupts, I could change the priority of these interrupts. And the last thing we need to put into the beginning of the main is we need to start the ADC. Just like we were doing in the while loop, starting it in the while loop, we're going to do that outside of the while loop because we're doing it in continuous mode. And we're just starting in the continuous mode, so it continually goes over and over again. And the ADC start is located in the control register. So now that we have it configured properly for continuous mode, interrupt enable, and we're setting the NVIC interrupt functions, we can go ahead and start putting the code into our handler. And in our handler, I'm just going to simply set the LCD, set the cursor location, because we're going to be, you know what, let me put in the initial thing we're displaying. We're going to send 2 lines, no delay, and we're just going to put ADC on the top and nothing on the second line. So at this position here, we want to put the number of the ADC, the value of the conversion. So we'll set the cursor location first, and it's 4 and then 5. So I'll put it 50, and we'll send an integer. And the integer to be displayed will be the ADC DR, the data register, because we should have that since the conversion has been ended or completed. And the max length, I'll just put 5 here. Should only be 4 digits, but I'm going to add 1 to it just in case. Let's go ahead and build the project and see if it still works. I have no errors. Looks like I have an error and it says ADC DR. I forgot to the 1 after the C, so let's go ahead and do that. All right, let's try it again. Looks like I have another error. What is that one? And it looks like I have an issue with the NVIC set priority. It looks right. Oh, you know what? Priority. Okay, I forgot an R here. Let's put that R in. It almost looks like it's correct. Okay, now let's try it again. Okay, no errors that time. So let's go ahead and flash the microcontroller and see if it still works. Okay, the microcontroller has been flashed. Let's go ahead and see if it changes, and it looks like it's working fine. So now that we've tested the microcontroller and we know that it's working, let's go ahead and go back to the code and put this code in the .h file for the ADC. So I'm going to open up the ADC and I'll make another function called setInterruptMode. I'm not going to be bringing anything in, I don't think. So let's just set our code block. We'll take all the information that we just created. Control X, cut, and we'll bring it into here. And I wouldn't be putting the continuous mode on unless I was using the interrupt at this point. I can't really imagine how I'll use it later, but at this point, I think I'm going to set it this way just so it'll be easier to put into the main program. I also probably want to set the non-continuous mode when I'm just doing standard pulling ADC conversions. So I want to take all of this out, and then I want to use the AND NOT to make sure this is a 0. So it unsets this particular bit. So it's in single conversion mode. So I'm going to call this polling mode. All right, so let's go ahead and save that. And in our main, we can just use ADC set interrupt mode. Okay, so let's go ahead and try this and see if it still works. We have no errors, so let's flash the microcontroller. Okay, the microcontroller was flashed. Make sure it still works. I'm going to show you how to bring in analog signals to the microcontroller on 2 different channels of the analog to digital converter. So you can convert channel 1, and in this case, I'm converting channel 4 as well. And I'm using potentiometers to show an analog signal coming into the microcontroller. The conversions for the analog to digital converter will be done through interrupts, and you will see that the conversions are listed as ADC1 and ADC4. So if I change the ADC1, which is the channel 1, you can see that the channel 1 does change, and the channel 4 changes independently of channel 1. I am only using these potentiometers in place of what would normally be used on these ADC channels, such as sensors. Another example would be having a completely different type of sensor here, like a temperature sensor, and maybe a sensor over here would be measuring the voltage of some part of a circuit, or a pressure sensor or something like that. In most circumstances, you'll need to use more than one channel on the ADC to bring in many sensors. So you're going to need to know how to receive those values from each channel separately. So let's go ahead and set up the circuit and go into the code. Oh, and I also added resistors here instead of just straight wires on one of them to show you at the low end how it affects the value, and on the high end how it affects the value. It doesn't go all the way up to 4095, and it doesn't go all the way down to 0 because there's resistance on each side of this. So it's as if this isn't getting the entire range of the voltage from the power rails. I would recommend putting small resistor values on either end so you're not putting the pin directly to the voltage extremes. Okay, so let's set up the circuit, and then let's see how we can accomplish this with code. Let's see what pins we'll need to use to access the channels for the analog to digital converter. Okay, we're currently using PA1, which is channel 1, ADC IN1. That's on pin number 15. And because my potentiometer is so large, I need to go a few tie strips over. I don't want to use the F because that's not the ADC. So I'm going to use the ADC IN4, which is the channel 4, and that's on pin number 20. So let's put one of the potentiometers on pin number 15, which is the ADC channel 1. Connect the 2 outer leads of the potentiometer to the plus and the minus rail. The other potentiometer to channel 4 of the ADC. And on this potentiometer, I'll be adding resistors to the power rail. Okay, let's start coding. The first thing we need to make sure is that we have the correct libraries installed or added to this project. The first thing we want to make sure is that the header files are loaded within the skeleton code. Is initialize all of the features that we're using, the ADC and the LCD. And we want to set up the LCD display. And I want to put something on the LCD that explains what we're going to be showing. So let's go ahead and do that now. We're going to use the function that we created called send2lines, which allows us to put 2 lines of information on the LCD all in one function. This doesn't need to happen in the while loop because we only need it to display once on the LCD. Once it's displayed, it'll stay there. So I'll show the ADC1 on the first line and ADC4 on the second line. And I'm calling it 4 because I'm using channel 4, and that just indicates to me that the number next to it is going to be the channel 4. Now let's do the initialization for the ADC. And I want to invoke the interrupt mode. We have a special function for that. And the channel select that was created in the ADC tutorial, I can select channel 1. And because I'm ORing this, the channel select is using the OR bitwise operation. I can go ahead and use the same function to set up channel 4 as well. So this tells the microcontroller that I want to use channel 4 and channel 1 as channels to receive analog information. And then I can go ahead and start the ADC. Since we're using interrupts for the ADC, it's going to go to a separate function because it's not going to be polling within the while loop. Let's set up that function now. The specific ADC function has to be called ADC1 IRQ handler. And we're not bringing anything in. So when the ADC has completed a conversion, it will jump right into this handler. And one thing to note is that we're using, within the interrupt mode, we're using the interrupt end of conversion, i.e. interrupt enable, end of conversion. That will end each conversion of each channel. So it will come into this function when each of the channels are converted. So while the microcontroller is running, when it's converted channel 1, it'll go into this handler and run the code within it. And then when it's complete, it'll go back to the while loop. And when channel 2 is completed converting, it'll go back to the handler and then run the code. And as far as I know, there's nothing in the microcontroller registers that gives us a status of which channel it has converted. So we're going to introduce a new variable that tells us which channel it is on. So I'm going to introduce a new integer to the program called channel. And this will tell me which channel it is currently on. The channels will be converted in order of channel, the smallest channel to the largest channel, like channel 1, 2, 3, 4. So it'll do it in that order as it is converting, unless you change the scan direction. The scan direction is in the configuration register, CFGR1, and the scan direction is on bit number 2. So the scan direction bit means that upward scan from channel 0 to channel 17. It'll scan in that direction. If you set it to 1, then it will backward scan from 17 to 0. In this case, we're going to keep it as an upward scan, and that is the default. It's 0. So we don't need to change that register. So within this function, we want to increment the channel variable by 1. But when it gets here, this channel, since it's 0, the first time it comes in here, it'll be 1. So we want to first grab the data from the ADC. And you could be tempted to actually show the ADC data on the LCD within this function. But the problem with that is the LCD functions and putting things onto that display takes a long time. And it takes so long in microcontroller terms, not human terms, that many of the ADC conversions will have already happened by the time it puts one set of information on the LCD. So we want to just grab the data and then display the information within our while loop. So let's go ahead and grab the data. And we're going to have to create another volatile integer for channel 1 data. And we'll do the same thing for the channel 4. So if the channel is currently at 0, then let's grab channel 1 data. And it will equal ADC1 DR, the data register. We're going to do the same thing to channel 1. If it gets to channel 1, we're going to get the channel 4 data. And the reason why we're incrementing 1 is because we're only setting channel 1 and channel 4. If we had something in between this, like channel 3, even if it was channel 3 was after channel 4, it'll still get it in sequence of channel 1, channel 2, channel 3, channel 4. But if we only have it set up to do channel 1 and channel 4, it'll only want to get channel 1 or channel 4. It's not going to try to receive the channel 2 or convert the channel 2 and convert channel 3. It will only convert these two. So when it comes into the function for the handler, it'll start out with the first one being channel 1. The next time it comes over here to the function, the handler function, it'll receive the channel 4 conversion. This is only a variable. The channel variable is only a variable to determine what data is picked up at what time it gets to the handler. Now in the handler, the channel keeps incrementing upwards. So I'm going to add another condition. I want it to do it before these conditions because I want it to grab 0 or 1. If the channel is equal to 2, then I want it to start over. So, because it's going to, after it does 1, it's going to increment the channel again, and it will be 2. So the next time it comes over here, it'll be 2, but I want it to be 0. So really, it's just toggling between 0 and 1. So I think we're finished with the handler function. Now we can display the data in the while loop. So we have in line 1, ADC 1, and line 2, ADC 4. So let's go ahead and set the cursor location, 5 and 6. So 6th position on the line, and we'll start out with line number 0, and we're going to send an integer, and the integer is going to be channel 1 data, and I'll give it five maximum digits, and we'll do the same thing for channel 2 data. We'll go to line number 1, and we'll just show channel 4 data. So it's constantly putting the information to the screen, but it's doing probably a lot more conversions before it actually gets to the screen. So you're still going to see it very quickly, but the proper data should go into the right place on the LCD. So let's do a build and see if it works. Looks like there were no errors, so that's a good thing. So let's go ahead and flash the microcontroller and see if it works. Okay, the microcontroller was flashed. You can see we have ADC 1 on the first line showing a number, a value, and ADC 4 on the second line showing a value. And if I change the first channel or the first potentiometer, you can see that the first ADC changes its value. And if I go to the next potentiometer, you can see that that also changes its value. One thing I didn't realize I did when I was putting the circuit together was I switched the leads to its negative and positive value. So the rotation that I use to turn it it goes in the opposite direction that I would think it does. So you can just change these leads. Like this lead would have to go to the negative and this one would go to the positive to get an intuitive rotation compared to the value of the ADC on the LCD. I want to show you a couple fixes that will enhance the output on the LCD display. In the previous videos, you'll notice that when I would, let's say, change the value, let's say for ADC1, and when I got lower in the value, you'll notice that there would be an artifact, a number here at the, let's say, 4th digit. You can see that I fixed that. And in the previous videos, what I would do is I would erase the number first, and then I would add the number, but that would cause the number to be very faint or almost transparent, and it would be very difficult to see the number. But there was an easier way to solve this problem, and I'm solving it within the actual library itself, where when it creates the string, or when it prints the string of numbers or characters, it would also print a space afterwards. So whatever was there in that location, it would be erased by the changed string of characters, or this changed next string of characters. This will really only solve the problem for numbers changing. Like if there was a number counting down, and the number counting down would be erasing as it counted down, and it would erase the next digit as it got that much lower. But if it was a string of characters, just regular string of characters, then it would erase the last one. It wouldn't erase the entire line. That's something that you still need to do. It makes more sense to have this feature for numbers counting down or numbers changing. So let's go ahead and see how you do this. Okay, we're inside of the LCD functions header file, and in the LCD send a string function, you'll notice that I added a character. I'm going to comment this out so you can see what happens if I don't do this. So I'm going to go ahead and go back to the main. So I'm going to build so there's no errors, and I'm going to go ahead and flash the microcontroller. So let's go ahead and change it to 4 digits. And as you can see, when I go down, we're in the 500s now, but the 8 was left over as an artifact. So let's go ahead and put that back in, put that space back in. You'll see that change. So going back into the LCD functions, we'll uncomment that out.
The more I think about this, the more I think that we should actually not put it in here, because when we're sending a string, we want to send it without a space at the end, because we may have an instance where we want to maintain whatever is after this particular string of characters on the display. There may be something already displayed on the LCD, so I don't want to put it here. I think it makes more sense to put it where the number is. And my first thought is just to put a space right here. So what would happen if I just put a space after the string format of the integer? If I'm going to do that, I should also do it to this one right here, but I'm going to test it first for the integer and see what happens. There's no errors, and I think that's pretty obvious. You'll also notice that I have a +1 here in the max length of digits, and I did that because of a comment that I got on YouTube specifying that I needed to put a +1 here to reserve for the null character, but I'm not really sure if it's needed or not. I'm going to keep doing the testing, and if I see over time when I am having more digits being passed to the LCD, and if I see any sort of problems with it, I'll either take it out or keep it in, or actually maybe even add another one because of this space. So I'll just keep looking at it and see, just to make sure of it, it works fine. So let's go ahead and test this out. We've already built the program, so I'm going to flash the microcontroller and see what happens. I'll adjust channel number 4 this time. It's this one right here. Yep, so it works. And so let's try it with a float. I'm going to go ahead and pass this number in as a float instead of an integer, and we'll see if it still works with a float after we make the changes. So back in the program, let's go ahead and put a space after the float and do a build and see if we have any errors. No errors. Let's go ahead and flash and see if it works. Actually, I need to still do the float. I didn't do that yet. So send an integer. I'll do that for data channel number 1. So I'll send it as a float. Send a floating point number, and then we want the floating point number to be displayed, so that's going to be channel 1 data. And then the max length of digits, I'm going to just put 5. I'll make it 6 because there may be a decimal in there, and I want to see the decimal happen. I'm going to comment this one out because I want to put this back in there. Let's go ahead and build and then flash the microcontroller again. Okay, you can see that channel 1 has been changed to a float. It has a 0.0. Obviously, it has a 0.0 because there's no decimal in the output of the ADC. So let's change, see if it actually moves. Okay, it does not delete the artifact. So let's see why this does not work. So we put the space there, but really, after looking at it and investigating it, this is a floating point number, and there's going to be decimals, and there really isn't any artifact. The 0.00, the other 0 that happened after it, is just because we're reserving that number of digits for this float. So you're always going to see those extra zeros at the end because the number really isn't changed. It is the real number, is it? So we can actually keep the floating point number just as it is. When you specify a number of digits, it's always going to show those number of digits, and you don't want it to show anything else because that's what you've created. So changing the LCD send to an integer, or send an integer, and putting a space after that really is the only thing we need to do. I'm going to show you how to create an external interrupt using a standard push button switch. An external interrupt is where you use a pin of the microcontroller as an input and you provide a signal to that pin, and the microcontroller will handle the interrupt by going to a special function where you can add code when this interrupt is fired. This is an alternative to the polling method of testing the input on a pin within the while loop, the never-ending loop. The pin that will be used for input is pin number 50. Pin number 50 is port A, pin number 15. The switch in this case is pulled to ground using a 220K resistor. I added a small resistor here, which is only 330 ohms. Just to add a little bit of resistance. And when the button is pressed, the pin will receive a high reading, which is on the plus rail. So when the button is pressed, it will go to this positive rail. When the button is not pressed, it'll go right through to the minus rail, which is pulled down to ground. When the button is pressed, it will increase. And you'll notice that it increases quite a bit on each button press, and that's because the button bounces. And the interrupt is extremely sensitive, and we are configuring the interrupt to increment a variable for every rising edge. So this particular type of experiment would be better on a non-mechanical clean signal coming in. You can eliminate the bounce
in the interrupt, but that will not be the subject of this particular tutorial. The circuit is actually the same as the previous push button videos. We're going to add a resistor to that pin pulled down to ground so the pin is not floating. When the button is pressed, it will connect to the high side or the plus rail. The first thing I'm going to do is just include my standard include files. And I'm going to include the LCD functions. And we want to set up the port A, pin 15 as input. So let's go ahead and do that first. And this is stuff that we've already learned how to do. I'm going to use the reset clock and control register and the advanced high performance bus, GPIO-A, enable. Now we're going to change the mode register for the GPIO-A to serve as input. And we want pin number 15. And we will also want to set no pull up, pull down, since we're doing that externally anyway. At this point, we might as well set up the LCD. And in the beginning of this, I'm going to put a not exact time delay, and I'm just going to put maybe 10,000 in here. And what I'm doing is I'm creating a very short time delay before the LCD initializes. I've noticed when I plug in the circuit for the first time, the LCD is not really ready until a little bit after the microcontroller sends this initialization code. So I'm going to add just a little bit of time delay, give the LCD some time to get ready. I'll set up the display, and I think I want to add some information to the display. I'm going to call it just A15, since it's a description of port A and pin number 15. In the second line, I'm not going to put anything. Let's stub out the interrupt function first, just so we can... Actually, let me do the NVIC first. The nested vector interrupt controller. And we're going to enable an IRQ, which is going to be the external interrupt. And we have some choices here. We have 0, 1, 2, 3, and 4 through 15. And because we're accessing the pin number 15, we're going to be using this particular interrupt. And now we need to set up the priority for the same external interrupt designation, and we're going to set priority to be 0. Priority, you have the option of going from 0 to 3, and 3 being the lowest priority, 0 being the highest priority. I'm not sure if that is actually correct, but I'm going to assume that is correct at this point, and I'm not using more than one interrupt in this case anyway, so it doesn't really matter how I set the priority. So now let's go ahead and stub out the void. And the reason why I wanted to do this first is because this right here actually is part of the name of the function for the handler. So I'm going to go ahead and copy that without the n at the end. And these functions for interrupts have to start out with void because we're not returning anything. We wouldn't be able to know what it's returning anyway, so we don't need to worry about that. I'm going to put in the external interrupt 4 through 15, IRQ, and then handler at the end. And then we're not bringing anything into this, and just like the return, we wouldn't really have any access to put parameters in that I know of, because the microcontroller handles calling this particular function when the interrupt is fired. Now let's get into the external interrupt specific control, how we control the way it interacts with the pin and how it picks up a signal. The first of these is the interrupt mask register, and we need to know which line, channel, or pin we're using. In this case, we're using pin number 15. And in this case, because it says 0 is when line X is masked, we want when the line X is not masked. So we want 15 not to be masked. So let's go ahead and set the mask register bit number 15 to a 1. The next control we need to consider is the rising trigger selection register, where we determine the way we pick up a signal is on the rising edge. The way we set up the circuit, the pin is idling at 0 volts. So it constantly sees 0 volts until we press the button. And at that point, the signal looks like this. It's bouncing, and then it finally reaches its 3 volts. It's going to find every single rising edge that you're going to be able to give it. And when a button press happens, you'll notice that there's a rising edge here. There's a rising edge right here. There's a rising edge here. And there's a rising edge here. Different buttons with different mechanical properties may have different outcomes. But the buttons I'm using have rising edges. It's going to capture every single rising edge that it gives you. If you want to put a push button on a pin using an external interrupt, then you're going to have to figure out a way to determine a true button press. So with that out of the way, let's go ahead and add the external interrupt rising trigger selection register. And to enable it, we're just going to put a 1 in bit number 15 for that register. Another register that we may have to consider is the system configuration register that controls the external interrupt configuration. And in my experiments, I've noticed that this doesn't really have any effect at all. I've commented it out and ran it, commented or uncommented it, or invoked it, and the results are exactly the same. So I'm going to put it in anyway, just because it doesn't seem to harm it any. So the way you use it is they have the configuration for each port, but you need to specify which pin, and that is what position or bit position that you use the specific bits within those positions. And you have many choices. You actually have 4 choices for the external interrupt configuration. You have the 1, which is from 0 to 3, 2 from 4 to 7, 3 from 8 to 11, and the last one, number 4, is from 12 to 15. And we're going to be using number 15, and we specifically want the PA. So it's going to be 000 in those bits. So let's go ahead and configure that one right now. And you'll notice that there is an array of 4 positions here. So you can, it's going to be from 0 to 3, and ours is going to be the 4th one. So it's 3 with an indexed, 0 indexed array. And we're going to select number 15 for PA. And the reason why it doesn't make a difference from my testing is because it's all zeros anyway. So it's going to be at the reset value. Now let's go to the function for the handler. This is where the microcontroller is going to take you when the interrupt fires. But you'll notice that it'll fire for all the lines between 4 and 15, all those channels or all those pins. So we need to determine which pin is being fired at the time. And the external interrupt pending register has that information. We are interested in the PR15. If we see a 1 in that bit, then the selected trigger request occurred, meaning that particular line has received a rising edge with the way we're controlling it in this particular program and circuit. So let's go ahead and test for that bit. If the 15th bit in the external interrupt pending register is true, then it found a rising edge. So now we've tested for the bit, and if it is true, we'll run this code. We have to reset this bit after we know that it has actually been fired. So to do that, we just do or put a 1 in that same bit. It seems odd to do this because it already has a 1 in it, because it wouldn't have gotten here unless it had a 1. But according to the datasheet, the request is reset by writing a 1 in the pending register. The datasheet really isn't very clear about this, and it took me quite a while to figure this out. But after doing some testing, if you don't actually add this line, as per the datasheet's recommendations, it really doesn't work. So this is actually needed. So in this particular case, I want to know if it's been fired or not. So I'm going to add another variable, and it's going to be a counter. I'm going to use a volatile int because I want it not to be optimized out. And I'll call it port a pin 15 counter. And right in here, I'm just going to have an increment by 1. So if it got to this location and it actually is the line number 15 has been fired, then this counter should count up. And I don't want to put anything else in this area because I don't want it to cause any delays. So I'm going to keep this very short just have this. I could just have a flag in here stating that a rising edge was found, and then I can deal with it in the while loop. But I just want to see a counter, and that this is easy enough to put it right inside of the interrupt function. So in the while loop, I'm going to display that counter on the LCD. We'll send it to the LCD as an integer. So everything should be good. Let me go ahead and build, and let's see if everything is good. Looks like we have an error. Let's take a look. RTSR, it's probably not the way to spell it. Oh, I see, because I have an underscore here. Put a hyphen. Should work now. Build it again and see if we have any errors. No errors, so I'm going to go ahead and flash the microcontroller and see what happens. The microcontroller has been flashed, and you can see that we have the correct label, A15:, and it has a 0. Let's see what happens when we press the button. You can see a number 2 appeared, 3, 4, then 7. So it is getting every rising edge whenever I press the button. And you can see that it is also picking up all the bouncing. Okay, so that is how to use the external interrupt to receive a digital signal from a pin. Let's add another button to the microcontroller so I can show you how to separate those two button presses, those two interrupts. And it's going to happen within the same interrupt handler, but on a different line or a different pin. The pin that I will use is located at pin number 44. Pin number 44 is here, port A, pin number 11. Let's add another push button to pin number 44, exactly the same way we did with the other push button. Now that we've added the button to the circuit, I'm going to go ahead and add another line to the LCD that describes what we're going to be showing. And that's pin number 11 on port A. And let's go ahead and get the pin 11 on port A set as an input on the GPIO. We don't need to enable the port again because we've already done that here. It looks like I actually did something wrong here. I'm only specifying 5, not 15, and it probably looked like I was doing 15. So I'm going to change that. Okay, so that's correct. And now I want to duplicate these two for the pin number 11, the interrupt mask register and the rising edge register, the rising trigger. So I'm just going to change these to 11. So now we're enabling pin number 11 on port A for input, and we're adding the interrupt, external interrupt control parameters for pin number 11 as well, or line number 11. This doesn't have to change because this is good for lines 4 through 15. And in here, the handler, it's going to handle everything between 4 and 15. So we need to duplicate this one. But we also need a new counter too. So let's make a counter first. And we'll just call this one port A pin 11 counter. I'll duplicate this one. I need number 11 here to test the pending ready bit. And we'll do this one over here to reset that. And we'll use the new counter. And now we need to display the counter in the while loop. So this is going to go on line 1, and we'll use the 11 counter. So this is all that should be needed. Let me go ahead and build and see if it builds correctly. Looks like it worked. The microcontroller has been flashed. And when I press the pin number 15 button, let's see what happens. Okay, so the display is showing the counter going up when I press the 15. And when I press the pin number 11, let's see what happens. Okay, so it looks like we have a successful implementation of an external interrupt using push buttons. One major caveat to using the external interrupts and assigning pins to these interrupts is that you can only use a single port for the line that you select. Say you're selecting line number 15. So the pin associated with 15, the port that you select, like port A, and you select pin number 15. You cannot use port B, pin number 15, or port C, pin number 15. You can only use port A, pin number 15. If you remove port A from pin number 15 and you use port B for pin number 15, then you're able to do that. You can see in this figure 22, external interrupt event GPIO mapping, that the external interrupt number from 0, 1, all the way to 15, you can see that they're all tied. All the ports are tied to a single interrupt line. So you need to choose between which port that you want to use for that particular line. In these videos, I've only used port A.
And in my tests, I've only been able to get port A to work. I'm not actually sure why. I've done many tests with port B, port C, port F, and I've connected them to internal interrupts, not interfering with port A and the pins that I'm using. So I'm not actually certain if I'm doing something wrong, or maybe that I have a damaged chip on my breadboard, but I was successfully able to do it with port A. So for that part of the experiment, I think it was a success. But because I wasn't able to use a different port, I failed in that respect. And I was doing the testing for probably about a week now, so I'm not going to continue with the tests for a different port. I think I've done a sufficient job in covering interrupts in general, but I will probably revisit interrupts at a later time because I want to start to cover other features of the microcontroller. If you're able to get another port to work on a different line or different pin, let me know in the comments. I hope this helps. Thank you for watching.
It's time to liberate the LCD. I'm removing the LCD for a few reasons. I want to have more space to add more devices, so I'm going to need the breadboard real estate. I need more space and more tie strips to be able to do what I want to do. The LCD also doesn't allow for enough presentation of information while doing my projects. I only have so much room on the LCD to be able to show what I need to show. And the LCD is mainly used for a display for the end user of the final device anyway. It's not really meant to be used as a debugging device, although it works for that. But my biggest reason that I want to remove the LCD now is that the circuits that I add to the breadboard, I want to make them as simple as possible for the beginner. My whole approach in teaching and learning myself is to work with the simplest and most minimal circuits as possible. So now we have all of this free area, breadboard real estate to use for future projects. And I'm not really too keen on these wires hanging around on this location of the breadboard. This was created because we needed space for the breadboard on this area for the LCD. So I'm going to add the wire connections back from this power rail to this power rail like I had it before the LCD was installed. And I'm going to remove these wires so I can clean up this top area here. And we'll be back to a very basic and simple circuit. Remove the two wires, pins 64 and 63, to the unconnected power rails, and now connect the two remaining power rails together. The circuit should now look like this. Pin number 1, which is a positive power connection, should be connected to the positive rail. The analog to digital converter power should be connected to the power rails. The other power connections, 31 and 32, should be connected to the power rails, and 64 and 63 should be connected to the power rails. All the power rails are connected together from this portion. This breadboard is connected to this breadboard's power rails using these two wires. The power on this part of the board is being provided by this power rail, and then this power rail is connected to the remaining breadboard with these two wires. So now all of the power rails have power going to them, and the entire board can be powered. The main power, of course, is coming from the ST-Link going to these two main power connectors. When you've finished installing the STMStudio, you'll be presented with a screen that looks similar to this, where you have a variable viewer here, and you're going to have the variables listed in this location, and you have the option of how you want to receive the information from the microcontroller using JTAG, the SWDIO, the SWIM, and the ST-Link. The ones that I'm going to be using, or the one that I'll be using, is the ST-Link SWD. I'm not going to get into this program in any depth right now, because as I do the projects, I'll show you how to use this program. And in this video, we will start with a quick example of the ADC, the analog to digital converter, and the potentiometer like we did before. And we will monitor the data register of the ADC using this program here. So let's go ahead and set up the circuit for the ADC, the potentiometer, on port A on one of those pins, one of the port A pins, like we did before. Add a potentiometer to pin number 15, and I'm adding 330 ohm resistors to each high and low leg of the potentiometer to provide a little bit of protection for the pin on the microcontroller. Okay, I'm starting with some skeleton code here, an empty project. Make sure that when you create your project, you'll have the adc.h in that project. Okay, let's put in the include files. This is our standard include. Include the adc.h file. So let's initialize the ADC. And we're going to set it up as the interrupt mode. And the channel we're using is channel number 1. And to get this ADC to start collecting data, we have to use the AD start bit in the control register. In the interrupt mode, look at the ADC file. In the interrupts, we are using the ADC1 IRQN. So I'm just going to copy that so we can create our function. Void ADC1 IRQ handler, void. And inside this, I want to put this into a variable because I want to view this variable in the STMStudio. So we'll create a volatile int. We'll call it ADC data. And over here, we'll take the ADC data and assign it the ADC1 data register value. So whatever is in the data register, we'll see it in this variable. So we can monitor this variable in the STMStudio program. So let's go ahead and open up the STMStudio. Well, first we need to build the file. Let's see if we have any errors in it. We have no errors. So we can go ahead and flash the microcontroller. So the microcontroller should be flashed. Now that we have the microcontroller flashed, we can go ahead and start the STMStudio. And the first thing we want to do is we want to import a variable into this location here. So you can press the right button, import, and at the ellipsis, just click on this, the bin file, and you want to use the ELF, the ELF file. And the ELF file has all of the information that you need within the program that we just created. And the one we want is the ADC data. If you remember from the file, this is the variable that we created, the ADC data. Going back to the STMStudio, once you've selected this, you can click on the import, and you'll see that it added it here, and you can press close. And you also want to send this variable to the viewer. You can have many variables in this location, and you can specify which ones you want to actually view at the time. So you press the right button and you send to var viewer. You're not going to see anything right here because the potentiometer is probably a little bit too high of a value, but also we haven't started playing it yet. So I'm going to go ahead and put the lower value at 0, put the upper value at 5,000 because I know it's going to be 4,095, and that's going to change your vertical axis. You can go ahead and play it, and you'll see that we have data at between the 2,000 and 2,250 range. And if I go to the potentiometer and I start changing the potentiometer, you'll see that it also changes in the variable viewer, that particular variable. You can also look at it not just as a curve, but you can look at it as a bar graph and as a table. So you just see the value here, which is what you would have seen in the LCD. So from now on, in the tutorials that I'm going to show and the projects that I include in this tutorial series, we'll be using this resource to view the variables that we put into the programs. This resource will be indispensable when we're working on new projects. We will be able to add quite a few variables to our programs and peer into how the program is performing as it runs on the chip itself. In this video, I'm going to explain the I2C communications protocol as it relates to the ARM microcontrollers, specifically the STM32. The I2C communication protocol allows a microcontroller to communicate to many devices, specifically as many as 127 devices. There are so many different types of devices that can be used, which include devices like temperature sensors, accelerometers, display devices, a device that you make yourself, and so many other devices because the I2C is such a popular communication method. And the reason why you're able to communicate to so many devices on 2 wires is because each one would have an ID, and each of these devices would have a unique ID. Some devices have IDs that are hard-coded in their circuit, and some of them have IDs that are configurable. One example is digital servos, because in a microcontroller project, you may need multiple servos, many of them, and each servo would need its own unique address or ID. So the digital servos allows you to create that ID programmatically. And this is done with only 2 wires from the microcontroller. And these 2 wires are SDA and SCL, the data and the clock. Each one of these devices will also have a data, and a clock that connect to these two wires. The fact that you can put so many devices on two wires communicating with the microcontroller is what makes this protocol so important and so versatile. One very important consideration, however, is that when you connect this type of protocol in a circuit, you have to include two pull-up resistors, one on each line. I will use a value of between 4.7K to 10K of resistance. And these values will be good for the number of devices that I have being used on the protocol. But remember that if you increase the number of devices and you vary the speed that you wish to communicate on this line, you may need a different resistor value. This resistor value is dependent on the capacitance on the line. The formula to determine the resistor value is equal to the time constant, which is going to be 1000 nanoseconds in this case, over 0.8743 times the capacitance measured on the I2C lines. Now let's talk about how this communication is established. In most cases, the microcontroller will be the master. I2C can be used in master or slave scenarios. The master initiates and stops the communication. The master will establish a start state, and then the master will either read or write from the slave devices, and then the master will stop the communication. I'll draw the SDA with a red line, and I'll draw the SCL with a blue line. And let's say that this device has an ID or an address of 1, and this one has an address of 2. In I2C, an address is the same thing as an ID. So when you're communicating to a device on the I2C line, you have to notify which device that you want to speak to. We can't forget the resistors. I want to make sure we put those in there. So let's go over a scenario where I read information from a device. Say I wanted to read, let's say the device 1 is a temperature sensor. So it gives us degrees Fahrenheit, or gives us some number that could be calculated to a temperature. So the first thing we need to do is the microcontroller needs to become the master, and this device, all these devices connected to the I2C are slaves. So we'll start with the microcontroller establishing the communication. Establish a start condition, and the microcontroller will need to determine if this is going to be a read or a write. It has to establish a direction for transfer. And we're always going to start with a write because we need to specify which device or which slave that we want to talk to. So we want to put it into write mode and send the address. And in this case, it's going to be number 1 because we want to talk to the device, the temperature sensor. The data sheet of the temperature sensor will provide all of the information you'll need to establish the correct communication. But for simplicity's sake, let's go ahead and just pretend that all we have to do is send the address over the I2C lines and specify the address of this particular device. So it is ready to send information back. If the transfer sending the address on the I2C line is successful, an acknowledge or an ACK will be received. And when the slave address has been sent, the TXIS flag gets set. And this flag is set automatically by the microcontroller. When the TXIS flag is set, that means that the response on the I2C line is acknowledged. This is actually called the ACK, the acknowledge. Now we can go into the read operation where we reverse the transfer direction so we can read. We will inform the microcontroller how many bytes we want to read. And now we want to wait for a byte to be received. And we do that by looking at the RxNE flag. This is the read data not empty. So we're going to wait until this is not set. When this is set and it's not empty, which means it's full, then we can capture the data stored in the RxDR register, the read data register. This is a very simplistic explanation of what happens in the communication of I2C. However, it is important for you to know data being sent and received in more detail because you'll need to be able to read the data sheets and understand what the requirements for each device, the I2C requirements for each device is. In this set of tutorials, I'm going to be using the ADXL 345 accelerometer. This is an accelerometer that is communicated via the I2C, and you'll see that there's an SDA and there's an SCL line on this board. I'll leave a link in the description for the product page, so if you don't have one, you can pick one up. This is the data sheet for the ADXL 345. You'll notice that the communication can be through SPI or I2C. In the data sheet, you want to look for the I2C documentation, and that's on page 18, so let's take a look at that. I gave an explanation of this particular accelerometer in a previous video, and I'll leave a link to that video in the description as well, talking in quite a bit of detail on this part of the communications. There's only 2 pages dedicated to I2C, so there's not that much information, but what it has in this portion of the documentation is very important for I2C. Quickly, you'll notice that it supports 2 different speeds, which is the standard mode and the fast mode. It looks like it doesn't support the fast plus mode, so we can't use that. The address for this board is 0x1D in hex, and is followed by a read-write bit, which means that the 7 bits of the address is going to be shifted left 1 by 1 bit, and the last bit in the 0 place will have the read-write bit. To explain what that means, this is the binary number for 0x1D, hexadecimal for 1D. They're only using 7 bits from 0 to 6. And this bit at the 7th place is not used in the address because the address doesn't go above 127. So we can take all of these numbers and shift it 1 bit to the left because we need this position for the read and write position, read or write position, 0 or 1. So this would look like this. So now that we've shifted it to the left 1, we can use this bit for the read-write. This is common for I2C devices. If you want to read, then this number becomes a 1. And now this number is 3B. 0x3b. If you want to write, then you would have to put a 0 here, and that would be 0x3a. But in most cases, you're just going to do the left shift for the address, and you're going to apply a 0 or a 1 in the last bit, in the 0-bit position. This chip also gives you the possibility of changing the address if you already have an address of 1D on the line somewhere with another device. Now let's take a look at how we can communicate with the ADXL 345. As stated before in the introduction of I2C, the master will start and stop the communication. And that is apparent in the writing, single or multi-byte writing, and then reading as well, single and multi-byte reading. And this is an accelerometer, and you're probably wondering why we have to do any writing to this accelerometer. It just gives output. But you can actually configure the accelerometer to meet specific needs. And just to give an example, on page 22, and I think it's 23 and 24. Yeah, this is page 23 of the datasheet. And it shows you all of the registers, the register map. And it'll show you which ones can be read and which ones can be read and written to. And you can see all the access data registers, which is where you'd have the gravity readings for each axis. And it would be held in these registers. There are also ones that you can write to, and you can specify or configure parameters within this accelerometer. And on page 24, it talks about the specifications of the registers themselves. We're not going to get into this right now. This is more information that you'll need for this particular video. We're just going to be discussing how to communicate I2C in general for this particular device. So in the single byte write, you have the master. The master initiates the start, and it writes the slave address on the I2C line, and the slave will acknowledge that. And remember, this is a write, so we are going to be specifying a particular register address to write to, and then we're going to get an ACK or acknowledge from the slave that register address for the register address, and then we're going to provide the data for that particular address that we want to be placed into that register, and then we're going to get another acknowledge, and then the master will stop. So this is a single byte write. On all of the communications, we're going to have to provide the slave address and a register address because we want to specify a register that we want to write to or read from. And the multi-byte write is the same thing for the first 2 bytes, the slave address, register address, and then you have multiple data that you can write to. And we'll see how this affects the accelerometer and how we write to the addresses using multiple data. For the read, a single byte read is a little bit different. We're going to have the master do a start. It's going to find the device with the slave address. We'll inform which register that we want to read from. And then we're going to do another start. And these are generally called the restart. And you'll provide the read or the slave address again, with the read bit, informing that device that we want to read from this register address. And then we're going to get the data from the slave, because the data you can see is on the bottom on the slave line. And then the master will provide the stop. And then the same thing happens with the multi-byte read, but we're going to allow the slave to provide us more than one data point. In the STM32 microcontroller, we can provide specifications on how much data that we want to read and how much data that we want to write. There is a number of byte specifications for the I2C in the microcontroller that we can adjust. The next thing we want to consider is the timing diagram. Fortunately, in the microcontroller, we have a way to specify timings for the overall I2C communication using the timings register in the STM32 I2C set of registers. Mainly, we're going to be looking at the 400, that's the clock frequency, and we have the fall time and the rise time. So we want to make sure that we have these rise times and fall times specified correctly. So we adhere to the timings of this particular device. So we're not going too fast for the device to be able to perform its operations. Okay, let's go ahead and set up the circuit for the I2C using the ADXL 345. We'll use the application circuit that is specified in the datasheet in the section for the I2C. This is on page 18. And you'll notice that the chip select, the CS, is tied to the high line. We have the SDA and the SCL, both pulled up high, and I'm using 10K resistors. The alt address, that's the SDO, which is right here, and that will be tied also to high. It shows it's tied to low here, but we can see that in the description it says that with the alt address pin tied high, the address for the device is 1D. So we want to use the 1D since this is the only device on the circuit, so it doesn't really matter which one we use. But I'm going to tie this one to high anyway, and then we'll be connecting the VDD and the ground to the high and low rails, to the power rails. The microcontroller shows a couple places where you can connect the I2C, and we're going to be using the number 1, the I2C1, and the SCL and the SDA. The SCL, I'm going to be using the one on port B, pin 6 for the SCL, port B, pin 7 for the SDA. You can see that port B, 8, and 9 are also available for the SCL and SDA. So if you're using the port B, 6, and 7 for, let's say, the USART TX and USART RX, then you can use these instead. You'll also notice I have 2 other wires plugged in to the circuit, and this is actually the logic analyzer. I have them plugged in. It's the brown wire and the black wire, and they're going to monitor these 2 lines to ensure that I have the correct communication going on. The 2 wires that I'm using on the logic analyzer is the channel number 1 and channel number 2, and I also have the ground, which is this first wire here, connected to the ground rail. The form factor of this board, well, it's going to cause it to cover a lot of the pins, a lot of the tie strips. Fortunately, the back of the board has no contacts, so we can put components underneath. So when we plug the board in, components can reside under the board. The pins that I need to reach are going to be these 2 pins here, 59 and 58. 60 is the boot pin, and it is connected to ground at this location. And that's pretty convenient because the board has ground on the right-hand side, and it can be plugged right into the boot pin on this side of it, not on the other side of the resistor, on this side of the resistor, because it's a direct connection to ground. And we have SDA and SCL right here. So they're going to have to tie to these 2 pins from this location back to somewhere around here. So there'll have to be a couple wires that stretch along that location. So let's go ahead and build the circuit. Let's start by adding the 2 wires to connect the SDA and SCL from the board to the microcontroller. We need to pull up the SDA and the SCL lines with resistors, and I'm using 10K resistors. To power the board, I will add a wire from the VCC pin to the power rail. To maintain the current ID for the device, I will connect the SDO pin to the positive, and the CS chip select pin needs to go to positive as well. Now we can seat the board in the proper tie strips. If you have a logic analyzer, you can do this, but it's not required. I'm simply taking a pin from a header. I slide the plastic portion down, and I'm going to insert it into the female end of the connector for the logic analyzer. I do that for all 3 connections that I'm using for the SDA, SCL, and the ground. You're not going to really need a logic analyzer, but if you start to see problems in communications and you just can't pinpoint why these communication problems are happening, then logic analyzers are a really good investment to save a lot of time and understand what's going on in those lines. For the I2C series, I set up a new project called I2C tutorial, or I2C tutorial. We can see that we have our standard skeleton code here. I'm going to first add the include for the chip. To access the port B pin 6 and 7, the SDA and SCL pins, port B needs to be enabled. And next we need to set up the mode, type, speed, and the alternate functions. We'll do the mode first, which tells the microcontroller that we're going to be using an alternate function for those pins. For the mode register, to set it for alternate function mode, we need a 1 and a 0 in these 2 bits. Let's see, 6 and 7. So it should be a 1, a 0, and a 1 and a 0. We'll do pin 6 first. So I'm going to put the 0 in the 0 bit of pin 6. And we want this 1 to have a 0 in it. This is a 0 bit for pin 6. And for the 1 digit, we would like a 1. So we're putting a 0 in the 0 bit, and we're putting a 1 in the 1 bit. So let's do that for pin number 7 as well. So now we've set up the mode for alternate function. Now let's take a look at the type register. And because this is I2C, and I2C uses an output open drain state, where we use the external resistors, the 10K resistors that I put on the circuit, we use those to pull up those lines. We'll set both of these to 1. And for the speed, we're going to go ahead and set it as the lowest speed, and we're going to set as 0 at this position and this position. It doesn't really matter if there's a 1 or a 0 in this position here. So as long as you put a 0 in here, the speed is going to be set to the lowest. Now we've set 0 at those positions, and since we are working open drain, and we're putting the resistors on there ourselves, we're going to do no pull up, no pull down. So we'll set these to 0. And we'll go ahead and use this one here, which actually is stored 11 or 1 1, so it becomes a 0 0 when you do an AND and a NOT. You can see that it has C here. Let's see what this looks like in binary. You can see that it puts 2 1s there, so when you do the AND and NOT, these 2 will be 0. Now I'm going to open the data sheet to see where the alternate function lies within those pins. The pinout and pin descriptions should have the information we're looking for. So you're going to look for something that says alternate functions, and it should look like this page here. So let's go to the port B, and we're looking for pin 6 and 7. Looks like we have the SCL and SDA on the AF1 selection of these pins. So we just have to remember AF1, and let's go back to the other data sheet or the reference manual, and you're going to look for the GPIO alternate functions low register, because we're looking at pin 6 and pin 7, nothing above that. So we want to select the AF1, and we want to put 0001 into these locations and these locations because it's AF1. And by doing this, we're telling those pins to use the alternate function 1, which are the SCL and SDA functions. There's a few ways you can do this, but you can just write out the whole binary number, this entire binary number. And I'm going to show you that method, but you can also use the left shift operator as well. And we can see that it has an array of 2 positions, which is 0 and 1. And we're going to be using the low or 0. And we're going to just have it equal to the binary number. And I'm going to write it out as if it's shown in the diagram. And we can see that there's 4 sets on each row, so there's 8 total. And we want a 1 to be here and a 1 to be here. And this should be the correct number. These positions, let's look at these positions here. This is 24 and this is 28. So we could have done this using the left shift operator. And we're ORing these 2, so 1s would be put in those positions, left shifting at 24 spaces and left shifting at 28 spaces. Now we can start adding the I2C code for controlling those registers. In the advanced peripheral bus, we want to enable the I2C. You can see in the RCC, Reset Clock and Control Register, the advanced peripheral bus has the I2C 1 and 2 enable bits within this register. So let's go ahead and invoke that. Now we're at the stage where we need to look at the timings. Setting up the timings is rather complicated. We have a lot going on here, and there's quite a bit of math that you have to do to set the timings correctly. And in the datasheet, it gives you timings information, which we will use. So first we can tell that we need to set this up as a 400 kilohertz SCL clock frequency, and that is a maximum. So we can go lower than this. And instead of going through all of that math, I noticed that they specified an Excel file called AN4235 that will determine the timings. This is the timing register. It will determine the timing number that you need according to certain specifications you enter into the Excel spreadsheet. So let me show you how to find this file so we can use it to determine the timing value that we have to put in the register. So I'm simply typing in that number and the STM32, and we should get something from st.com. Let's see if this is the correct one. It says it was for the for the 3 and for the 0. So this is the one we have. So it'll work for the one we have. And getting the software should give us the Excel file. And once you log in or register, you should start getting the download. Let's take a look and see what's inside this folder. You can see it says I2C timings configuration. I'm going to need to enable editing and enable content. Okay, so we're going to be using our microcontroller in master mode, and we'll use the standard mode, not the fast mode or the fast mode plus. We'll keep this at 100. You know what? Let's go ahead and change it to 400. Okay, we want to put this in fast mode. So let's change that to 400. All right, let's try to go ahead and run it and see what happens. You can see that it changed the SCL high and the SCL low. The SCL high is 2 and the SCL low is 10. It also changed the SCL DEL part of the timing register to 1. It also shows that we're at a 0 for coefficient of digital filter. You have the analog filter delay on, and we have a rise time and a fall time. I'm not going to mess with the analog filter delay and the coefficient of digital filter. I'm going to keep that at the reset value, but I may change these numbers because the ADXL may require these numbers to be changed. So let's take a look at the ADXL. So let's look at the rise time in nanoseconds first. See if we can find that. This is the rise time here, and that says maximum of 300. So this number is fine. It falls within the realm of what this allows, a maximum of 300. It can't be more than 300. So let's take a look at the other one, which is the fall time. Let's see what the datasheet says for that. So it gives me two different options for fall time. They both have a TF here, and they're both T11. And over here, it shows it right here for at the fall of the SCL and the rise and fall of the SDA. And it says that it needs to be a maximum of 300 or a maximum of 250. So I'm just going to make sure that it's below those maximums. So those should be fine. So I'll go ahead and use this number for the timings register. I'm going to copy that. So we'll put that number into this register here, timing register. In the example code that it uses for the I2C, it casts a 32-bit unsigned integer to this number. So I'm going to go ahead and add this as well, just to make sure that I don't have to worry about some debugging issues later on. The I2C has a control register like most features of the chip. So let's go ahead and see what we need to do in that. And there are two control registers. There's number one and number 2. The control register number 1, is more of a register that takes care of initialization, the setting up the peripheral to do what you need it to do. And the one that we're more interested in is the peripheral enable. And we need to enable this in the first control register. The second control register is the register you're going to be using while you're communicating. And it allows you to do a start, stop, a NAC, how many bytes you intend to either receive or transmit, and the slave address bit or the slave ID. You'll be entering into this. You'll see that it's kind of interesting to notice that there's 9 positions here, or 10 positions here. So generally we're going to be using a 7-bit address, which is going to be in this position here, and we'll have a write or a read bit at this position. And you'll see in the programming that this is actually done automatically, but we will have to set up the ID or the address in this location using a left shift operator. So let's go ahead and set up the first control register, which is the peripheral enable. The code so far takes care of setting up and the main initialization of the I2C. First, setting up the 2 pins so they are output for the alternate function, and setting up the I2C for the timing and enabling the peripheral. And I need a 1 here. Now I'm ready to get into the control register number 2, which is more specific to the actual communication. And the first thing I'd like to do is apply the slave address. And we're going to apply the slave address in 1 through 7, bits 1 through 7, because this bit is reserved for read and write. So let's go ahead and do that. Access the I2C. I'm going to access the I2C control register 2. And I'm going to place the slave address into this control register, directly into this control register, because if you look at the entire 32-bit register, the slave address actually starts from 0 to 9. And if we just apply it directly, it's going to fall right at this location anyway. So since we want it in 1 through 7 and not 0 through 6, we want to left shift it 1. And from the datasheet, we know that the device ID is 1D in hexadecimal. So we'll need to use that. So I'm going to take the 1D and I'm going to left shift it by 1 bit place. And by doing this, I'm reserving the 0 bit for the read write. Now we're ready to tell the microcontroller which direction we would like to transfer, if we're going to read or write, and that's this particular bit here. And you might be wondering, why aren't we changing this bit? And that's because a lot of things are happening behind the scenes within the microcontroller itself. And by affecting this bit, you are telling the microcontroller to deliver the data on the SDA line appropriately, which will cause a transfer on the line with the address and the read-write bit correctly applied. Also, you want to make sure that you set the address and the read-write before you do a start condition. So let's go ahead and go to the WRN bit, and let's take a look at and see what we need to do first using the ADC 345. Okay, so we want to do a single byte read. So the first thing we need to do is we need to do a write. So let's go ahead and set the direction for a write, and that's going to be a 0. And to put a 0 in that bit, we're going to use the AND NOT. Now let's tell the microcontroller how many bytes we would like to write. Let's go ahead and take a look at the datasheet again. And it looks like we want to write 1 byte in this particular case. And that's the register address. So how do we do that? So this is at location number 16. So we want to put the number of bytes within this area. So we're going to have to do a left shift. And we'll use the OR bitwise operation, and we're going to have the number of bytes left shifted 16 times. So we want 1 byte. If we wanted 2 bytes, then we just replace this with a 2. If we wanted 4 bytes, we would replace this with a 4. So we just want 1 byte, so let's go ahead and establish that. Now I can go ahead and establish the start condition. And to establish the start condition, I'm just going to put a 1 in the start bit, which is the 13th bit. So let's go ahead and do that. Now we're going to put the address of what register we would like to affect from the ADXL 345 accelerometer. Let's look at the addresses that we can write to and then read from. We need to write, or we need to access a register address by first writing that register address and then getting the acknowledge and then restarting and then reading from that address. I'm going to select a register address that already has a reset value within it. The addresses that have reset values are 0. You can see one here that has a number in it, and that's at 2C. Another one at 30, and it looks like that's it. I'm inclined to go with this reset value, the register address of 2C, because I want to make sure that in the program, when I send the address, I'm going to actually be able to look at the address in the logic analyzer and make sure that it's 2C. If I get a 00, but I get a right number, then I'm not really sure if I'm actually delivering an address or I have some other kind of bug going on that delivered a 0. So this way I can be sure that I have some kind of actual address that I can verify as 2C. We need to put the hex value of 2C into the transmit data register. But before we do that, we want to make sure that we have a start condition established. And the way we confirm this is just to test to see if this start condition is true in the control register. So let's write that. Let's take a look at the start bit in the control register number 2. This is on bit number 13. By writing a 1, which we've done on that bit, we are creating a restart or start generation. It states that this bit is set by software, which is what we do, and is cleared by hardware after the start, followed by the address sequence
is sent. So we should be able to test for this one, for this start bit. And if it is cleared, we can move ahead. But there is another bit called the TC bit at bit number 6 in the status register called the transfer complete. It states that it is cleared by software when the start bit or stop bit is set. What I'm trying to do here is determine when the microcontroller is ready to send data on the I2C line. I don't want to just put a byte in the transmit data register until I know it's ready for a byte to be placed in that register. I'm not sure the state of the transfer complete before the start bit has been set. I don't see anything else here that could be telling me when I'm ready to send. So I'm just going to use the start bit and test the start bit to make sure it's cleared, because I know that the address sequence has been sent. So I should be all right by just placing the byte within the transfer data register after I test for this bit. So while the start bit is set, I don't want it to do anything, and I want it to, when it clears, I want it to go to the next step. I forgot a 1 here again. All right. Now I think I'm ready to insert the byte or the register address into the transmit data register. The transmit data register is TXDR, and we're just going to assign the byte to this register. So the byte was 0x2C, I believe. Now before we move on, we need to make sure that this has been sent on the line. And the way we figure that out is there is a status bit called TXE. This is the transmit data register empty flag. It's under the status register, and we can see it over on bit number 0. And it says that this bit is set by hardware when the TXDR register is empty. So we know that the TXDR is empty because it has already transmitted that data on the SDA line. So we want a line in the code that says, while this bit is 0, not set, it'll wait. So we want a not before this statement. And the I2C 1, and we're looking in the ISR, the status register, and the mask is the TXE bit. So in the single byte read, we have performed the start sequence. We've written the slave address and the register address. This is done automatically when we apply the start condition because we've already set the slave address into the register that we needed to set it, and we've sent the register address on the line, and now we need to do a start and then a read. But before I do that, I want to check the line. I want to make sure that so far what I've done works. So I'm going to go ahead and apply a stop condition, and we can flash the microcontroller and see if the SDA line does have both the slave address and the register address sent on that line. The stop condition is very similar to the start condition. We're just going to replace the start with the stop. And the test is the same as well, because the hardware automatically resets the stop bit, just like it did with the start bit. So let's go ahead and just do a copy and paste. And we're just going to change this to stop. So let's review what I've done here. On this line, we set the slave address or the slave ID, and we left shifted it by 1 to make room for the read or write bit. On this line, we're setting the read-write bit to write by putting a 0 in that location. And on this line, at the 16th bit, in the control register 2, we're setting the number of bytes that we're going to send. Here we're establishing the start condition, and on this line we're making sure that the start condition is met. Then we write the register address to the transmit data register. To confirm that the transmit has been established, we are testing to make sure that the transmit data register is empty. And finally, we are establishing a stop condition. The stop condition automatically applies a NAC to the SDA line, informing to the slave that no further data will be transmitted or received, at least until a start is reestablished. Now we're finally confirming that a stop condition has been established. Now I'm going to do a build to make sure everything is good. It looks like I have a couple errors here. And I forgot to put an R after the PUPD and the GPIOB, so do a rebuild. So it looks like I have no more errors and the build is successful. Now I can flash the microcontroller and look at the line with my logic analyzer to make sure we have the correct data on the line. Since nothing can be seen on the microcontroller, I'm going to show the results in the logic analyzer. I have the analyzer set to I2C. I added one of the many that can be created, and the I2C is using the channel 0 and channel 1 lines. You can see it says SDA and SCL. When I press start, it'll start listening on those 2 lines. So I need to set this up so it will give me enough time. It says duration 5 seconds. That should be enough for me to, I'm going to change it to 10, I think, for me to get the data when I power up the microcontroller. I haven't flashed a microcontroller yet, but I'm going to go ahead and do that. Okay, the microcontroller has been flashed. So when I unplug the microcontroller and then plug it back in, I'm going to do that while I have the logic analyzer listening to those lines. So I'm going to go ahead and press start. Okay, I've disconnected it and then connected it again. We can see that there is information written to the line. You can see that in the act of unplugging it and plugging it back in, I got 2 occurrences of it. So it must have, when I was plugging it in, it must have had multiple power down and power ups because of the connection, the mechanical connection of the USB port. So let's take a look at it. It looks like we have a write and a 3A. And let's take a look at the program while we're doing this. Let's see how small I can get this. Probably not going to be able to see it, but I'll just go back and forth. Okay, so we put a 1D in the slave address register and we left shifted at 1. So when we do that, the 3A is the correct number for that, because we're actually changing the number by left shifting it by 1. And we got an ACK back from the slave, which is good. And it's interesting, it says comma. So I guess 2C is a comma in ASCII. So I have, let's see, ASCII and hex. So I'm telling it to tell me what is the ASCII equivalent of the hex. And it says comma, and we got a 2C, which is good. So we did write that address correctly, and it did transmit that address on the line. And then we received an ACK by the slave, and we should be able to see it on the line here as well. So let's see if we can get to that. This was when the microcontroller was disconnected for a moment. So let's go back over here and take a look at, this is how tiny this communication is. And it happens within, actually this is milliseconds and this is microseconds. So let's take a look at what we have here. We have a write. This is, the green is the start condition. And the green, the having this go down, this line go down, and then this line go down signifies on the I2C, this is a start condition. And then when this line goes up, which is the SCL, and then this line goes up, which is the SDA, then that signifies a stop condition. You can see that there's the first section here is a write 3A, and that is the slave address plus on bit 0 a write condition. And then next we sent the 2C. You can see that we have a waveform that shows the 2C. And these are just zeros and ones and zeros. So the down is a 0 and the up is a 1. And each SCL pulse here will separate these bits. We transmitted a 2C for the register address only to be able to read the contents of that register. And when we do read that register, we should see this particular number on that register. So according to the data sheet, we've completed with the single byte read, we've completed the start, the slave address write, and the transmission of the register address. Now we can go ahead and read the contents of that particular address. So we need to do a restart, and then we need to do a read and the slave address again. Instead of a write, we're going to be doing a read, which is a 1. And then we're going to store the data into the receiving data register. So let's go back to the code and see how that works. Remember that we need to establish whatever we need to do before the start, which includes the number of bytes we're going to be reading this time. And then we're going to establish the read direction, read-write direction. We don't need to put the slave address into the control register again, because this doesn't change, it stays the same. So we only need to take these two things, the read-write direction and the number of bytes, and then we're going to do another start. So let's go ahead and just take all of this code here, and we're going to do a copy and paste. I'm going to include the comment as well. And we want to do it before the stop, because the stop is the end of communications for the I2C. So now I've pasted that in. So let's change this from a write to a read, and that's just putting a 1 into that register. So we're just going to OR the read-write bit, putting a 1 there. You've probably noticed that there's some repeating code here, and that's something we can clean up right now. So let's go ahead and create a function that does the reading and writing and then the start. So let's take this bit of information here, this bit of code, and we're going to create a function to set the read-write direction, the number of bytes, and the start. I'm going to cut that, put a little bit of space here so I know where that goes. And I'm going to put it up at the top because I don't want to make a prototype. And I'll just create a placeholder here. Call this one I2C for the name. And then I'm going to have two inputs here. Let's go ahead and put the code in first so we know what those inputs are. So we know we need to either read or write. So let's go ahead and I'm going to split this up into two functions, one for read and one for write. And on the read, let's make this the write first because I have it already set up. And I want to apply a number of characters. So I'm going to use the int. I'll call this number of bytes. To write. I'm going to go ahead and make this verbose. Okay, so I2C read, and I'll change this one here to read, make it easy to understand. And I'm just going to take the one that I created here instead of copying the other one since I already changed the read. Okay, so the integer number of bytes to read and the number of bytes to write, I want to add in here. So I'm going to go ahead and just replace this. This should work. And we're going to go ahead and I'm just going to copy this and put it right into where it needs to go. We're writing, and the number of bytes to write is going to be 1. So this would come right after we establish the slave address. Let's go ahead and change the other one here. I'm just going to copy this just like the other one. So we're only going to be reading 1 byte in this case. So I think this is pretty clear. So we want to establish the slave address. We want to do a start write of 1 character, 1 byte, and we're going to do the 1 character. And then we're going to do a start read, and we haven't established the read yet. But there's a little bit more refactoring we could do within here because this is still duplicating code, and I don't like that either. So I'm going to add the code that's not duplicated, or keep the code that's not duplicated, send the other duplicated code. So what we're doing here, the only thing we're changing in this start write and start read is this line here. So this line has to stay, but the rest of them are identical. So let's create a function called I2C start, and we'll enter the number of bytes again. We're not going to specify whether to read or write. And we'll just copy this or cut and paste this code into that. And now we can replace that with the function name, but we want to replace the number of bytes to write into here because we're transferring the number of bytes to be specified right here. We're transferring that into the I2C start number of bytes. Let's do the same thing to the read side. Okay, so we're going to change that from write to read. So we've created 2 main functions, start write, start read, and any duplicated code that we had in there, we put it into its own function. So now the main program is pretty easy to read. We're doing a start write, 1 byte, start read, 1 byte. So let's go ahead and do our code for reading the byte that's on the line. The reading is actually very similar to the writing on the line, but we want to make sure that our read data register is empty before we put information into it. So while, let's go ahead and put our 2 parentheses in there because we're going to be notting this. While it is not, we're going to use the ISR register, the status register, and our mask is going to be the RXNE register, which is the receive not empty register. And when the receive not empty register is a 0, we want it to stay at this location. We don't want it to move on. Only if the RXNE is 0, the receive not empty is 0. And right here we have it's not 1, which is 0. We're going to hold while it's 0. We don't want to mess with the microcontroller while this is happening, so we want to hold while it's 0. If the RXNE, the not empty register, is the bit is 1, meaning that the previous received data byte has not been read, the SCL line is stretched low until the I2C data register is read, meaning that we actually look at this register in our code. So this is telling us that the RXNE will be 1 while the data register is holding the data until it is read, until we actually physically put the code in and it reads the data register. So let's go ahead and do that. So while it is 0, stay here because it's doing some process to put the data onto the data register. So let's go ahead and read the data register so we can inform the microcontroller to go to the next steps. We need to take this information from the data register and actually put it in some variable. So let's create a variable. I'm going to put this in an unsigned integer and I'll call it received data. We should be able to just assign it as we declare it. So let's go ahead and assign it here. And we're going to take it from the I2C 1, and it's going to be the RxDR variable. We're not going to do anything with this variable because right now we're just looking at the line and seeing if it's doing what it's supposed to be doing. So we'll take a look at the logic analyzer instead and see if we've received the correct data on that line. But before I do that, I want to go ahead and build it just to see if we have all of the programming correct. Okay, it looks like we have an error here. The first one is just a warning. It's telling me that I'm not using this variable anywhere else in the program. And that doesn't really worry me that much. So I'm just going to ignore that one. But this error is it's a fatal error error. And I forgot to put a 1 here in the I2C. So let's change that. So the error is over here. Just put a 1 here. We'll do it again. So it looks like I only have that warning here. I'm not too worried about that. And the build was successful, so I'm going to flash the chip while I am monitoring the I2C lines to see what kind of condition I get. The microcontroller has been flashed. I'm going to go ahead and start the analyzer. So I should have some information on the analyzer while I was plugging it in, and you can see that I do. Let's take a look at what it has captured. We know this is correct because we have a write, and it's a 3A, which is the 1D, which is the slave address, and then a 0 after that, which creates a 3A number. And then we're entering the register address of 2C, and then it immediately does a read, which is the slave address, which is the 1D, and then a 1 after that, which is 3B. A 0 and then a 1 would be from an A to a B, so that's pretty easy to understand. And then it gives us a 0A, which is interesting. This is a carriage return symbol. That was the ASCII version of a 0A, and then a NAC, which is the stop. So let's take a look and see what the reset value of that register is, and it is 1010. So let's take a look and see what 1010 is. So the conversion of 1010 does convert to A, or 0x0A, which is exactly what we got on the SDA line. Let's take a look and see what the waveform looks like. So I'm going to zoom in. You can see that there is a start, which is the green dot on the SDA line. And then we have another start and then a stop. We know that we did the first start, and we have the slave address and the write bit after the first start. And then the next we have the 2C, which is the register address. We have a restart condition here, and we have a read, which is the slave address and the first bit being a 1. And then we have the actual data that's on that register of 0A. And then finally the stop condition. So in this video, we have successfully written the slave address and a write. We've delivered the register address to the line so we can read that register address, and we got back the correct reset value of that register address. Additionally, we created a few more functions so the program can be more easily read, and we can still see there's quite a bit more cleanup that we need to do. We can put all of this code into an initialization function, and then we can create a header file that contains all of these functions. So in the main program, we have very little code to apply, and then we can do much more complex tasks when accessing slave devices, reading and writing from them. USART is Universal Synchronous Asynchronous Receive Transmit. This is a communication protocol that allows two devices to communicate using a transmit and receive. The devices that can be used for USART have to be devices that have the ability to communicate using the USART communication protocol. The devices that I'll be using in this next set of videos is the ARM microcontroller, the STM32, and a servo by Dynamixel, the AX12 Plus or the AX18A. Both of these have the capability to communicate using USART. USART is also one of the most flexible ways to communicate between two devices. You can communicate with either one or two lines between them. So you can have the transmit and receive on a single line, which is called half duplex, which is the way this one works, because you can see that there's a power, ground, and a communication wire. That's it. There are two connectors here, so you can have multiple devices working at the same time connected to a single microcontroller like this. You don't have this kind of flexibility with a lot of other communication protocols. For instance, if you wanted to communicate using the I2C, you have to use two lines. One for clock, which is the SDA, like this accelerometer uses, and SCL. You still have to use the lines for power, so you still have to power the board with two lines, and you also have to have two other lines for the clock and the data. Another form of communication is SPI, which you also have to use two lines, MISO and MOSI, master in, slave out, master out, slave in. So if you wanted to, let's say, have two microcontrollers communicate, you could use the SPI communications protocol and have these two devices communicate. With SPI communications, you have three lines. You have a clock line, you have a master in, slave out, and a master out, slave in. And the clock allows you to synchronize the communication between the two devices. With UART, both devices agree on a single speed. So when you transmit from one and then receive from the other, the transmission will be at a specific speed that both of them will be transmitting and receiving.
Imagine I am a microcontroller and I am set to a baud rate of 9600 baud. Imagine I am another microcontroller and I'm set to a baud rate of 57600 baud. That microcontroller probably won't be able to understand me. So it's really important to set the communication speed on both devices to the same speed or baud rate. The actual data that is transmitted from one device to the other is in the form of a data frame. The data frame starts with a start bit that informs the destination device that the communication has started, and then a set number of bits to form a byte or a word. You can think of a byte as, say, a letter in the alphabet. A parity bit, which checks to make sure that the data in the data frame is going to be correct, and the stop bit. Just like the communication speed needs to be the same on both devices, the data frame specifications must also be the same on both devices, meaning there's always going to be a start bit, there's always going to be a stop bit, there's always going to be a parity bit or not on both devices, and there's always going to be the same number of bits in each data frame. And we'll get more into the specifics of that when we start programming. So we've gone over the items that you need to know to configure USART. That is, both devices have to be set for the communication, for speed, for the if you're going to have parity or not, and the number of bits in the data frame. You're going to find that USART is a really easy communication protocol because all you're going to be doing is you're going to be putting your character or whatever you want to communicate into a shift register. It's like a little buffer. And what it does is it sends that character out onto the transmit line and then simply wait for the microcontroller to tell you that it has been transmitted. You can do this over and over for as many characters as you want to transmit. When you want to receive information from another device, you're going to be waiting for something to appear in another buffer for receiving. And then once the microcontroller tells you that something is in the buffer, you can take it and use it however you need to. So let's talk about the hardware for a moment. So let's go to newbiehack.com and take a look at the map of all the pins. Look at the alternate or additional functions for the pins, and you'll see USART 2. So this particular microcontroller has USART number 2, and it also has, let's see, this is one side of it. So let's go to the other side. Here's USART 1, USART 1, USART 1, USART 1, and USART 1 here. I'll probably be using the USART 1 section over here. And we're looking for the TX and RX. And it looks like the TX and RX are here. So the TX is here and the RX is here. And that's 42 and 43. You can also click on these pins here to find out what functions they are. So 43 is the RX or receiving, and 42 is the TX or the transmit. The pins that we're going to be using is number 43 and 42, which is located right here. In this project, since I want to use half duplex, because I'm going to be using the servo that uses only a single receive and transmit line, I'm going to take pins number 42 and 43 and tie them together. So I'll be able to transmit and receive on the same line. I've never tied these two together. The datasheet for the servo says that you need to tie the separate pins through a chip that allows us to shift the receiving and transmitting. I still may need to do that, but I want to try this experiment anyway, just to see if it'll work. The schematic they use is using a chip with the part number 74LVC2G241, which is not the easiest chip to find. And also, they show 5 volts here. So that's something that really concerns me for the RX and TX lines. I have to make sure that the RX and TX on the microcontroller are 5 volt tolerant. So I will be able to do that. And they also show that it's the RX is pulled up with a 10K resistor and the TX is pulled down with the 10K resistor. I want to see if I can not have to worry about that and only put a 10K resistor pull up on both lines as they're showing on this side. There are alternate chips that I can use instead of the 74LVC2G241. I may just use a tri-state buffer chip to do the same thing, but that will only be investigated after I see if this works or not. Looking at the datasheet from ST Micro for this particular controller, I can see that the 43 and 42 are 5 volt tolerant. The FT means that the pin is 5 volt tolerant. You can see on page 28 the descriptions of the I/O structure and the tolerances and what is allowed on each pin. Another consideration we may need to make is that we may need to use a crystal oscillator instead of the internal RC resistor capacitor type of clock that it's used. The clock inside the microcontroller is not as accurate as a crystal oscillator. I will most likely not have to use a crystal oscillator, but when it comes to projects that are very critical, it is best to use a crystal oscillator just so you can make sure, you can ensure that all of the data going back and forth is always going to be accurate. So I'm going to increase the speed of the microcontroller to 48 megahertz, and that will be fast enough that I can scale it down and make a very accurate baud rate for the USART. Also, the servo is able to communicate up to 1 megahertz. So 1 megahertz is easily divisible by 48 megahertz. So that shouldn't be a problem getting a good communication speed matched with the servo. There's also a really cool feature built into the microcontroller. It's called the 1-bit feature, and it is a majority vote feature that evaluates bits being communicated. So it evaluates the stream of voltage, either 0 or 1, voltage that creates a 1 bit or voltage that creates a 0 bit. The 1-bit feature will evaluate the communication of a 0 and a 1. So a clean signal would be something like this. This is a 1, this is a 0, this is a 1. Maybe there's another 1 here, and then it goes back down to 0. But the communication may not be as clean. It may be kind of messy, and then it goes back down, goes up, stays up, goes back down, maybe it comes up a little bit. So it's kind of messy looking, but what the 1-bit feature does is it divides this up into 3 sections. And if it looks like this one is a 1, it'll put a 1 here. If it looks like this is a 0, because it kind of looks like a 0, it'll put a 0 there. And this one kind of looks like a 1. So this is a majority vote, and 1 wins. This one should be a 0, and they all look pretty good. So that would be 0, 0, 0. So that would definitely be a 0. This one looks like it would be a 1, a 0, and a 1. That would be a 1. So we definitely have 1, 0, 1. And this one looks like it would be a 1, 0, 1 again, so that would be a 1. And this one looks like it would be a 0, 0, 1, which would be still a 0. These are majorities, and the majority wins. If you have a scenario where it's supposed to be a 0, but it shows 2 1s, then the 1s win, and that may not be a good thing. So the microcontroller gives you another feature with the majority vote, and it flags the ones that don't have all 1s or all 0s. So you can use this in your error catching, and if you see any of those flags, you can retransmit the information or receive the information. Since we're going to be working with the clock and increasing the clock, we need to prescale the clock or divide the clock and use a couple timer functions. So if you look at chapter 26 on page 268, you can take a look at some of the information here, maybe do this project. I'll be going over the prescaler, the PSC, and the ARR registers. And if you don't have the book, don't worry, I'll be going over it, but it won't be in as great detail as it is in the book. I'm going to show you how to change the clock speed of the microcontroller from 8 megahertz to 48 megahertz. This is an STM32F030 microcontroller. The STM microcontrollers have an internal clock and an external clock, and each of these clocks have a low speed and a high speed. The high speed internal clock is the HSI, and the low speed internal clock is the LSI. The external ones, which we'll talk about in another video, is the HSE, which is high-speed external, and LSE, which is low-speed external. In this particular microcontroller, the default speed is 8 megahertz. 8 million cycles per second. Inside the ARM microcontroller, there is a pulse, very similar to like a heartbeat, but the pulse of a microcontroller looks more like this. And within each pulse, an instruction is able to be carried out, very similar to the instructions or like the code that we create, but these are more low-level instructions. But you don't really need to know that. But in some circumstances, you need this pulse to be faster. At default, this particular microcontroller, this is the STM32F030, it runs at 8 megahertz. And that is using the internal oscillator. It's a RC resistor capacitor oscillator, which is not really that important, but you do need to know that this is the HSI, the high speed internal oscillator. And this microcontroller has the ability to run at 8 megahertz using this internal oscillator, or it can run at higher speeds using the PLL clock. So this is the internal oscillator, which is already available to you. The speed of this internal oscillator can be varied. You can prescale upscale this, or you can divide this into a smaller speed, like maybe 4 megahertz if you wanted to divide it by 2, or you can increase this speed using the PLL, which is a multiplier. And all you need to know is that this PLL allows the internal clock, the HSI, the high-speed internal clock, to be multiplied. But it's multiplied by this speed divided by 2, which is 4 megahertz. So let's go ahead and try this out and see what we can do with this internal HSI, high-speed internal clock, and how we can make the clock speed faster using the PLL. Because the PLL clock uses the VSS-A and VDD-A to power its clock, pins number 12 and 13 need to be connected to the power as well. Pin number 12 is connected to the negative, and pin number 13 is connected to the positive. So let's create a new project and see what we need to do to change the system clock on the microcontroller. Okay, so there are a couple of ways you can change the system clock speed, and that is using the clock configuration and the pinout and configuration. So you can take a look here and go to the RCC, and there are some parameters you can change. I'm not going to be doing any changes in here, so I'm going to go straight into the clock configuration. And this is actually a pretty simple graphic representation or a block diagram of the system clock. And it shows you the low speed external, high speed external, and these are the two external sources that you're able to use. The low speed external can accept up to 1000 kilohertz, and the high speed external can go up to 32 megahertz. But that's only at the input of the microcontroller. You can actually change its speed after the input. So you could essentially multiply that speed using the PLL multiplier. In this case, we're going to be using the HSI, which is the high-speed internal oscillator. And you can see that the HSI right now is at 8 megahertz. That's default. And if you wanted to change the low speed, that is at 40 kilohertz at default. So if you look at this block diagram, if you follow the traces with the HSI, you'll see that it goes to this little control here. And it gives you the ability to control what you're going to be using as the main clock. Are you going to use the HSI and then you're going to maintain the 8 megahertz? Or are you going to change it to the PLL-CLK, which can also change it? You can see that I have a problem here, and it tells me where I have the problem. I can click on Resolve Clock Issues, or I can just pick the down arrow and change the value. And you can see that when I change the multiplier, and I have this selected, you'll see the output is 16 megahertz. But I'm multiplying this by 4. Shouldn't I be getting a 32 megahertz? But if you trace the lines over here, the HSI, if you trace all the way down, you'll see that it's divided by 2 here, and then it goes into the PLL multiplier. So first, your 8 megahertz is divided by 2, which is 4, and then it multiplies by 4, which is 16. And then it goes on from there. You can change prescalers, dividing the clock further if you want to. You can divide the clock over here, which goes back down to 8. You can divide it over here. You can change some of these features or peripherals to different speeds. We're going to maintain a non-division, but in our case, we want to change it to 48. So we want to multiply it by 12. So when we multiply it by 12, you'll see that it shows the value as 48 megahertz. And you can also see that it's changed here as well. And you have the option of changing it here. Like, let's say we want to change this to 24. What will it do? Okay, so 24. By changing this to 24, I'm essentially changing it to 24 over here. And what it did is it automatically changed this to 6. So we want to go back to 12, and you'll see that it goes back to 48. And I can change this back down to dividing by 1, so it doesn't slow this one down. So it takes a little bit of getting used to looking at this block diagram, but it's pretty simple after you look at the tracing of where these things go. If I go back to the HSI, you'll see that it goes back to 8. If I wanted to change this manually to 48 and press enter, it says no solution, but you'll see that after I accepted that, it changed this to 12. It changed this PLL-CLK to be operating under the PLL clock. It accepted that value. So let's go ahead and save, because you'll see this little asterisk here. It's telling us that this file hasn't been saved. And once we save it, it will want to auto-generate the code for us. So this is sort of the easy way of creating the code to change the system clock. But I'll also show you a manual approach as well. So let's go ahead and save it. You can also click on this button right here, Device Configuration Tool, Code Generation, And if I press this, it'll also generate the code. I'm just going to go ahead and save it. And it'll ask you, do you want to generate code? And I'm going to say yes. And I do want to open the main.c file. And here is the code that has all of the commented code telling you where you can place your code. I don't generally look at that. It does create a lot of bloat in your code, but just ignore it at the moment, because I may want to change the values in the IOC file. And if I take all of the comments out, it will put the comments right back in once it generates the code again. So I'm just going to keep these comments in here. All right, this is the portion of the code that was changed automatically. You can see that it's using the HSI in the beginning, the oscillator type. The HSI is on because it has to use the HSI and the PLL to operate. The PLL is just multiplying the high-speed internal oscillator. And you'll also notice that the PLL is on. The PLL source is the HSI. It wants to use the HSI and not the external. It's using the internal. If we were using the external, it would be using the PLL source of HSE instead. It's multiplying it by 12, and you'll get a resulting 48 megahertz. And in this condition, it's making sure that this process is completed. And in this section of code, it is changing the clock source to the PLL-CLK. And with the AHB and the APB, which we'll go through later in other videos, it is not dividing it by anything except for 1. You can see that here. The AHB prescaler is divided by 1, and the APB prescaler is divided by 1. But that's not really that important in this particular video, so you don't have to really worry about that. I'm going to go back to the main.c. And once we program the microcontroller with this code, the microcontroller will be running at 48 megahertz. But how do we really know that? And I'm going to test this using a variable. So I'm going to add a variable outside of the main. So it's a global variable. I'm going to put it inside this user code begin 0. And I'm going to use a variable called test counter. It will be a volatile variable. And there's no real explanation on why I'm using the volatile, except that it will keep this active during the operation of the microcontroller. You need to use the volatile keyword to make sure it's not optimized out. And it's going to be an integer. And the name of this variable is going to be called test count. And I'm going to assign it as 0 at the beginning. And I'm going to use the counter to determine whether this microcontroller is actually running at 48 megahertz. To verify that the microcontroller is actually running at 48 megahertz, I'm going to use the timer, and the timer works like this. The timer will use the internal clock, and I'm going to use timer 1, and this is how we'll be writing it in code, timer 1, and the timer 1 will be running at 48 megahertz unless we prescale it or divide it down. I want this variable that we just created to tell me when 1 second has elapsed. So since the timer 1 is at 48 megahertz, I'm going to use the prescaler, which is a way to divide this down to a smaller number. So instead of the timer counting up to 48 million cycles per second, I want it to count up to, let's say, 1,000 cycles per second. So to do that, we would divide it by 48,000. This is the prescaler. So now the timer is counting at 1,000 times per second. So what I want to do is I want to make sure that there is a trigger in the timer that will tell me that it's reached 1,000. So we're going to create a sawtooth pattern here. So the timer is going to be going up, and instead of keep going up and then just counting indefinitely, we're going to use the ARR, which is this top level here. And the ARR is going to be 1,000. So when it's reached 1,000, it will drop back down to 0. And then it will count up again until it reaches 1,000. And then it will drop back down to 0 and count up again to 1,000. So at each 1,000, because we divided it by 48,000 at 48 megahertz, the timer 1 is counting at 1,000 pulses per second. So if we have a top value of 1,000, then we should get this trigger every second. So let's go ahead and try that out. I'm going to enable timer number 1. Timer number 1 is in the reset and clock control register under the advanced peripheral bus enable register. And we're going to we're going to set the bit for the timer 1 enable. So let's take a look at the registers for the timer. So this is the timer number 1. It starts at page 220. You can read the chapter if you want, but I'm going to go straight to the timer control registers, which is the 267. And you can see that there is the first one is time 1 CR1. But before we do that, we need to enable the timer in the advanced peripheral bus. So if you take a look on page 113, you'll see the description of the advanced peripheral clock enable register, RCC APB2ENR. This is what we put in our program. Inside of this APB2ENR register, you'll notice that timer 1 enable bit is located here. You need to turn this bit on or set this to 1 for this register. So let's go ahead and do that. We're using the OR bitwise operation to set the bit. I'm going to use the control space to look at all of the things that I can change. And the timer 1 is located right here. Okay. And I got a comment stating that the video that I'm showing how to set and how to reset bits, like using this OR bitwise operation and the AND not bitwise operation, is a bit of a misnomer. Because this is actually a mask. It's not really setting a particular bit number. And that is true, but there really isn't any need to understand bitwise operations and truth tables at this point. Just knowing how to set and reset bits is perfectly sufficient at this point. If you want to learn more, I'm going to put a card at this position of this video, and you can watch my old video in the AVR series on how to do bitwise arithmetic using the AND and the OR, and how to use masks, which is what this really is. If you look at it, you can see that it's taking a single bit, which is a 1. It's actually 1 in decimal and 1 in hexadecimal as well. And it's moving it 11 places to the left. This is the shift operator. And I show that in that video as well. And if you look at the reference manual, you'll notice that that's the 11th position. So it's taking a 1 and it's moving a 1 to the 11th position. And it's a 1. It's just like the number looks just like this. I'm going to use a comment for this. This is a 32-bit number. So this is the number. This is essentially what the register looks like, because you can see it has 32 places from 0 to 31, which is 32 places. And what this is showing you here, taking a number 1 and shifting it 11 spaces, is doing this, putting a 1 in this location. That's all it's doing. And it is as simple as that. So this value here is the same as this value right here, which is the same as this value here, which is using the bitwise shift operator. And we're not going to be getting into complexities like this because there really isn't any need to do this unless we start to use functions, and I show you in more advanced tutorials like I did in the previous series on how to set certain data pins of the LCD or something like that. So, but we won't be doing that for a while in this series. So I'm going to keep it as simple as possible. We don't have to worry about this stuff. All we really need to know is what bit we're affecting, and it's the timer 1 enable bit. That's it. So let's go ahead and enable the counter portion of this timer. We have to go back to the timer 1 section of this document, which is around 220, I think, or actually it was 267. Okay, so in the CR1 register for the timer 1, you'll see that there is a CEN, which is a counter enable. So we want to have the counter to be enabled. The counter is going to count up as fast as the system clock counts up, unless we divide it by some number. So let's see, where is that CEN? Should be at the end somewhere, I guess. Yeah, this is the counter enable. So to enable the counter, we want to write a 1 in that bit. So which bit is that? That is the bit 0, and it's called the CEN. So let's go ahead and do that. So we're using the timer 1, and we're using the CR1, the control register 1, and we're using the OR bitwise operation because we want to set the bit. We want to make the bit 1. So in here, we just use TIM, timer, because timer 1, timer 2, timer 3, they all have the same specifications or registers. So we're using TIM CR1. I'm going to use my control space to look at what we have here. So we have the CEN, counter enable. Let's go ahead and accept that. So now we've enabled the counter. Now we want to prescale the counter by 48,000. So we're going to use the, well, let's take a look at the reference manual and see what we can find here. We're looking for the PSC register. Okay, here's the timer 1 PSC. And this is a prescaler. It just divides the system clock, or the clock that the counter uses. And you can see that there's a 16-bit number here. A 16-bit number can go from 0 to 65,565. So that's why we can't just specify 48 million in this register, because we have to work within its bounds. So 48,000 is less than 65,535. So we can go ahead and use that number. So we're dividing the 48 million clock cycles, which is what the timer 1 is using, and we're dividing it down to 1,000 pulses per second. So let's go ahead and do that. So the timer 1, using the prescaler register, and we're going to just make it equals, because this is not a bitwise operation. We're just going to put a number in here, and this is going to be 48,000. Now we need to create the ARR number, which is the top trigger value that causes the counter to reset back down to 0. So the ARR value is the next one, which is the auto reload register. What this does is the counter will count up the 1,000 times per second, and we can put a value here. We could say 2,000 if we wanted to, like the ARR value would be 2,000. So that means that if the timer is now running at 1,000 times per second, it will reset every 2 seconds. But we want it to reset every 1 second, so we're going to put a value of 1,000 here. You can see that this is a 16-bit number as well, so it has a top value of, you guessed it, 65,535. So let's go ahead and put that in as 1,000. ARR, which is the auto reload register, and we're going to make that equal to 1,000. So now the ARR value is going to top out at 1,000 and cause the counter to reset back to 0 and then go back up to 1,000 again. So what we need to do now is use our new variable and make this variable equal the counter. And we're putting this inside of the while loop because we want this to continually run. We're going to get the value of the counter from the counter register. So let's take a look at that. The counter register is just above the prescaler register, and you can see that it can have a maximum value of 65,535. This register is automatically populated with a number of the counter value. So let's go ahead and access this register and take the number out of this register and put it into the variable that we created. So test count is going to be equal to the timer 1 count register. So all we're doing is we're accessing the count register, the counter value from timer 1, and we're putting it into the test count. We're assigning it to the test count variable. So now that we have a variable here, we can monitor this variable in the STMStudio. So I'm going to go ahead and plug in the programmer and program the microcontroller. And let's go ahead and press the play button and see if we have any errors. We have 0 errors and 0 warnings. And because this is a new project, it's going to give me the launch configuration properties. And I can check to see if the debugger has the correct information in here. I usually have this at none, so I'm going to click that and everything else looks good. I don't need to scan this for the serial number because if I change this ST-link, then it'll give me an error and I have to rescan it. So I'm not going to do that. I'm going to go ahead and press OK, and hopefully everything goes well. Okay, we didn't have any errors after the download verified successfully. Because in the last videos that I wasn't able to get this to work, I wasn't using the VDDA and the VSSA. Let's go ahead and take a look at those, the power domain, and show you why that didn't work. So this is the data sheet for the microcontroller that I'm using. Let me make it smaller. We're going to go to the power supply scheme, or okay, yeah, it actually shows here that the VDDA and the VDDA and the VSSA, which is the same, it's just positive and negative. The PLL uses that portion of the power, the VDDA and the VSSA, and I didn't have those two connected, so I would immediately get an error here, and I would have to erase the microcontroller to be able to reprogram the microcontroller. But I have that connected, as you saw in the beginning of this video. So let's take a look and see the variable in action. using the STMStudio. Okay, so the STMStudio, I'm going to have to import the ELF file for that project. I can go over here and get the ELF file. If I go to debug, you can see that there's an ELF file here. If I press the right button and I go to properties, I can copy this to the clipboard, or I can just go there because it's pretty easy. It's under the users, my name, and then STM32 CubeIDE workspace 18.0, and then the project name under debug, and then the ELF is there. So I'm going to copy this, and in the STMStudio, I'm going to right click here and I'm going to import, and this is the executable file that I'm needing here. So I'm going to just go ahead and press the ellipsis and paste it here. I'm using the Control V because it didn't give me the option when I write, and say select executable file, and it usually says this. I'm not sure why it says this, but the gdb command print x ampersand apb PRSC table 0 failed, but that doesn't matter because all we're really care about is the test count. I'm going to import that, close, and now I need to send this to the var viewer, which is over here. So I'm going to send to var viewer, and when I press the play button, since the microcontroller is already connected, it should show me the value. So you can see the count value is happening once every second. 1 1000, 2 1000, 3 1000, 4 1000, 5 1000, 6 1000, 1 Mississippi, 2 Mississippi, 3 Mississippi. So it looks like it is running at the correct speed at 48 megahertz. Because we divided it down 48,000 times, and then we're counting every 1,000 ARR value, and we're looking at the counter that is counting up from 0 to 1,000. Let's take a look at that again and make sure that it's counting up to 1,000. So you can see the 1,000 here, that's counting up to 1,000, and it's going back down to 0. So it has that sawtooth look to it. Now, what if we wanted to do this manually at the register level rather than using the IOC file? I'm going to go ahead and show that to you now. So I'm going to erase this system clock completely. This is the generated code, and I'm going to erase all of the comments since I don't need any of this. I do want to keep the air handler just in case I use it sometime in the future. I always like to have it. I could use maybe the LED with this. Let's say light up the LED if there is an error happening in the code. I'm not going to need this call either, and I'm not going to need this function prototype because I took out the actual function. So I can remove that. So you can see all we have is the include. Let me save this so we don't have all those lines there. So we have the include, main.h. We have our variable that we created, the HAL init. I'm going to keep that in. Probably not going to be using any of this. We have the timer code that we just put in, and we have the counter that is passed into the test count variable, and we have our error handler. So that's all we have in here. So now we have to create our own clock, and this is how you do it. We have to first make sure that we're using the HSI as our main clock, the high-speed internal clock. That is actually already set as default. So we don't actually need to put those lines of code in, but I'm going to do it anyway, just as a confirmation that we're using it. So the clock and control register contains all of the clock source registers. So let's go to the reference and let's go to the RCC portion of this manual. Okay, so the reset and clock and control register. Let me go back up. So here's the reset clock and control section of the reference manual. It's on page 87. And here's the clocks portion of it. And it talks about the HSE, which is the high-speed external, and the HSI, which is the high-speed internal, and the PLL, which is the phase lock loop. And that is a far more advanced topic, and I have no idea how that works, and I'm not even going to get into that. But it is a way to multiply the HSI clock and the HSE clock, and probably the LSE and LSI, but I'm probably never going to work with these two clocks unless I absolutely have to for some reason. So the PLL, so we need to make sure that the HSI is selected as the main clock, and to find that out, we're going to go to the registers, find out how to do that. So the clock control register is the CR register, and you'll see that there is an HSI on, and we want to make sure that that is a 1. Let's go confirm that. Yeah, the HSI oscillator is on, so we want to make sure that is a 1 at that position. You can see that it is already on by default because this is an 83. The 3 value is actually a 1, so this HSI on is already a 1 at reset. So let's go ahead and do that in the code and change this bit to a 1. Set this bit. How do we do that? We use the OR bitwise operation. All right, so we're going to go RCC, control register, and we're going to use the OR bitwise operation, RCC, CR, and put the C in here. And the bit that we want to select is the HSI on. And now we want to make sure that the HSI is ready. So once we've turned it on, we want to wait until the HSI actually is on. We're going to use a while statement, and we're going to use the HSI ready flag. So this is the HSI RDY flag. Let's see how that works. So if it's a 0, then it is not ready. So we want to wait while it's not ready. So if it's equal to 0, then it is not ready. So let's go ahead and do that. I'm going to put another set of parentheses in here. RCC CR, the RCC CR HSI ready. If this is equal to 0, keep waiting because it's not ready yet. Now we want to make sure that the HSI, the high-speed internal oscillator, is being used as our system clock oscillator. And you do this through the CFGR, the clock configuration register. And we're going to use the SW, the first 2 digits of this register. Let's go take a look at what this SW requires. So the SW, the HSI selected as system clock is 00. So we have to make sure we have a 00 there. That is our reset value. So we don't really have to do this because our reset value is already 0 is a 00 in binary. And then we're going to use the SWS to determine that it is in fact changed to the HSI, which will also be a 00. You can see that it says read only. It's not read and write. This is a status. It just tells you what value it is. So once we set it to 00, we're going to read this and then make sure it's read at a 00. So we're going to use another while statement to determine this. So let's go to the RCC CFGR register, and we're going to use the AND NOT bitwise operators for both the SW bits. I'm going to use the control enter to see, or control space to see the list here, and we're looking for the SW. That's the SWS, and this is the SW. So if I put SW here, it's already the 2-bit digits in this register. So we can just do this in one line, just like this, because this SW actually shows a 1, 1. And when we're doing an AND and NOT, it is nodding the 1, 1, and it's creating a 0 for those 2 positions. So this is all we need to do, is do this in one line. So the SWS needs to be 0, 0. So let's go ahead and write the while loop to wait until that is a 0, 0. We're using the AND to do an AND bitwise operation here in the condition, the SWS. And this is going to be a not equal to, well, it's not equal to the HSI value, which is 0, 0. We're going to use the built-in definitions for this. And there should be one labeled HSI. So while it is not equal to the HSI, wait until it is equal to HSI, and then we can move on. Now, to use the PLL, the phase lock loop functionality with the internal oscillator, we need to first disable the PLL so we can make changes to it. And this is actually spelled out for you in the reference manual. Let's go to the PLL section. Okay, so in the PLL section, in the clocks section, there'll be a section devoted to the PLL. There's the HSI clock, and then there's a PLL clock. And right here it says disable the PLL by setting PLL on to 0. And I'll show you where that register is. Wait until the PLL ready is cleared, meaning that it's unlocked. At that point, the PLL is fully stopped. It's not working anymore, so we can make changes. We can now change the parameters. We can set the multiplication to 12, the PLL multiplier, and then we can start the PLL on again and lock the PLL. And the PLL ready determines whether it's locked or unlocked, which I'll show you in a moment. This is in the control register. So we're going to go to the RCC CR again, the control register, this one right here. And you'll see that there's a PLL on, which we have to set and reset. We're going to reset it first to turn it off. And we're also going to wait until it is ready. So you can see where it says locked and unlocked. So first we're going to turn the PLL off. We're going to make sure that the PLL is unlocked using the PLL ready flag. We're going to make the changes like multiply the PLL multiplier to 12. Then we're going to turn the PLL back on and then wait until it's locked. So we can't make any more changes. So let's go ahead and do that. So first thing we need to do is turn the PLL off. That's in the RCC control register. And we're going to use the AND not bitwise operation to set PLL to 0 or off. We want this to be a 0, so we're doing the AND not bitwise operation. Now we're going to wait for the PLL ready to show us that it is unlocked. While it is, let's see, what number does it have to be? While it is not equal to 0, we stay in the loop because we want it to be 0. So let's go ahead and put in not equal to 0. I put these in here because if I wanted some code to be in here, I can put it in here. These are demarcations for code within these brackets. Just like the brackets with the int main, open and close, you have a bunch of code within it. Okay, let's see. Now we can create the PLL multiplier to 12. So let's go ahead and do that. And I think that's in the same register. Let's take a look. No, it's in another register. So let's take a look. CFGR. Okay, here's the PLL multiplier. So what does this need to be? The multiplier number 12. So what we need to do is we need to set these bits as 1, 0, 1, 0 in the multiplier section. So this should be 1, 0, 1, and 0. But there's an easy way to do this, because first what we could do, because we don't know what's in these spots right now. We do know actually because it's a 0, 0, 0. This is the reset value. So they are all zeros, but what if we're in the middle of a larger program and we don't know how we set it before and we want to, reset it to a different number? This could be 1, 1, 1, 1 if for all we know. So what we want to do is first turn those into zeros using the clock multiplier by 2. So we can reset those, all 4 of them, by using the AND NOT operation. And then we can use the OR operation with the clock multiplier for 12. So let's go ahead and do that. It's the CFGR, and we're going to use the AND NOT operation because we want all zeros in those 4 positions. So the PLL-MUL, the multiplier, right here is 0, 0, 0, 0. So you can see that's going to show up as 1, 1, 1, 1, which is F. F is the same thing in hex as 1, 1, 1, 1 in binary. So what that's doing, this is just a mask. And what that's going to do is it's going to turn all those into zeros. 0, 0, 0, 0. RCC. Now we're going to use the PLL multiplier 12 and using the bitwise OR operation. CFGR, and using the OR bitwise operation. So now we've assigned the PLL multiplier 12 inside of the CFGR register as 1010. So now we can go ahead and turn the PLL back on and lock it. I'm just going to go ahead and copy and paste that set of code here, and I'm going to use the OR bitwise operation to put a 1 there. Let's just make sure that that's correct. I have to go back to the CR. Here we go. Yes, so we're turning it back on and we're going to wait until it's locked. So we're turning it back on using the OR bitwise operation, and then we're going to wait while it's 0 because we want it to be a 1. So right here, it's a 1 when it's locked. So we're going to keep waiting while it's a 0. And when it's a 1, it'll get out of this loop and go to the next thing. Now we want to use the PLL clock as our main clock now that we're using the PLL. So let's change it from the HSI to the PLL. We're not going to be turning off the HSI. We're just going to be assigning the main clock source as the PLL, but we're still using the HSI, so that has to remain on. So I'm going to go ahead and just copy and paste this part of the code, and we want to set it to the PLL. It's already 0, 0, so we're pretty confident that we can just do this, SW and underscore PLL clock. So now we're assigning the PLL clock as our oscillator. Let's go ahead and just do a confirmation of this. That's in the CFGR register. That should be down here, I think. Yeah. All right. So the SW is the system clock switch and PLL is 1, 0. And that's what we want to select. So we're going to go ahead and do an OR bitwise operation and set it to the PLL. And then we want to make sure that it's as long as it's stay in this loop while it's not the PLL. So when we're making the switch to PLL, we have to give the system some time to actually do the switch. And the status register, switch status, is giving us a status that it's switched to the right clock, and we're waiting until it's the PLL. So if it's not the PLL, stay in this loop. When it is the PLL, escape out of this loop and go on to the next thing. And that's it. That's all we have to do. So in review, we are turning on the HSI, the high-speed internal clock. We are using that as the clock source, which is really just making this 0, 0. We probably don't even need to do this, but I'm doing it anyway. It doesn't really matter. We are turning off the PLL so we can change the multiplication, and we're also unlocking it, waiting until it's unlocked. Then we're turning it back on. We are locking it back so we can't make any more changes to the PLL, and then we're switching the main clock source, the system clock, to the PLL clock. So let's go ahead and try it out and see if it works. We should get the same values and timing for the timer 1 count as we did before when we used the IOC, the auto-generated code. So this is the register level code, which is just a few lines. It's not that hard, just setting and resetting some bits. So let's go ahead and press the run. My microcontroller was still plugged in. We have 0 errors, and now it's connecting and transferring the program. The download verified successfully. Now it's shutting down. And now when it says shutting down, by the way, it's shutting down its connection to the microcontroller, but the microcontroller is still running because it's plugged in and it has power, but it doesn't have communication between the STM32 Cube IDE. And that makes it easy for us to use the STMStudio, because when we go to the STMStudio, we're not going to be blocked by any communication that's happening currently. We can just go ahead and press the play and it'll start doing it. But first we have to import that information. So let's go ahead and import. We're going to use that same executable file, but I'm going to go ahead and manually look for it. I'm going to go to my PC. I'm going to go to my C drive. I'm going to my users, phood, going to STM32 Cube IDE, my workspace 1.8.0, and this is the one. This is my new project. And then we're going to go to the debug because that's where the ELF file is. So we're going to double click on the ELF file. We're getting that same error, but don't worry about that error. Give it to us twice for some reason, not sure why. I'm selecting the test count. That's our variable that we created. We're going to import that variable, click on close, and we're going to send this to the var viewer1 and play it. See if we get the same output. Yes. It looks like it's doing this every second. So we were able to change the clock speed using the auto-generated code with the IOC file. And we were also able to do it using the register level bit changes to registers. In this video, we're going to learn how to initialize the UART, which is a communication protocol to be able to serially communicate to other devices. Let's go into where we change the speed of the microcontroller, and I used the name change system clock speed for the name of the project. I'm going into core, source, and the main.c. And the code that we have is the code that changes the speed of the clock. And then I use a timer to test whether it actually happened or not. We don't need this portion of the program, so I'm going to delete it. The test count and the variable that I used for the monitoring of this count. So all we have is the include main.h, the initialization for the HAL, the code that speeds up the microcontroller to 48 megahertz, and that is it. In this particular video, I'm going to be using the register level code, not code that is created by auto-generated code or from the HAL, the hardware abstract layer. I want to tidy up this information, so I'm going to put all of this into a header file. So I can just call this code in using one line. And the reason why I do this is just to make the overall code look neater and more organized. I could just keep it here in the just after the main, but in larger programs, which we'll be making, it's going to be more difficult to debug and find where problems exist and where particular code is actually located for doing what function. And this particular function is changing the speed of the microcontroller. So let's take this code and I'm going to press Ctrl X, which is just cutting it and putting it into the clipboard. And I'm going to create an include file. I'm going to press the right button. If you already have the book, you already know how to do this. I'm going to go to new and header file. The header file is going to be called change to 48 megahertz .h. The .h just means it's a header file. We're essentially making a library. Click finish, and you'll notice that a few lines are included here. And this simply makes sure that the code is only compiled once. So I'm going to create this function. The function is going to have a name. A function needs a return data type, but we don't need one. And we're not passing any parameters into this. Later on, when we make the function more sophisticated, we can add more parameters, maybe changing the internal clock to other values, but because we're specifying this as a function only changing it to 48 megahertz, I'm just leaving it alone like this. Now we need to add our code within these code brackets, and that's all we have to do for the header file. Some of you that understand how to program C and C++ will notice that this may not be the standard way of doing or making libraries. In this particular video, I want to show just a very simple way, and that's just making a header file. In most circumstances, you're going to be making a header file and a C file. The header file will only have some macros, defines, and function prototypes, which just really include this single line here. And then the C file would have these functions. But when the program is so simple like this, it's not really that much going on, I put everything into the header file. Let me go ahead and save this real quick. In the main, I want to include this new header file, hash include, and then in quotes, I'm going to type in change to 48mhz.h. Now you'll see the squiggly line underneath disappeared because it knows that this exists and we can use it. So after the HAL init, I'm going to use the function change. I'm going to use the control spacebar because there's only one of these available functions, and use the semicolon afterwards. What I've just done is essentially turned all of those lines that are in here into a single line. Hopefully this makes sense to you, and this makes everything more organized and easier to understand. Now that if I want to change something that is specific to changing the internal clock to 48 megahertz, I can just click on this and then open declaration, and it'll go straight to that part of the program and we can make changes to it. I'm going to exit this. And now let's go ahead and get started with the initialization for the UART. You'll notice that this microcontroller has more than one USART. There are pins on this side which have the TX for UART2 and the RX for UART2, but we'll notice that there's no UART1 on this side. So we'll have to go to the other side of the chip. You'll notice that there's a UART1 RX and a UART1 TX. So we can use pin number P, port B7 and port B6, which is 58 and 59. But we can also use PA10 and PA9, which is the receiving RX and the transmit TX. So each of the UARTs have two separate options. So let's say, for instance, I'm using PB6 and PB7 for something else, maybe I2C or a timer 16, or just using the input outputs for the PB7 and PB6. So in that case, we would use PA10 and PA9, and hopefully we're not using those two pins for something else. But if we are, we can always use the UART2. And here's another UART2 for the TX on PA14, and you have the UART2 on PA1 and PA2. And here's the UART2 RX. I'm going to elect to use the UART1 TX on PA9. We'll also use the UART1 RX to receive information, but right now I just want to transmit information on that pin and test that the transmission is correct and functional. The UART1 RX and the UART1 TX, they are both alternate functions, so we have to set up these two pins for alternate functions. But we also have to enable these two pins first. So let's go ahead and enable the GPIO-A. To enable those pins on port A, we need to enable GPIO-A, A enable. So let's go ahead and use that, semicolon, and now the GPIO-A pins are enabled. Whenever we're setting up a GPIO for a port, we need to set up the mode register, the speed register, the pull up, pull down register, and the type register. Let's take a look at the mode register first. If you look at the motor 9, mode register 9, mode register 10, so those are the two pins that we want to affect because that's the RX pin and the TX pin. And we want to change it for the alternate function mode. So let's go ahead and do that. That's a 1 and a 0. So see the 1 place and the 0 place. The 1 place needs a 1, and the 0 place, which is this one, needs a 0. Okay, let's put a 0 in the 0 position of 9 and 10. I'm going to be putting both of them within the parentheses using the OR bitwise operation. This is an easy way to reset 2 bits at the same time. And I want the 0 position. I'm going to use the OR here and for the 10 as well. Okay, now I need to set a 1 in the 1 position. So that takes care of the TX and RX for the mode register. Now let's talk about the speed. What speed should I use for those two pins? Okay, the speed register has low speed, medium speed, and high speed. So where you can find the speed for these is in the actual data sheet. So let's take a look at that. This gives you the IOAC characteristics, but it also shows the speed, the max speed for each of these, the X0, the 0,1, and the 1,1, which matches the X0, 0,1, and 1,1. So the slowest speed is 2 megahertz. The medium is 10 megahertz, and the maximum frequency is 50, 30, or 20. And I doubt if mine will go any more than 30 because 48 megahertz is the fastest you can go on this chip anyway. So, and I think that the low speed is probably going to be sufficient for what I need because the baud rate that I'm going to be using is, we're able to do a maximum of 6 megahertz or megabits per second, I should say. So we can communicate with 1 megabits per second on this if I have it at 2 megahertz. If we wanted to use 6 megabits per second, then you'd need to use the 10 or the medium. The higher you put this, anything higher than the low speed will cause the chip to draw more power. So, there really isn't any need to do anything more than the low, especially during, through these tutorials. I don't think I'm going to go over 1 million baud anyway. So I'll establish the 00. That is what it is on reset, I believe. Let's see, yeah, so reset actually has it like that. But let's go ahead and make them 0 anyway. We'll use the AND equals not again. And I'm going to do both at the same time. And since there are 2 positions, a 0 position and a 1 position, I need to put zeros in both of those. Even though in the second position, or the 1 position, it doesn't require anything because it has an X there. But I'm going to put a 0 there anyway. All right, if we use just the 10, I'll start with 9, and then I'll do the 10. I'll use the OR, okay, and the 10. What this is doing is it's going to use the AND and NOT and put 2 zeros, 1 in each position, because I'm just using the 10 and the 9. If I did 9 underscore 0, it would just do the 0 position, and underscore 1 would be doing the 1 position. But I want both positions done at the same time. Now let's take a look at the pull up, pull down register. So the pull up, pull down is, we have 00 for no pull up, pull down, pull down, or reserved. But I don't really know what state to put this in because, since the reference manual doesn't really talk about what state you need, I'm going to take a look at the timing diagrams or the diagrams for the data frame for the USART. So let's go to the USART section and see if we can find something that gives us a hint. Character description. Okay, this is good. So I'm looking for something like this, which shows the state of the line. And this looks like it would be a line for like TX or RX because it shows the data frame within that area. So I see that the line starts high, which means that, the state is high generally on idle until there's a data frame. And you can see here it looks like it's high and low, but that's only because it's going to another data frame. So what this tells me is there is a pull-up resistor. It is latched high. It is always high. So when you put a pull-up resistor on that pin, it's going to maintain a high level or a high signal until there's a change on that pin to bring it low. So let's go ahead and use the pull up, pull down. So it's 0, 1. So the 1 place has a 0 and the 0 place has a 1. So let's go ahead and do that. Since there's going to be 1 and a 0, we're going to have 2 lines. So let's start with I'm going to go ahead and put zeros in both of them, just like we did on this one here. And that will just reset both of the positions, and then we'll just put the 1 in the position we need. So let's start with that. These are sort of variations that you can use when you're doing your coding. It's almost putting the PUPD in a reset state, like putting 2 zeros in it. So let's go ahead and do that. So we're resetting both positions of 9 and 10. I'm going to do a copy and paste, so it'll be a little bit faster. And we're going to OR, bitwise OR operation, take out the NOT. And we're only going to be affecting position 0 because we need a 1 in position 0. Okay, so that's the PUPD, the pull up, pull down register. Let's go on and take a look at the type register. I think that's O type actually. This one is O speed, output speed, and output type. So you have a push pull state, which is a reset state, which is 0. And then you have the output open drain. Both of these states can function with a pull up or a pull down state. So I'm going to go ahead and just keep it at this state as 0. Since the O-type register, output type register is only a single bit, we can just do this in one line. And we're making the bit 0. I've set the pins to the correct state. Now I need to select the alternate function for these pins of USART TX, transmit, and USART RX, receive. We need to go to the datasheet for this information. not the reference manual, because we need to get the correct alternate function number for these two pins. So GPIO-A, we have 9 and 10 right here. And you can see that there's USART1 TX and USART1 RX. The 9 is the TX and the 10 is the RX. And it is located AF1. So let's see what we need to do to select AF1 for those pins. So this is the low and this is the high. And the low will contain the settings for pins 0 through 7, the 8 pins, the 8 first pins. And then the next one will be from 8, 15. So we need to use the high or the 1. The low is the 0 and the high is the 1. And these are in an array. So we need to set it as AF1. But in this case, I want to set it to AF0 first because that makes them all 0, and then I'll set them to the 1 afterwards. To access the high alternate functions, it's AFR, and then a 1 in the bracket because this is an array. We're going to first reset all of these positions. So we're going to use the AND NOT. Let's see what selections we have. The AFR high H, and we have 0, 1, 2, 3, 4, 5, 6, 7. And you'll notice that in the data sheet, it's actually 8 through 15, but we only have 0 through 7. So we're going to have to use 8 was the 0, so we're going to have to use 1 and 2. So let's go ahead and use 1 and 2. Now we need to put a 1 in those 0 positions. We're going to use the bitwise OR operation, and we may need to use the shift operator. So I want to put a 1 here, and I want to put a 1 here, because this is 9, and this is 10, and we want AF1, which is a 1 here. So that would be 0, 0, 0, 1. So I need to left shift it 1, 2, 3, 4 times, and for this one, I need to left shift it 1, 2, 3, 4, 5, 6, 7, 8. So 4 and 8. Okay, I'm not actually sure if I showed you how to use the shift operator, but it's really simple. We're going to take a 1 that we want to put in some position. We're going to left shift it because when you just put it a 1 just like this, it would start from the beginning, the farthest rightmost digit. So we want to left shift it on this one. We want to left shift it 4, which is 5 positions. It's the 5th position essentially. And let's do a bitwise OR operation again here. So we can do 2 of these. And then this one is going to be left shifted 8 times, which is going to be on the 9th position. So it's like we're walking the 1 from the rightmost position 8 times over, which will land in the 9th position. And the same thing with this one. We're walking the 1 from the rightmost position, and we're left shifting it, walking it 4 times, which will be ending up in the 5th position. All right, so we have finished setting up the pins for the alternate function. Now we need to set up the actual USART. We need to enable USART, and we need to set up the registers for the USART, such as the stop bit, the parity, the number of bits in the data frame, those kinds of things. Okay, so this is at the APB, the Advanced Peripheral Bus 2. So let's go ahead and use that, and we have a USART1 enable. Okay, so let's establish this. Just like doing a line like this, we're going to be enabling the USART. Let's go back to that register we were looking at earlier. And we're using the OR bitwise operation because we want to set the USART enable to 1. So here it is, the USART 1 enable. Now the other items that we need to set are going to be the baud rate and the data frame specifics. The first register we need to set is the baud rate. So let's see how to do that. We're going to, just like the GPIOA we specified before, we're going to use USART1. All of the parameters, data, the flags, the statuses, the registers that we need to access will be under USART1. So the BRR, you can see all of the different items we can set here. So let's start with the BRR, which is the baud rate. So let's take a look how to do this. The baud rate register requires us to determine the baud rate and establish a specific USART division, which is like a prescaler. So we have to come up with this USART division to find the correct baud rate. So if we take our clock source, which is 48 megahertz, and we actually divide the baud to get the USART division. So if we use a calculator and take 48 million, and let's say we want 9600 baud, we just divide that by 9600, and that equals 5000. So let's see what else we need to consider. So it shows that we have to multiply this by 2, the clock, which would be 9600 baud, or 9600, and divide that by the baud to get the USART div. But that's only if you're oversampling by 8. And I'm going to be oversampling by 16, and I'll tell you why. I want the most oversampling I can get. So the reason why you pick oversampling by 16 is if you're more interested in the quality of the information coming in. And the oversampling by 8 is best for speed. You can see this and get more information in the selecting the clock source and proper oversampling method. This is on page 604. And it shows if you're doing it by 8, you achieve higher speeds, and by 16, you increase the tolerance of the receiver. But there is one caveat to using the 16, and if you have a 48 million internal clock speed, you divide that by 16, and you have 3 million left over. And if you divide it by 8, which is oversampling by 8, you can achieve the highest, or the 6 million bits per second, the 6 million baud. The 1 bit is also pretty important when it comes to the quality of the bits coming in. And this uses the majority vote, and where the majority vote, it takes the majority vote of the 3 samples in the center of the received bit. So when you're talking about the center of the received bit, that is the cleanest part of the bit coming in, because when you have a change from high to low or low to high, and then you have a change from low to high or high to low, at the center of that is where there is less transient response, or there's less bouncing up and down of the transmit and receive line. So at the center, you're going to get the cleanest signal. And at that center, you're going to have the majority vote for 3 of the samples. And that looks like this. So the majority vote, if there's 2 or more of a specific 1 or 0, then it will be that particular bit. So like 3 zeros would obviously be a 0. 2 zeros, there's more zeros than there is 1, and that's obviously a 0, and so on. And you'll also see that there is a status that we can access that will tell us if the signal wasn't clean or not. We know this one is perfectly clean. This is all zeros, and this one is perfectly clean, and that's all ones. But the ones that have mixed zeros and ones, those we can actually tell if they're clean or not. And we can, if we want, do something about it. We can inform, let's say, a retransmission of those bits. So let's go ahead and set the over 8 and the 1 bit. Let's see, where would that be? The over 8 bit is located in the control register 1 for the USART. We'll do the BRR a little bit later. And now we want to set the 1 bit. So let's see if we can find that one. So the 1 bit is located in the CR3. The 1 bit is right here. And let's just make sure that we have the right one. The 3 sample bit method, which is the majority vote method. Now we're ready to specify the baud rate. So the baud rate is going to be just equal to a particular number. We don't have to use any bitwise operations, because we're just going to assign BRR the baud rate, or the number that we have to specify for the baud rate. So if we go to the BRR, I think it's somewhere around here. Yep, this is the next one. You can see that it's 16 bits, and the 16 bits is used for just a specific number. When the over 8 is set to 0, we're using 16. This is the, actually no, this is the, it uses the entire 16 bits when over 8 is equal to 0. When over 8 is equal to 1, you have to take the portion of the BRR 0 to 2 and shift it to the right. So since we're not doing that, we don't have to worry about this. We're just going to put the number right in from 0 to 15, which is 16 bits. So just to reiterate that and make it more clear, in the baud rate generation on 23.4.4 on page 607, you'll see that it says when over 8 is equal to 0, then BRR is just equal to the USART division, like a prescaler. And when the over 8 is equal to 1, and that means that it's only 8 oversampling, then you have to take the 0 to 3 shifted 1 bit to the right, which is the BRR 2 from 0 to 2. The number 3 must be cleared, must not have anything in it.
and then the 15 to 4 to 15 has the remaining part of the USART div. So this is a little bit more complicated, but if we ever want to go above 3 million baud, 3 megabits per second, then we would consider doing this. And I'm probably never going to go over 3 megabits per second in serial communication. So I'm going to maintain this specification here and just make the BRR equal to my USART division. And to find that out, it's 48 million, which is our clock speed, divided by, let's say, 9600 baud, which I've already done before, and that's 5000, which I did here. So the 5000, it actually has a table for the common ones, the 9.6 kilobits per second. If it is overclocked by 16 here, then you can use the hex code of 1388. So let's just verify what that is. So the decimal value is 5000 and 1388, so that's correct. So we would put this, or we just put 5000 into the BRR. I'm going to move this to the last line before I do that. I'll bring this with it. And we're just going to put 5000 in here. I could have put the hex number in here, but 5000 is very easy to understand. We did the division correctly. So let's talk about the data frame for a moment. The data frame consists of a start bit, a number of bits to form a word or a byte, which is just a character or something like that, which is like the letter A or a question mark or something like that. A parity bit, and a parity bit is only used for determining if a problem occurred in the communication. It's really sort of a check. And then 1, 1.5, or 2 stop bits. The idle on the line, like the transmit line or the receive line, is always going to be a high line, a high signal. So it's going to be at the top. The top would be a 1 and the bottom would be a 0. So a line going across here would be a high or a 1. So the start bit has to be a 0 to tell the other device that's receiving that a byte is coming. To form code, let's take a look at this in a vertical way. So we're going to be setting a start bit. Then we're going to form the byte. So set bit 1, 2, 3, 4, 5, 6, 7, and 8. And it doesn't have to have 8 bits. It can have actually 9 bits or 7 bits as well. It's how you're going to set up the data frame, which we'll talk about in a second. Then we either use a parity bit or not, and that is in the setup of the data frame. We can elect not to use a parity bit if we feel that the communication is going to be error-free or this isn't a critical application. And then we have the 2 stop bits. So this is an example of like how we would write our code to create the data frame. But let's go ahead and set up the data frame first. So let's take a look at what we need to change. The start bit is something we're going to either set. The start bit is not something we can change, but let's put it there anyway. We need to set the number of bits in the byte and then parity and stop bit. Let's take a look at the reference manual. So let's go to the datasheet, the programming reference manual, and let's go to the USART section. And specifically, I'm interested in the control register 1 for now. And the control register has pretty much everything we'll need to set the data frame. Right off the bat, we can see that it starts with the M1, which is the word length. There's also an M0 we should look at as well. But let's take a look at M1. And if M1, which is bit number 28, this is one of the bits included with M0. So you need to take a look at M0 and M1. So M0 is here at number 12 and M1 is at number 28. And these work together to determine what specifications for the data frame, specifically for the start bit and the data bits. So let's take a look at M0. Let's see if it has M0 here. Okay. So this particular one determines a 0 and a 1 for either 8 data bits or 9 data bits. So let's take a look at M1. So you can see that if M0 is 0, which is right here, that's 8 data bits. If M0 is 1, then it's 9 data bits. M1 is both 0 in those two cases. So I'm never going to use 7 data bits. I'm always going to be using probably 8 or 9, but in this particular demonstration, I'll be using 8 data bits. So this actually, the M1 and the M0 need to be 0. You can see M0, for 0, it's 8 data bits. So those two, the M0 and M1, work together in determining the 8, 9, or 7 data bits. It can also be noted that 00 is the reset value, so it's automatically set for 8 data bits. We can go ahead and add those lines of code just so we make sure that we're setting it for 8 data bits.
Okay, to change the word length, we access the control register 1 and the USART 1. We're going to be turning off, which is resetting or setting the M0 and M1 to 0. So the AND not bitwise operation is going to be used. So we can do both of them at the same time. Let's see what it gives us using the control spacebar. I don't see the M0 and M1. So that's interesting. Let's look at the M. Let's go to the declaration. I'm clicking on the right button on this define and open declaration. And it says word length, which is the correct one. By setting this to 0, it'll be 8 data bits, and setting it to 1 will be 9 data bits. So I don't see where the M1 is located. The M0 was at the 12th bit location, and the M1 was at the 28th bit location. And it looks like there is no such location. Okay, so I guess we'll just use the M0. That's all we have to do to set it for 8 data bits. So this is setting the word length to 8 data bits. Now let's look at parity.
So there are 2 bits in the control register for parity. One is either enabling it or disabling it, which its reset value is disabling, and you can select which one you want to use, even or odd. I'm not going to enable it for this particular demonstration, so I'm going to just keep it at 0, and it doesn't really matter which one this is on because it'll be disabled. If you do use the parity and enable it, and you set it either to even or odd, you'll have another bit in the ISR, the status register, the interrupt and status register, and you'll have a PE, and this is a parity error. So you can determine whether there was a parity error or not. And this is mainly used in the receiving portion of the serial communication. So when this parity error shows up, you can do whatever you need to do to either inform of the error or send to the transmitting side that there was an error, and you can request that information be resent, possibly. So let's go back to the control register. And the last part of the data frame is the stop bits. So let's take a look at that. I think that's in the control register 2, stop bits here. Okay, so it has two bits. So let's take a look at what we have to do on that one. On the stop bits, the reset value is 00. Let me just double check that. Yeah, the reset value is 00. And that means it has 1 stop bit. A data frame has to have a start bit and a stop bit, so it informs the receiver that is the data frame, the beginning and the end of the data frame. And in this particular case, I'm using, or it's reset to 1 stop bit, and I'm going to maintain that reset state. I need to set that at the reset condition. So that was the PCE, and I want to make sure that that's disabled.
All right, so let's first disable the parity feature. And we're looking for PCE. Now for the stop bit, we're going to only have 1 stop bit. This is in CR2. And since we're resetting it, we're using the AND NOT operation. Okay. All right. So we have completed the setup of the data frame. We are going to do a transmit test. So we're going to test the microcontroller and transmit it to a device. In this case, we're going to transmit it to a logic analyzer, and we'll get into that a little bit later, but we want to enable the transmit. But if you are going to use another device as a receiving, like a computer or the servo that we're going to be doing later on, you need to do all of this. You need to set that device to these settings as well. And so you'll want to make a note of the settings that you've created here. And when you get to the setting of the next device, you'll need to remember how you set this. So let's go ahead and enable the transmit. We're not going to enable the receive because we're just not going to transmit and then receive back to the same microcontroller. That wouldn't make any sense. Although we could probably do that, and we can look at various variables. We could set up variables in the program and see how the variables react in our testing. But I'd rather do this using a logic analyzer. It's a device that you're able to see what's going on the USART transmit line, and it serves as like another device and it's receiving. And we will have to set it up exactly the way we're setting it up here. So we'll need to set that up for the 8 data bits and disabling the parity and using one stop bit. So let's go ahead and do the transmit enable and carry on with the programming. Okay, so the transmit enable is bit number 3 on the control register 1. So for transmit enable, we want to enable it, so we want to put a 1 there. We're using the OR bitwise operation because we're setting this transmit enable. And now we actually still need to enable the USART. And I know that I said that we're doing that here, but this is actually just enabling it under the reset clock and control register. We actually need to enable the USART. We set everything up with the USART first, and then we need to actually enable the USART in the control register. USART enable here, the UE. This is when you actually enable the USART, and all of the control parameters being set in the USART need to be set before this actually happens. So the UE is the main mechanism that starts the USART, and then you can start to communicate after that. So let's go ahead and enable the USART. And putting 1 there is USART enabled. So let's use the OR bitwise operation to enable the USART. Now we're ready to start transmitting. Because these 3 are all the AND NOT, you could actually put this in one line and just put all 3 of these as an ORing each other, as you've seen me done in previous videos. And this one as well, we could do this in one line if we wanted to. But in this particular case, I'm going to keep it in as separate just so it's more clear what's going on in this tutorial. And specifically, we're going to be only doing a transmit, and we're going to test the line using the logic analyzer to see what's being transmitted. The way that this microcontroller allows you to send data over the transmit line is it has a register called the TDR, the Transmit Data Register. There's also a shift register. And then there's a flag called the TXE, the Transmit Empty, and that is a single bit, a 0 or a 1. The Transmit Data Register is 9 bits long. That is because you can either have 7, 8, or 9-bit data, depending on how you configured the data frame. And the shift register is going to be the same. But you don't have to really be concerned with the shift register. But here is how this process happens. By default, the TXE, Transmit Data Register Empty, is going to be a 1 because there's nothing in the Transmit Data Register. You're going to put data into the Transmit Data Register to be able to transmit this data on the transmit line. So once this is done, your Transmit Data Register Empty flag will be 0. The data is then put into the shift register, and now the TXE Transmit Data Register Empty flag will be a 1 because there's nothing in here. So now you can go ahead and put the data into the Transmit Data Register. And now the TXE Transmit Data Register Empty flag will be a 0, telling you that you are not allowed to put anything into the Transmit Data Register. The data in the shift register will at some point go to the transmit line. And now this data will go ahead and be transferred to the shift register. The TXE will be a 1 again because the TDR is empty. So now data can come in here. Now the TXE will be a 0 again. At some point, this shift register will transmit the data. And this happens over and over again, as long as you have data to transmit. And this will happen over and over again until you run out of data. We'll be using the while loop to wait for this Transmit Data Register Empty flag to happen before we put the data in. So let's go ahead and take a look at how to do that. In the ISR, the Interrupt and Status Register, there is a TXE, which is the Transmit Data Register Empty flag. So we can use this Transmit Data Register Empty, and that's the TDR register. So we're going to test this, or we're going to wait while it is 0, not transferred to the shift register. We're going to wait during that time, and then once a 1 appears in the TXE, then we can proceed and put some more data into the Transmit Data Register. I'm going to put this code in the while loop because I want this code to keep running over and over again so I can capture the communication with my logic analyzer, and you'll see why later on. So first we want to make sure that the TXE flag is a 1, which means that the transmit data register is empty. So essentially, we're going to be making sure that the TXE flag is waiting while it's a 0. Then we want to put in the data or the character into the TDR register. And then we want to repeat a number of times that we send the message that we want to send. Let's write this condition for the flag first. It's in the ISR register for the USART. And we always use the AND bitwise condition to test a particular bit in a register. And we're waiting while it's a 0, so we don't want it to go to the next step until it's a 1. So while it's a 0, it stays here. Now we want to add the character to the TDR transmit data register. And we're just going to be using the equals because we just want the data to be put directly into this register. We don't need to have any bitwise operations here because we're not really affecting the bits. We're just adding data right into this register. And we can just put in a character, just like this. It doesn't need to be a number. It doesn't need to be a hexadecimal value or a bit value. It can just be the actual data that you want to send. And in this case, I want to send an N because I'm going to be spelling out NewbieHack, which is the name of the website that is coupled with these videos. You can, of course, put in the number that's associated with the N, which is an ASCII character code. You can also put in the hex value or the bit value, which is the binary number. But to make it easy, I'm just going to be putting the N here. I'm going to be repeating this for the number of characters that I want. Here we go. Okay, so I'm going to be spelling out NewbieHack. I just did a bunch of copy and paste. And of course, I'm doing it this way so you can understand what's going on. And it's going to be easy to understand why we're going to be putting this in a function later. So let's go ahead and do this. NewbieHack and E. I'll use lowercase and uppercase letters. W, B, I, E, H, A, C, and K. Okay, so it's going to continually send out the word NewbieHack over and over again until I turn the microcontroller off. And that's really it. That's all it takes. But you can see that this is very repetitive. So later, what I'll do is I'll create a function to do this all in one step, all in one line. And then I'll create another function to do an entire line in one line. So you can just send a string over the transmit line. So you're seeing step by step how a library would evolve essentially. So I'm going to plug in the microcontroller and do the run for the first time. Okay, I'm going to plug it in. I got a download verified successfully, shutting down exit. So it is running right now. I didn't get any errors in the code, but that doesn't mean that I won't get any runtime errors. So what we have to do now is put a probe on the TX line, which is I think it was the pin 10 of port A. Turn on the logic analyzer and see what's on that line. I inserted male pins into the ground and into the purple wire here because I intend to use the ground. Well, you have to use the ground, and you're going to put that in the ground into the ground power rail. And then number 7, I'm going to insert this into the pin number 42, which is the transmit line. All right, so it looks like all of these are being shown here, all the channels. So I want to clear all of those, and I only want to show channel number 7. I'm going to remove channel number 0. This is the device settings. I don't think I need 16 million cycles per second, so I can probably go down to maybe 1 million cycles per second so I can get more data. And I'm going to go to the analyzers, and I want the async serial. Let's go ahead and edit that and make sure that I have all of the information correct. I have channel 7 here, 9600 baud, 8 bits for the byte, which is standard, 1 stop bit, which is a standard, no parity bit. This all conforms to what I have in the microcontroller. I'm not going to do an inverted. Let's see, let's go ahead and save that. And I'm going to unplug the microcontroller. I'm going to start sampling first because I don't want the first frame to be in error. And I'm going to go ahead and plug it in. Now you'll see data start coming in. I'm going to stop it because obviously it's only one word. I probably got a bunch of them. So let's see if I make this a little bit bigger, and then I'll make this part bigger here so I can see what's going on. So the data, it's nothing for a while. And then as I scroll down, you can start seeing newbie hack. So it did work. It's successful. We can change how or what the data results are. Looks like if I make it binary, you can see the binary version of it. If I do decimal, you can see what the decimal number is represented. ASCII, so you can see in whatever form you wish. You can also take a look here at the actual results from the sampling and what the line was. Let's go ahead and take a look at. So there were some framing errors there, and then newbie hack came up here. So I guess this is the framing errors were happening while the microcontroller was starting up. You can see how many samples happen in a very small amount of time. And that is how to initialize the USART and transmit on the USART.